Lecture 1, Software Development in Practice.
Hello and welcome to CS5150 Software Engineering. This Cornell course is for master's students and seniors in computer science and related disciplines. It's a transitional course. It bridges the gap between academic computer science that you learn in universities and practical software development in the outside world. This first lecture has two objectives. The first is to explain why large-scale production software is different, and the second is to introduce some of the themes that occur throughout the course.
This is not a course about programming. We assume that you're technically proficient. We assume that you know a good deal about computing, that you can program reasonably, and you can learn more on the job. But in software development, success or failure depend on many factors beyond writing good code. When you leave Cornell, you're going to work on production projects, where success or failure may literally cost millions of dollars. Soon, you may be in charge of these projects. If you have your own company, it may be your money. We don't want you to make mistakes, but if you are going to make mistakes, we want you to make them now and to learn from them. Let me tell you a little bit about my own experience. For much of my career, I was in charge of computing at universities, such as Dartmouth College and Carnegie Mellon. I also spent some time in industry. During this time, I was in charge of a wide variety of projects: operating systems, compilers, early campus networks, routers and the protocols that they use, distributed computing environments, file systems and so forth. I also had responsibility for administrative data processing like general ledger and payroll systems, and I've had a long-term special interest in digital libraries. The overall theme has been the first production systems, where the methods had previously been used only in research. During the course, I will describe some of these projects, both successes and failures, and mainly I will describe them from the viewpoint of a senior manager.
This brings us to the first theme of this course, the variety of software products. Many of your projects will develop applications, maybe websites or mobile apps for smartphones. But there are many other types of software. Here are some examples. Developing a website is very different from developing, shall we say, a system for air traffic control or for scientific computing.
Why is this variety important? It's important because there are some people who will try to tell you that there is one and only one correct way to develop software, and they will try to cast scorn on other methods. They are wrong. Software projects are very varied, client requirements are very varied, and as a result, there's a variety of ways to build software, some of which are appropriate in some circumstances, others in other circumstances. Don't let anybody tell you that there's a standard process for software engineering. There isn't. There's no best language, no best operating system, and so forth. A skilled software developer has to know a wide variety of approaches, methods, and tools. The craft of software development is to select appropriate methods for each project and apply them effectively. Despite this variety, there are some principles that apply for all software. First of all, what is good software? There are certain general characteristics of good software. Functionality, it works. Usability, people can use it. It can be maintained, it's reliable, it's efficient. Good software products require good programming, but programming quality is not the end. It's the means to the end, not to the end itself. Now for a second theme, money. Software is expensive. Every project spends a lot of money on people, the salaries of skilled professionals. But there's another cost which sometimes is even bigger, and that's organizational change. To introduce a new computer system into an organization often means lots of changes. Later in the course, we will see 2 examples of projects where good software failed because the organizations were not prepared to make the necessary changes. Since software is expensive, if you're in charge of a development project, the first question you should ask is, who is paying the money? And what does that person or organization want? What do they consider success? What do they consider failure? Technical people may have very different criteria for success from the people who are in charge of the organization who are paying the money. It's important that you understand what they want, not just build the system that you think is technically good. Every software project has a trade-off between the functionality, that is, what does the project do, the cost to develop it, and the time to develop it. If the client wants to add extra functionality, there will inevitably be extra costs for development, testing, and maintenance, and this will take more time. So the question is, what is important to the person who is paying? Listen to them and build the system that the client wants. Here are some examples. At Dartmouth College, we developed a new general ledger financial system. The people who use the system, like the controller's office and the treasurer's office, kept asking for more functionality. But the president made it very clear that time was crucial to him. He wanted the system to be in operation on July the 1st the following year. Therefore, we developed a minimal system with just the basic functionality that we could deliver on time. If you're involved with startup companies, you'll find this is particularly important. You need to have the features that will generate real customers who will pay for the product, but you want to have as simple a product as you can so that you can actually start getting some money. The next 2 examples show some of the contrasts. Think about car anti-lock brakes. They have to work. The functionality has to be really solid, because if they don't work, if there are bugs, there may be accidents and people will lose their lives. So functionality is vitally important there. Contrast this with some features in a cell phone, such as a web browser. Of course, the browser is important, but it may be more important to ship the product on time, even with a browser that is incomplete or not fully tested. I've already used the word client as the person for whom a software product is developed. I want to make sure we have the same understanding of this term, and then I want to say a few words about customers and users. The client is the person for whom the software development team creates the software. The client will provide resources and expect some product in return. Usually the client is a member of the organization that's providing the money, and the client's job success may depend upon the success of the software product. Satisfying the client is a primary measure of success in any software product. Here are some examples of types of software and who the client is in each case. So for each category of product, who is the client, who is providing the money, and what do they want? So first of all, a bespoke system, a one-off system, for example, for a government department like the IRS. Here it's fairly straightforward. The IRS is providing the money. The head of the IRS or some senior person within the organization is responsible for it and is the client. And what they want, of course, is a system that works and does what the money was provided for. A slightly more complex system is one in which there is a generic package. For example, Cornell's payroll system is based on a general package developed by PeopleSoft with modifications for Cornell. the person doing the modifications is responsible both to PeopleSoft and to Cornell. Typically, the client in this case will be a department of Cornell, and PeopleSoft will be writing this software for Cornell. A product like a cell phone is more straightforward. The product manager in charge of the cell phone will require software. This is the client, will provide the money, and what they want, of course, is software that is working reliably before the delivery date for the system. Research projects are another example where there's some ambiguity. For example, the Cornell Web Lab, which I was involved with for several years, we developed the software for the National Science Foundation using National Science Foundation money. I would say in this context, I, as the principal investigator, was the client, and the National Science Foundation clearly was a very interested party. Finally, let's ask, who is the client for a general purpose package, for example, Microsoft Excel? The important thing to understand is, although this product is sold to customers, they are not the client. For a small package, the client might be a marketing division within the company, but for a package as big and important as Excel, the client is the company, Microsoft. I'm sure that at Microsoft there is a group of senior executives who are responsible for Microsoft Office, of which Excel is one part, and within that group of senior executives there is one person who is explicitly charged with making sure that Excel works, and he is the client, or she is the client. Customers and users. A customer is the person who buys the software or selects it for use by an organization. That is, the development is not directly done for the customer, but clearly the client will be thinking, what does the customer want? What will lead customers to buy this piece of software? The user is the person who actually uses the software. And this may not be the same as the customer. With personal software, it very often is. If I buy a package to use on my computer, I am both the customer and the user. But in organizations, the customer may be, for example, a purchasing department, and the users are different people. So the Cornell Finance Office uses Microsoft Excel. The customer will be the person who does purchasing for the Cornell Finance Office. The users are the people in accounting and payroll and other financial offices who actually use the program.
Lecture 1, end of Part 1. Lecture 1, Software Development in Practice, Part 2.
Risk is a theme that runs throughout software development. Many, probably most software development projects run into difficulties at some stage. There are many problems, but they can be grouped together in our normal three categories. Function, the software does not work as expected, or it is full of bugs. Cost, the project is over budget. Or time, late delivery. Surveys suggest that perhaps 50% of all software is never used. It's never used because it does the wrong thing, that users dislike to use it, there are no customers, or circumstances have changed during the development. Underlying these causes of failure, there is the risk that the software developers build the wrong software. They build the software that they think the client wants, and it turns out not to be the software that the client actually wants or needs. This is why it is so important that the software team must understand what the client expects of the software and understand what the client's organization expects of the client. The software development team will often have insights that the client or the organization don't have, and they should offer suggestions, they should offer technical insights, but fundamentally the decision belongs to the client. Remember that client satisfaction is a primary measure of success in a software project. The first sentence on this slide may seem too strong, but it's true. Failures of software development projects can bankrupt companies. It's particularly the case when the software is part of a product that's being brought to the market. If it's late or if it doesn't work and the product doesn't sell, the company may suffer enormous financial loss. So whatever you're developing software, think about the risks from the client's point of view. What is the penalty to the client if the software is late, if it's over budget or it does not work or it's full of bugs? Failure of a software development project will often cost senior executives their job. For example, when Apple tried to compete with Google Maps, they released a mapping application that was weak. Customers didn't like it, it had lots of troubles. The executive who was in charge of that project didn't stay in his position very long. If risk is a problem in software development, it is worth taking effort to minimize risk. Here are several things that you will be doing during your project. They all involve communication between the client and the development team. First of all, a feasibility study before you begin the project so that you all know what's going on and you know that it's worth doing. Secondly, understanding the requirements, which are what the client wants, and separating that from the design, which is how you, the developers, meet the requirements. As the project continues, there will be various milestones and releases where the developers report or demonstrate progress to the client. Finally, when the development team thinks the job is complete, there's a period of acceptance where the client tests the software and makes sure that it meets the requirements. The acceptance may include user testing, which will usually be done jointly with the developers. Finally, the handover, where the completed product is handed over to the client, is an important part of the project in its own right. The term visibility is used in software development as a technical term. The people who take responsibility must know what is happening in a project. And in fact, everybody involved in a project should know how the project is going. The problem as seen by a manager is that he or she must rely on others for reports of progress or difficulties. And software developers are not very good at reporting progress. They have difficulty evaluating progress. In particular, they're usually optimistic about progress. They consider reporting a waste of time and so forth. You will make regular progress reports on your projects as part of your milestones. And we have a full lecture talking about ways of managing progress. Incidentally, working software provides excellent visibility, and if you have anything to demonstrate or anything that can be released early, that is tremendously useful in a project. Finally, I would like to just mention a technique that's become very important recently in software development, particularly for web companies and companies with that sort of development. Everybody who's worked in software knows that small projects are easier to manage than big ones. If you have a small project with a small team working for just a few weeks to produce a specific deliverable, it's much easier and much less risky than large projects. So risk is minimized by frequent delivery of working software. If you have releases every few weeks rather than every few months, clients and customers and users can evaluate the work and their opportunities to adapt to changing circumstances. This is one of the basic principles of agile software development. Teamwork is a fundamental theme that runs through software development. The challenge is not how to make each individual productive, it's how to make teams effective. This is particularly true with large software projects. Such projects usually are built on older ones, and it's rare to start a new system from scratch. So how teams build on the work of others is a fundamental skill of software development. Much software is built in increments with different teams responsible for the increments. So how can different teams work together to create a good software product? You will find that large and very large systems have different needs and need different ways to be managed. In this course, we'll spend quite a lot of time on software design, because with large projects, it's very important that the software architecture is well established and understood by all parties. We're also going to put some effort into object-oriented program design, which is another very important building block in large-scale systems. With large-scale systems, there are some parts that can be built individually, but some parts, such as reliability, testing, and verification, have to be done at a system-wide level. Finally, this is always made more difficult when the system is building on old legacy systems from the past.
A few words about scale. Your CS5150 projects are about 0.3 of a person year. That is very small by production standards. It's about the size of 1 or 2 sprints in a typical agile process. In contrast, a really big project may be 100 or 1,000 or even 10,000 person years. That is, thousands of people working for many years. These large systems are developed by many people, and those people will be constantly changing throughout the project. Before a big project is completed, you can be sure that the requirements will have changed many times, and you can be sure that no large system is ever complete. Moreover, nobody will fully understand the entire system. Nobody will comprehend more than a fraction of the project. I hope that many of you will have the opportunity to manage large software projects. It's challenging, but it's very satisfying when things go well. If you do, you'll find you're always thinking about the software as a product. You'll be thinking about things like quality control, performance, usability, and security. You'll be thinking about maintenance and how the product is going to evolve in the future. You'll need to think carefully about how you're going to manage the project. You're going to need to manage people. You're going to have to be aware of the economic, legal, and social environment in which the project is being done. And you'll need to have a development process that's appropriate for your particular system. In this course, we're going to look at 4 of these processes. We're going to look at iterative refinement. We're going to look at a variant of it called spiral development. We're going to look at the modern agile methods, what they can do and what they can't do. And we're going to look at some of the traditional sequential methods.
To complete this introductory lecture, I want to talk about professional responsibility. Organizations rely on software developers. They assume that you're competent. Software that does not work effectively can destroy an organization. They trust you to develop good software. In developing software, developers and particularly system administrators may have access to highly confidential information, trade secrets, personal data, and so forth. Software is developed in a complex legal environment involving intellectual property, obscenity, contracts, and so forth. We have a lecture on this subject, and it's an important one. Finally, there's acceptable use and misuse. Computer abuse can paralyze an organization, and developers are very much responsible for making sure it doesn't happen. There was a famous example at Cornell where a PhD student in computer science released on the internet a worm that he'd been doing research on and essentially paralyzed large portions of the internet. Academic integrity and professional practice. Software engineering is a collaborative activity, and you should always feel encouraged to work together as teams. But there are tasks, particularly in a course like this, there are some tasks that require individual work. The general rule is always give credit to your sources and collaborators. It's good professional practice to make use of the expertise of others and to build on previous work, but only with proper attribution. It's unethical, and in academic life it's called cheating, to use the efforts of others without attribution. There is a page on the course website called Academic Integrity. It says some things about software development, and it points to the Cornell code. I expect everybody to read this and to follow this code.
End of Lecture 1, Software Development in Practice. Lecture 2, Steps in the Software Development Process.
This is the first of 2 lectures that look at processes for software development. There are many varieties of software, and correspondingly, there are many varieties of process for software development. But there are certain activities that occur in almost every project. Things like user interface design, coding, and acceptance testing. In this lecture, I look at some of these activities. In the next lecture, I will show how they can be combined into a procedure to create a software product.
The fundamental assumption behind a lot of software development is that good processes lead to good software. Good processes should reduce the risks, and good processes should enhance visibility. Good processes should also enable teamwork. There are a variety of software processes, and this is necessary because software products are very varied. Therefore, there is no standard process for all software engineering projects. But successful software development projects all need to address similar issues. This creates a number of process steps that should be part of all software projects, and the purpose of this lecture is to define those steps.
This slide summarizes basic steps that are part of almost all software development projects. Before beginning the project, there is a feasibility study and planning to decide whether or not actually to do the project. Then there are a series of steps that you could consider as part of the development: requirements, user interface design, system and program design, the implementation, that's the coding, and finally acceptance and release. When the system is put into production, there is a phase of operations and maintenance. These steps may be repeated many times during the development cycle, but it's important to distinguish among the steps and to be clear which you're doing at any given moment. Notice the final sentence on this slide. There are some important aspects of software development, such as testing, security, and performance, that are part of many of these steps.
Now let's look at some of these process steps in more detail. First of all, feasibility. A feasibility study is the very first thing that you do with a project. It precedes the decision to begin a project. This is where you ask questions like, what is the scope of the proposed project? Is it technically feasible? What are the projected benefits? What are the costs, timetable, and so forth? Are the resources available? What are the risks and how they can be managed? A feasibility study leads to a decision, go or no go. Should the project be done? Your first assignment is to do a feasibility study for your project. And there is a full lecture on how to go about feasibility studies. Requirements are the first step in the actual development. They define the function of the system from the client's viewpoint. They establish the system's functionality, constraints, and goals, and this is done by consultation with the client, customers, users and so forth. And they must be done in a way that the client and the development staff understand so they can reach agreement. This step is sometimes divided into stages: requirements analysis, requirements definition, requirements specification. And the requirements may be developed in a self-contained study, or they may emerge incrementally. Getting the requirements wrong and failing to agree on them is probably the biggest single cause of software projects failing. If the client and the development team do not agree about what the requirements are, the project is almost doomed to failure.
Usability is of very great importance in modern software, and that requires good user interface design. User interface design itself cannot be done in the abstract. It has to be evaluated with users. Therefore, user interface design is iterative. You will design the user interface, you will test it with users, you will then revise the user interface based on the evaluation, and you'll repeat this loop until there's a user interface that the client and the development team are happy with.
Next step, the system and program design. The design describes the system from the software developer's point of view. The system design establishes an overall system architecture, both hardware and software, that matches the requirements. Then the program design represents the software functions in a form that can be transformed into one or more executable programs. User testing is often carried out as part of this design step. When we talk about program and system design, we will also talk about modeling. Models are used to represent requirements, system architecture, and program design. This course will teach the basic concepts of one of the leading modeling languages, the Unified Modeling Language known as UML. You are all familiar with the next process step, the actual implementation. This is where the program code is written. The software design is translated into a set of programs or program units. In a production system, these software components may be written by the development team, but they can also be acquired from elsewhere or modified from existing components. Program testing is an integral part of the implementation. This is done by the development staff. Individual components are tested against the design, and then the components are integrated and tested against the design as a complete system. When the implementation is completed, then the development team hands the system to the client for acceptance testing. So the purpose of acceptance testing is for the client to test that the system meets the requirements. Often this is done with selected customers and users, and the development team often help with the mechanics of the testing. After successful acceptance testing, the system is delivered to the client and released into production or marketed to customers. The final step is operation and maintenance. With operation, the system is put into use, and with maintenance, errors and problems are identified and fixed. Over the years, a big system is likely to change, is likely to evolve. Requirements will change, new functions will be added, it'll have to adapt to a changing technical environment, and after many years, a system may be very different from the original system put into production. Eventually, it will be phased out and the system will be withdrawn from service. These steps are sometimes called the software life cycle. Quality control applies to almost all the steps. During the requirements step, there's the question of validating the requirements. The program and system design also need to be validated. Then we have usability testing, program testing, and acceptance testing. Finally, once the system goes live, there is bug fixing and maintenance. People often get confused about the word testing. The term is used in several different contexts, which are indeed easily confused. User testing is to test whether the user interface is convenient for users. So for this, versions of the user interface are tested by users, and their experience may lead to changes in the requirements or the design. Program testing, I think you're already familiar with. The development team tests components individually, unit testing, or in combination, which is known as system testing, against the design to find bugs. Finally, when the development team thinks they have a completed system, we have acceptance testing, where the client tests the final version of the system, or parts of the system, against the requirements.
Almost every software project will include these basic steps in some shape or form, but there are many variations in how you do it. The steps may be informal or they may be formal. They may be carried out in various sequences. You may do them once, or you may repeat them. The way in which the steps are combined is called a software development process. And in this course, we're going to concentrate on 4 major alternatives. The first is iterative refinement. Here the idea is that you go quickly through all the steps to create a rough system. This is evaluated by the clients and the development team. And a second iteration, followed by a third or even fourth iteration, is carried out, steadily improving the system before it's released. Spiral development is a variation of iterative refinement, which I believe was first made popular by Microsoft for their large systems like their operating systems. Here the idea is to create a stable version of the system which lacks some of the functionality. New and updated components are added to the developing system by the development team when they're ready. Agile development is a family of techniques in which the development is divided into a sequence of small sprints. The aim is that each sprint should create deployable code. Finally, we're going to look at the waterfall model, or in practice the modified waterfall model. In this model, the idea is to do each step once, complete that step, and then move on to the next.
You will sometimes hear the terms heavyweight and lightweight software development. I think these terms are quite useful. In a heavyweight process, such as the modified waterfall model, the development team works through each process slowly and systematically with the aim of fully completing each step and delivering a complete software product that will need minimum changes and revision. In a lightweight process, the development team works more quickly and releases working software in small increments. Each increment includes all the process steps, but there's an expectation that changes will be made based on experience. And the best example of this is agile software development. Here is a chart from the Manifesto for Agile Software Development. You need to be careful with a chart like this because it's developed by enthusiasts, and the Agile Software Development Manifesto was certainly written by enthusiasts. They are inclined to not realize the weaknesses of the lightweight methodologies and to overemphasize the weaknesses of the heavyweight methodologies. But I think this is quite a useful chart in comparing the approaches of the two methods. Take a look at it and see if you find it useful. One final thing while we're talking about processes and process steps is the concept of a deliverable. A deliverable is some work product that is delivered to the client. In a heavyweight process in particular, each step creates a deliverable. This is often documentation, mock-up of user interfaces or something like that. Might be a requirement specification. One of the aims of lightweight processes is to reduce the number of deliverables and to emphasize incremental working code with minimal supporting documentation. For the course projects, we're going to ask you for something in between, and at each of the 3 presentations, you're expected to provide a report to the client and to the course team, which summarizes what you've done up to that moment. To end this lecture, I'd like to look at an old exam question. This question is very similar to the type of question that you're going to get in your tests. So here's the question. An online information system is being developed using a modified version of the waterfall model. It's likely to be based on web technology. How much should the choice of technology be considered during the feasibility study? In how much detail should the choice of technology be specified during the requirements phase of the project? At what stage should the decision be made to use an Apache Web Server 2.0 with Tomcat 4.1? Although this question talks about the waterfall model, the question actually applies to all software processes. So first of all, how much should the choice of technology be considered during the feasibility study? Remember that the goal of the feasibility study is to ask whether a project is feasible, and that includes, is it technically feasible? One good way to do this is to identify a single possible technical approach and analyze it to show that it's capable of fulfilling the requirements. It can also be used to estimate costs of hardware and software. However, this is not a commitment to use that particular approach. When the system design is carried out, there may be totally different technologies that are better and will be chosen. For example, it might be decided not to use a web-based system. So in the feasibility study, the question is simply to show that there is at least one possible technical approach. Now let's look at the requirements. Remember, the requirements is a statement of need as expressed by a client. The client's requirements are probably not expressed in technical terms at all. The client wants the system to collect certain data, to save it and carry out specified processes, such as displaying it and performing calculations and so forth. The decision of how to store and manipulate the data using specific technology is not a requirement of the client. It comes later as part of the design. Finally, at what stage should the decision be made to use an Apache Web Server 2.0 with Tomcat 4.1? This is part of the system design where the developers take the requirements from the client and design a system that's capable of fulfilling the requirements.
End of Lecture 2, Steps in the Software Development Process. Lecture 3, Examples of Software Development Processes.
This is the second of 2 lectures about software development processes. In the last lecture, I looked at activities that occur in almost every software project. In this lecture, I look at how these activities can be combined into a software development process. I will look at 4 examples: agile methods, iterative refinement, spiral development, and the modified waterfall model. I will also give you some advice about how to choose a process for your CS5150 projects.
We'll begin with a couple of definitions. First of all, an activity. An activity is a general term for any part of a project. It might, for example, be develop the user interface for a certain part of a website, or do the unit testing on a certain element of code. Typically, each step in the software development process can be broken down into several activities. Another way of breaking down projects is to use a sprint. With a sprint, the emphasis is on a set period of time with a fixed size of team, and the aim is to complete a specific part of a project. So each sprint will go through most of or all of the process steps. It will do everything from the requirements to the completion of the code for that part of the project. Typical sprints might have a team of 6 to 8 people working for 2 to 4 weeks. Now let's look at our first example of a software development process, iterative refinement.
The basic concept is to create a prototype system early in the development process. This prototype can be reviewed with clients and tested with users. Hopefully, this interaction will improve the understanding of the requirements and clarify the design. Then, the prototype can be refined in a series of iterations, each of which produces a version of the system closer to what everybody wants. The driving force behind this approach is the realization the requirements are hard to understand until there is an operational system. This is particularly true with user interfaces. There is no substitute for having a prototype interface or a very good mock-up and trying it with users. Mistakes in the requirements are the most expensive to correct. Therefore, it makes sense not to invest too much money in developing the system until there's a good understanding of the requirements. Later in this course, I'm going to use an example of converting a national archive from paper-based to computer-based. Understandings of the requirements were very vague at the beginning of this project, and therefore the recommendation was to use an iterative process. This diagram summarizes how iterative refinement works. Each color is a complete iteration. So in the middle, there is a blue iteration. It begins with a preliminary set of requirements, a prototype design, prototype implementation, and a review of the prototype. Based on that, it's possible to start the orange iteration. This has better requirements, a fuller design, a more complete implementation, and ends again with a review of the prototype system. Go round this loop several times, and eventually the system will be understood well enough to come up with the final version, which is the outside dark red loop. The final set of requirements, the final design, the final implementation, a final review, acceptance test, and eventually the release. This is a medium weight process. Documentation is created during the process. Iterative refinement has some special techniques of its own that enable the client to review the planned system early during development without spending too much money on the various parts. I mentioned user interface mockups. It's not necessary to code up every detail of the user interface in order to test it. The software components are deliberately written to be thrown away. So there's no attempt to polish the details of the components. Some modules may not be implemented at all in the early prototypes. They'll just use dummies. These are the techniques that are called rapid prototyping, and you'll often hear this system called successive refinement. The underlying idea is to get something working as quickly as possible for clients and users to see. But these early versions are not intended to be released. Here's another diagram which looks at iterative refinement as it might be with a large system. Instead of going round the iteration loop as I talked about earlier, it may make sense to treat individual components or parts of the system separately. So there's continual updating of parts of the requirements, continual updating of the design, and continual updating of the implementation with intermediate versions as the project goes along.
This leads to our second example of a software development process, spiral development. With spiral development, you begin with a base system that has the overall structure of the final product, but may not have all the components. Missing components can be replaced by dummy stubs. For all the completed components, you need a comprehensive set of test cases. Then, use a succession of sprints to develop new or improved components, each of which should have a complete set of test cases. When these sprints are completed, the new components are added to the source code library and the test cases are added to the test library. On a daily cycle, rebuild the entire system from the source code and run the complete set of test cases. With spiral development, there is always a fully tested system. It may not have full functionality, but the functionality that is there is complete. Spiral development is used for big systems like operating systems. This is the technique that Microsoft uses for new versions of its operating systems. Here there may be hundreds or thousands of different components under development at the same time. Each of them can be developed independently and then checked in to the central system, and the test case is run so there's always a stable system. This slide shows spiral development. On the right in dark red is the daily cycle. Build the entire system from the source code library, run the entire test suite. On the left, you see the development teams developing new and improved components. When each is complete, it's checked into the source code library and into the test library, ready for the next daily cycle. With these first two examples, iterative refinement and spiral development, the entire system is completed before anything is released. But when software is released online, it's often possible to divide the development into a sequence of sprints that are developed and released in quick succession. This is particularly true of web-based services. One of the pioneers was Amazon. When it was a startup company, it developed a very small system which it released, and then ever since has added small amounts of functionality on a quick release cycle. The advantages of this approach are many. First of all, the payback on the investment begins soon. Next, the requirements are more clearly understood in developing subsequent sprints, and this minimizes waste. Feedback from customers and clients can be incorporated into later phases. And above all, it's easier for a small team to develop a small sprint correctly than to coordinate large projects with many ramifications. This slide shows the original version of Agile development. The project is divided into a series of sprints. Each sprint ends with the release of the code developed during that sprint. So the project is divided into a number of small tasks which we call sprints. And for each sprint, the team works through a full software development cycle which includes planning, requirements analysis, design, coding, testing, acceptance testing, and releases the finished code. Each sprint is completed in a fixed time period. 4 weeks was typical of the early Agile development. And the size of the sprint is based on what a team of 5 to 10 people can achieve during that period. So far, I've described the original version of Agile development, in which each sprint ended with released code. In practice, this is rarely possible. But there's so many other advantages of this approach that many people use variants of Agile development. In fact, if you read the software literature, you will find an enormous number of different techniques, all claiming to be the right and proper way to do Agile development.
Some of these processes have names like heroic programming or Scrum, but they all use many of the basic concepts. From my point of view, the characteristics of an agile type development are follows. First of all, the project is divided into a large number of sprints, and each sprint goes through the entire development cycle, ending up with fully tested code. And the processes are lightweight processes. There's minimal documentation, and the sprints are organized by the teams. If you want a general definition, here is a definition from Wikipedia, which I think is quite good. Agile software development describes a set of principles for software development under which requirements and solutions evolve through the collaborative effort of self-organizing cross-functional teams. Here is a diagram very similar to the previous diagram, but with one important difference. Here we have a series of sprints, and each sprint ends with fully tested code. But it makes no assumption about what happens to that code. There are several things that can happen. First of all, the code can be released. This is the original Agile method. Or it can be combined with code from other sprints for subsequent release. And we've just talked about spiral development, in which the individual sprints are incorporated into a larger code base on a steadily improving cycle. Agile development is great for developing or continually enhancing systems within an established architecture. But there is a challenge. A high-level team is needed to establish that overall architecture and make sure that all the sprints fit together. With Agile development, requirements and design emerge incrementally. And that means that inevitably, some parts of the early sprints will need to be reworked later. And this will require changes to code that has already been fully tested, may even have been released. This is always awkward, and it's wasting expensive people's time and effort. If the volume of rework is large, you should not be using Agile development. It's more efficient not to fully polish each component, but to use iterative refinement to minimize the amount of rework. Lecture 3, end of Part 1. Lecture 3, examples of software development processes, Part 2.
Historically, the earliest software development process to be studied was sequential development, and in particular the waterfall model. The idea of the waterfall model is that each step is completed and documented before starting the next. So the feasibility study is ended before the requirements begin. The requirements are completed before the system design, and so forth. There are problems with this basic model, and it's rarely used in practice. The waterfall model is a heavyweight process. It depends upon full documentation of each process step. This has several advantages. The documentation and the fact that each step is completed before beginning the next gives very good visibility to the process. There's separation of tasks, so they can be scheduled separately, or they can be given to different specialists. It's possible to do quality control at the end of each step, and it's possible to do cost monitoring at the end of each step. But there's a major disadvantage. In practice, as you work through each stage in the process, you will get new understanding of the previous stages. And this often requires the earlier stages to be revised. The pure waterfall model is not flexible enough. And in fact, no pure sequential model works well. For example, A feasibility study cannot create a budget and a schedule without some preliminary study of the requirements and a tentative design. But the actual detailed design and the implementation that follows will reveal gaps in the requirement specification, and they'll have to be revised. During the time that a project is going on, there are often changes in the external world. This may lead to changes of requirements, or new technology may become available which should be made use of during the software development. The plan must allow for some form of iteration. This leads to the modified waterfall model. If you look at this diagram, it's the same as the basic waterfall model, except that after every step, there is an opportunity for feedback to earlier steps. So if the implementation finds something that should have been changed in the requirements, there's a feedback loop that enables the requirements to be changed. The hope in the modified waterfall model is that the changes will not be very great. The idea is to try to get everything right at each step, but to accept the fact that there will be changes and to build that into the schedule and to have everybody comfortable with it. So when is sequential development a good process? It works best when the requirements are well understood and the design is straightforward. That is, when it is actually possible to do the steps one at a time with only limited changes later. I mentioned that historically sequential development had been the first of the major process methodologies. A lot of the early systems were conversion of manual data processing systems such as electricity billing, where the requirements were well understood. The computer system should replicate what had previously done by hand, and few changes were made during the development. Another good example is where there's a new model of a product where the functionality is closely derived from an earlier product. I used the automatic braking system for a car in one of the previous lectures. Finally, in large complex systems, it's often the case that some components are relatively straightforward, their requirements are well known, and they can be developed separately using sequential development, even while other parts of the system need a more flexible approach. Before finishing with sequential development, I want to say a few words about contracts. When an organization places a contract with some software house to develop software, in the past, and unfortunately still at times, organizations thought that the sequential model was a good way to provide contracts for software. They could split the contract into several small contracts, one contract for requirement, one contract for system design and so forth, have a separate contract for each with a separate price, and when each stage was completed, sign off and pay for it. The trouble with this is it ended up with a very fragmented sequential process, which, as we've discussed, is very bad practice. One of the reasons that government software contracts often get into difficulties is because government departments still use this contracting method much too much.
We've now introduced the four major types of software development process. In practice, many large projects use processes that combine aspects of these four types of process. For example, with spiral development, I suggested that new components can be developed using sprints, but large components may be developed using other methods such as iterative refinement or sequential development. User interfaces have to be tested with users. This means that any project that includes a user interface must have some iterative development. So even within an agile or sequential process, part of the development will be iterative refinement of the user interface.
A very common form of mixed process is phased development. And this can combine sequential and iterative elements. For phase 1, a simple system with basic functionality is brought quickly into production. This system may be developed using a sequential or iterative refinement. Then for phase 2, phase 3 and so forth, new expanded systems are developed based on experience gained from the users of the previous phases. These phases typically will involve making changes to the phase 1, so this is an iterative approach. The advantage, payback on the investment begins sooner, and the requirements are more clearly understood when developing subsequent phases. Phased development is a bit like incremental development, but the phases are bigger and the scope is determined by the functionality that's going to be released, not by the constraints of time and staffing. Here's an example from my own experience. We were adding graphics to an existing programming environment. We had general ideas of what we wanted to do, but the details of the semantics and the syntax of the graphics needed to be explored. So we made a series of prototype versions by extending the current environment with a preprocessor and a runtime support package. Each version was tested with users until the users were pleased with the function. We then had a good understanding of the requirements, a design that we were confident in, but code that had been created incrementally and was very rough. Therefore, we threw the code away, and for phase 2, we created a much higher quality implementation using a modified waterfall approach, starting with the previous prototype, which was in operation, but we used the previous prototype as our requirements for phase 2. As I've said several times, there is no single software development process that works for all projects. But large software organizations often have their own internal processes that work well for the type of software that they develop. For example, Amazon.com, which is a leader in internet commerce, makes extensive use of sprints. Most software development is divided in increments of about 4 weeks elapsed time. The leadership of Amazon is particularly strong technically, and they have a very strong overall architectural group that specifies what is to be done in each sprint. As a contrast, Lockheed Martin, which is primarily a contractor writing software for the government, follows a sequential process that matches the way that the US government manages software contracts. SAP, the business software company, emphasizes the functionality that's seen by their business companies, their business customers. This changes only slowly over time, and they have a great deal of experience, and therefore they can do a lot of sequential development. I actually don't know how they do it, but the sort of projects they do, I'm sure they specify requirements very carefully before actually implementing them. Microsoft, which is the biggest software company in the world, focusing on PC software, places a great deal of emphasis on making sure that new software is compatible with the equipment and the old software that's out there. They do a great deal of testing, and they make extensive use of a spiral process, which for their big projects can last for several years. So, you've got a software project. How do you choose a process? I think one of the starting points is to look at the expenses and the risks of changes. If you don't understand the requirements well, or you expect them to change, you must have a process that keeps flexibility. So iterative refinement, sprints, phased implementation are all ways to avoid enormous expense before you fully understand the requirements and the design. If, on the other hand, you have a big software system with many interrelated components, you really don't want to change the system architecture during development. If at all possible, a sequential process such as a modified waterfall model, where at least the system architecture is really well understood and does not change, can be a very good way to go. If you're building software that's going to be sold, and if the market is not very well understood, use a process that gets operational software in front of the customers as quickly as possible. And this is where the incremental development and sprints are particularly valuable. Some final observations about software processes. A completed project will always include all the basic process steps, but the development process is always partly evolutionary. All the time what you're trying to do is to lower the risk, but to end up with a really nicely architectured and well implemented software product. So some of the ways you can lower risk: prototyping key components, frequent releases, or dividing the project into phases, early and repeated testing with users and customers, a visible software process so that the people who are funding the project, the clients and the senior management know what's going on. And finally, making use of reusable components so that if a component doesn't work out as intended, different components can be used. Although it's pleasant to think you can complete each task as you go along, it's never possible to complete everything completely without provision for revision. This is sometimes called throwing it over the wall, and it just does not work. Here are some suggestions about how you might select a development process for your CS5150 project. Probably most projects use some form of iterative refinement. If you do, I suggest that you aim to have an operational prototype by the first presentation. This will be very, very basic. It will have lots of dummy stubs. There'll be a lot of things that don't work, but it'll be something that you can discuss with your client, and you can use the feedback to test with users and to come up with a better iteration for the second presentation. From the second presentation, you should have a pretty good idea of what the final requirements are and should be able to complete a nicely polished version for the third presentation and release at the end of the semester.
I'm sure that many of you would like to try agile development for your projects. There is not much time, but it's just possible to squeeze 3 sprints into the semester. If you do, remember that the aim is that each sprint should end with fully tested code. So for sprint 1, take one section of the project and do it completely. Sprint 2, another section. Sprint 3, a final section, and combine them into the final product. If you cannot complete the various sections, you'll do better off using iterative refinement.
Finally, there will be some projects which can use a sequential development, the modified waterfall model. If you have a project where the requirements are fairly well understood and where the design is likely not to be changed very much, this is the way to go. I would suggest that by the first presentation, which is halfway through the semester, you should have the requirements finished and be well underway with the design. By the second presentation, you should have the design completed and be well underway with the implementation. And if you do these well, you should be able to have the implementation completed and acceptance testing done by the end of the semester.
End of Lecture 3. Lecture 4, Feasibility Studies.
The first stage in any software project is to decide whether or not to do the project. That is the purpose of a feasibility study. When you understand the resources and effort that goes into a big software project, you can understand how important it is to study carefully what you're doing before you commit yourself to doing it. Without a good feasibility study, you cannot draw up a proper budget, a proper timetable, or decide what resources you have to allocate to the project.
Feasibility study is made before committing to a project, and it leads to a decision. The decision may be to go ahead with a project, to not go ahead with a project, or to think again and study further. The feasibility study should include estimates of budgets, and in production projects, the feasibility study can often be in the form of a budget request. In my own experience, doing research projects, the feasibility study has often been in the form of a proposal to a funding agency such as the National Science Foundation. Feasibility studies are difficult. One reason is uncertainty. Clients often are unsure of exactly what they want the project to achieve. The benefits are often hard to quantify, and with complex projects, the technical approach is usually ill-defined. It's very difficult to make estimates of resources and timetable with this uncertainty. Finally, and this may be the biggest challenge of all, many projects require organizational changes, and these are very difficult to predict during a feasibility study. For all these reasons, feasibility studies rely heavily on the judgment of the people doing them, and that's a very good reason for having your best people involved in the feasibility study and making sure that they have time and resources to do a good job. There's another reason why feasibility studies are difficult, and that's to do with advocacy. Advocacy is needed to build enthusiasm for a project. To convince an organization to undertake an expensive, complex project with many risks needs enthusiasm. And enthusiasm is good, but enthusiasts often emphasize potential benefits and downplay risks. Moreover, the people carrying out the feasibility study and making the decision often have a vested interest in the project going ahead. For example, they may be hoping to get a contract to actually implement the project. They may feel that this project is good for their own career, and so forth. In doing your CS5150 feasibility study, it's quite possible that you may end up recommending not going ahead with the project, or you may decide that the project is too ambitious or the concept needs change. This is good, and if you do find that you cannot recommend the project, we appreciate that and you should do so. A feasibility study makes recommendations. Senior members of the client's organization decide whether to begin a major software project. What information do these decision makers need? First, there is the obvious question, who is the client? Who is this project for? Often a bigger question is the scope. What are the boundaries of the project? What's going to be included? What is not going to be included in the project? Benefits? Why is this being done? What are the benefits? Can they be quantified? If the software is a product to be sold, what are the forecasts of likely sales? Technical. The feasibility study does not do the technical design, but there must be at least one technical way to carry out the project. Resources, what's it going to cost? What are the estimates of staff, time, equipment, and so forth? And finally, what are the alternatives? What are the options if the project is not done? Behind all of this are risks. There are risks everywhere. Can they be minimized? Technical risks in some ways are the most obvious. There needs to be an outline plan with a rough timetable and staff allocation. This, of course, makes assumptions about technology, scope, and so forth, but it's a starting point. The plan must have very large margin for contingencies. Typically, projects require twice the staff and or time that are envisaged in the feasibility plan, and this must be allowed for. Then there are a set of external factors. Every system interacts with other systems. Are the others committed to the necessary efforts? For example, do the potential users want this system or will they use it? Are there customers who will buy it? There are often external pressures and obstacles that dictate how a project is going to be carried out, and they must be considered during the feasibility study. Any major computer system makes demand on an organization. The feasibility study needs to ask questions about the organization. Does the organization have the management expertise to do the project, to fit the project into its other workings? Where is the technical expertise? Does the organization have the technical expertise? It's very easy to say that the work will be carried out by a contractor, but the organization still needs expertise to oversee the work. Finally, there's an organizational commitment. Are there going to be changes in personnel, workflow, and so forth? If so, is the organization committed? At one stage in my career, a group of us worked on a system for the United States Copyright Office to allow electronic deposit of documents. This project made very good progress technically and then got stalled. It was only afterwards we realized that the changes in clerical workflow were perhaps the most difficult part of the entire project, and the organization at that time was not committed to making those changes. I now want to look at two examples of what goes wrong when a feasibility study is not done properly. The first one concerns a United States government agency which manages huge numbers of documents and other records and wished to move from a paper-based approach to a system that could manage digital documents. The first very sensible step was to ask a computing center at another university to develop a prototype system which demonstrated some of the core technology. The next step was that Congress voted funds to procure a major computer system. They then commissioned an external feasibility study to report on the technical approach to be followed and to comment on the results of the university prototype. Now, you should recognize there's some problems with this chronology. The first thing is the decision to go ahead was made and the budget was approved before the feasibility study was begun. How do we know that Congress provided the right amount of money over the right timetable? The other thing is the feasibility study looked only at the technical aspects. I was not a member of that feasibility study, but I was one of the external readers, so I know the contents of what was discussed. They identified several problems. The first and most fundamental was organizational. The agency senior management did not have the experience to lead a very large computing project. And no thought was given to the workflow and job changes that would affect almost everybody in the organization. The next, and this is quite a common problem, is they did not study the materials that would be involved. They made no estimates of the volumes, of the kind of data, nor the complex policies for access. Many of these documents had real issues of privacy, some of them were classified information and so forth. In summary, the requirements were complex and only partially understood. It was inevitable that major changes were going to take place even after the system went into production with real users. But there was a dilemma. The feasibility study was paid for by the agency and restricted to technical considerations. I've told you they're organizational questions, but they weren't even asked to comment on them. They actually recommended a phased approach using iterative refinement over many years. And this would probably have worked, but only after the organizational problems had been addressed. However, the agency had money from Congress, and this was money that either they had to spend or they would lose it, and they did not want to return the money. Therefore, they adopted a pure waterfall model. They put out a request for a proposal for the requirements and placed a major contract with a software house. So this is clearly the wrong process at the wrong stage of a complex system. This is how disasters are made, and this system has got into all sorts of problems during the implementation. I mentioned that scope is one of the most difficult parts of a feasibility study. The scope describes the boundary of the system. It will list what are the functions that this system will do, and also, perhaps even more important, what are the functions this system will not do. It will probably have a list of dependencies on external systems, and it will have a list of current systems that need to be replaced or altered. Confusion over scope is a common reason for clients to be dissatisfied with the system. You will know that you have not done your scope properly if, at your presentations of your CS5150 projects, you get comments like, "Is that all you plan to do?" Or, "I assumed you were going to do XYZ." Or, "I can't use the system without something." My second example is about confusion over scope. A government organization required a repository system to store and make accessible very large amounts of highly varied materials over long periods of time. An outside organization that I'll call C built a repository system and store and manipulate complex digital material. I should mention that I was a member of this organization C at the time and was in fact responsible for part of this project. The problem we fell into was that nobody built the subsystems that were needed to go with the repository. We needed systems to organize, validate, and to load material into the repository, and also systems to provide access to it. The government organization L expected that the repository system would include these subsystems. We at C considered the subsystems separate from the repository system and expected that L would provide them. If we'd done a more thorough feasibility study, we would have seen this confusion in advance. The benefits section of a feasibility study asks the question, what is gained by this project? Ideally, you'd like to quantify the benefits, but often there are benefits that are difficult to measure precisely. Remember, we're talking about benefits to the organization that is paying for the project. Here's some examples. The aim may be to create a marketable product. If so, the feasibility study needs to include estimates of sales and factors such as how important is time to market. Many organizations carry out projects because they want to become more efficient. For example, they may want to save staff. There are an important group of organizations that are too complex to control manually. Think of a production line in a factory, for example. New or improved service is always important. For example, faster response to customers. And you'll often have projects that are carried out in order to improve safety or security or some aspect of the organization's work that is difficult to do manually. In all of these benefits, remember that professional benefits are not a reason for doing a project. You do not say, we want to do this project because it'd be fun to do, or it's advanced technology, or it's neat technically. You've got to express benefits in terms of the organization that is paying for it. Feasibility studies need to demonstrate that the proposed systems are technically feasible. The technical approach that is actually followed may be very different from the one that's discussed in the feasibility study, but there should be in the study enough to prove that the system is feasible. So it's going to have an outline of the requirements, a possible system design, for example, using a database system or distributed architecture, possible choices of the software to be acquired or developed, and estimates of the numbers of users, data, transactions, and so forth. These rough numbers are part of the provisional plan that's used to estimate the staffing, timetable, equipment needs. And in fact, every feasibility study has to have a plan. It's an outline plan, and inevitably, when the project gets underway, things will be changed. But to make a decision, the decision makers need estimates of the staffing and equipment needs and a preliminary timetable. They need major milestones and decision points, and they need the interactions with and dependencies upon external systems. For this reason, the feasibility study typically provides a preliminary list of deliverables and delivery dates. There's a separate lecture about project management.
Lecture 4, Feasibility Studies, end of Part 1. Lecture 4, Feasibility Studies, Part 2.
Software development is full of risks. A feasibility study should be honest in identifying risks and proposing alternatives other than the approach recommended in the study. With risk analysis, the first question is, what can go wrong? This is the normal questions of functionality, cost, and time. In order to manage these risks, how will the progress be monitored and problems identified? This is our standard question about visibility. Finally, what are the fallback options? If things go wrong, what can be changed, or what is inflexible? For the alternatives, first of all, what if the decision is made not to do this project? What are the alternatives? Is it possible to continue with the current system, to enhance it in small ways, or to create a new system but using a different approach from this study? If the decision is made to go ahead, should it be developed by in-house software development team or contracted out? If there is a contract, how will it be managed? Finally, are there alternative phases of delivery? And are there possible points for revising the plan or even terminating the project? There are not many formal techniques for feasibility studies, but behind all the approaches, there is the theme of making sure that the client and the development team have the same understanding of the goals of the system and the associated risks and benefits. Typically, the development team will not know a great deal about the client's organization when they start. Therefore, they need to have interviews with the client and the staff of the client's organization. They also need to review existing systems, including competitor systems, to see what they do well, what they don't do well, and to generally understand from the organization's point of view what this system is required to do. For the client to understand the recommendations for the proposed system, it's very useful to have some demonstrations of key features or alternative similar systems that they can look at. Mock-ups of user interfaces can be very useful at this stage. It is often quite useful to walk through typical transactions or interactions so the client gets an understanding of what is being proposed. The feasibility study must include a budget and it must include some sort of timetable, but these are going to be very rough. For example, an outline budget is likely to just talk about a certain number of people for a certain number of months at so much per month without going into details about who these people are or exactly how they're going to be allocated. If there is needs for extra equipment, buildings and so forth, these should be put in the feasibility study, but they can be quite rough. On this slide, I suggest that a contingency of at least 50% is needed on all software projects. In practice, this is low, and maybe it's reasonable to talk in terms of a contingency of 100%. That is, to tell the client that most projects take twice as long to do or cost twice as much. The planning does not have to be in great detail, but it should definitely talk about phases and milestones. What are the deliverables? What are the approximate dates? When are the planned releases? When will the client see the outcomes of the system? And when can they decide if they're going to make major changes? At the end of the feasibility study, there's the decision. Different organizations and different senior managers have different ways of making decisions. Some, for example, like to be part of the feasibility study. They're monitoring the team, they have frequent progress reports, and by the time that the study is completed, they know what the recommendations are and how comfortable they are going to be making a decision to go ahead. Others leave the team to do their work, but expect a written report at the end which will contain the information that's needed to make a decision. My own personal style is that I really like to talk to the people who have done the work. So at the end of a feasibility study, I might spend half a day or longer face-to-face questioning of the knowledgeable people. Why do you recommend this? What information do you gather, and so forth? Whatever the approach made to the decision, the key thing is that the decision maker must really understand the decision they're making. It mustn't be a superficial decision, because they're going to take responsibility for the success or failure of the project. I've mentioned feasibility reports. In general, the modern style of software development is to reduce the number of written reports. But I think feasibility studies are one case where there has to be a written report. And it should be a well-written, well-presented document. It's going to be for a general audience. It's not a technical document. It's going to be for the client, for the financial management, for the decision makers. And that includes the technical management, but above all, it's for the client and the client's organization. The length is difficult. It's got to be short enough that everybody reads it, but it's got to be long enough that no important topics are skipped. One way to achieve this is to include details in supporting documents so that anybody who wishes to dig into the details can do so, but that it's possible to read the basic report without looking at all the details. Remember always with a report that it's got to be read and understood. If the report is not understood, then it's useless. The first CS5150 assignment is a feasibility report. There are two good examples of reports from previous years on the website. They're placed there with the permission of the students. For this course, there are some specific requirements for the feasibility report. There needs to be an outline plan showing principal activities and milestones, and this should have sufficient detail that somebody reading the report can be confident that you understand what's got to be done in order to complete the project on time. There's got to be discussion of the business considerations, who owns the software at the end of the project. And finally, there's got to be risk analysis. What can go wrong and what is your fallback plan? In particular, many, perhaps most CS5150 projects are overambitious. You can't complete everything in the time available, so what are the alternatives? Here are some challenges you should look at and think about as you do your study. First of all, the team. Every team has people with different skills. Be realistic about the skills that people have and how many hours per week they're going to put into the course. They're not working full-time. People are taking many other courses. Time is always a challenge on these projects. The project must be completed by the end of the semester, and that means an operational system with documentation and presentations and handover. These are all time-consuming. Do you need special equipment and software? If so, who's going to pay for it, and how long will it take to get. Client availability often is a challenge. You're going to need to have lots of meetings with your client. Is the client sufficiently available and able to help you? Startup time. Never underestimate how long it takes to create a team, to schedule meetings, to acquire software, to learn new systems and so forth. I mentioned business consideration, licenses, trade secrets and so forth. And then ambition. You certainly don't want to have nothing to show at the end of the semester. What are your alternatives? Here's some ideas about how you can minimize risk in your projects. Because time is so short, specify several target levels of functionality. First of all, there's the required level. What is essential to get done for the project to be a success? Then there are the desirable extras, and then there's the optional material that will be added if things go well. Feasibility. Are there intermediate deliverables that you can produce so that the team and the client know how things are going? Communication within the team, with the client and with the teaching assistants is critical. How are you going to do this? All this requires well-defined development process. Good processes do lead to good software, and good processes do reduce risk. A few words about the report. Typically, several members of the team will write different sections of the report. This is fine, even if they have different styles. But do get a single person to read and edit the entire report. In particular, this person should look for consistency. Do the sections about the scope and requirements agree? And does the plan match the scope? Style. Is the text comprehensible? Some of your clients are technically knowledgeable, others are not. Use terminology that's appropriate to the client, and in particular, do not use jargon that's not clear to the client. Several members of this course come from overseas, and several people do not have English as their first language. In general, this is not a problem, but for this particular report, if you do have a native English speaker on your team, ask them to do the final editing. Remember that the purpose of a feasibility study is to establish if a project is feasible at reasonable cost within the planned period. The report should end with recommendations about whether to proceed, but the final decision is made jointly by the client with help from the development team. In previous years, here are some of the problems I've seen with feasibility studies. One problem is the report is often vague about the scope. If you don't have a clear definition of scope, it's not clear that the project is feasible. Another problem is lack of detail in the plan. The plan should have enough detail to describe the activities convincingly. Otherwise, it's impossible to estimate the effort. Finally, almost every project is too ambitious. The report needs to describe how you will monitor the progress and how you will adjust the scope if necessary.
Lecture 4, Feasibility Studies, end of lecture. Lecture 5, Project Management.
This lecture is about project management. How to break a complex project into tasks and activities. How to estimate the total time to complete the project. And how to track progress against the plan. Heavyweight software processes, such as the modified waterfall model, differ from lightweight processes, such as Agile, in how they manage projects. But the underlying goals are the same. Make sure that the resources are used effectively and provide visibility for everybody involved with the project.
We begin with a historic example. one of the seminal books on software engineering was written by Fred Brooks Jr. more than 40 years ago. He was in charge of one of the first really big software development projects, the operating system for the IBM 360, which was delivered more than 2 years late. And the book discusses what he learned while working on this project. Early in the book, he asks the question, how does a project get 2 years behind schedule? And he gives the very simple but profound answer, 1 day at a time. The aim of project management is to manage those 1 day at a time. So the aim is to complete a project on time, on budget, with the required functionality, to the satisfaction of the client, without exhausting the team, and to provide visibility about the progress of a project. I would add a second purpose of the visibility is that if the project runs into difficulties, to be able to see those difficulties early so that corrections can be made. Here are some of the challenges of project management. Clients want precise information. They want to know, will the system do what was promised? When will it be delivered? If late, how late? How do the costs compare with the budget? Often, the client sees the software as part of a larger activity. If the system is a product, marketing and development must be combined. For example, Microsoft Office consists of several large separate development projects which are sold as a single unit. Sometimes the system has to work with other systems and developments must be coordinated. For example, the various systems that are combined in a modern automobile. But while the client would like precise information, every software system is different, and most systems are not well specified, or the requirements change during development. Estimating time and effort is full of errors, even when the system is well understood. We're not going to get precise information, but we need good information to manage the projects. Here are some of the aspects of project management. First of all, planning. At the beginning, there needs to be an outline schedule as part of the feasibility study, and this is required for your CS5150 projects. Then for each part of the project, there needs to be a fuller schedule. This can be for each process step, for each iteration, for each sprint. There needs to be contingency planning, continual anticipation of possible problems. Progress tracking against the plan, regular comparison of progress against the plan, if necessary, modification of the plan, if necessary, changes of scope and so forth, made jointly by the client and developers. Finally, at the end of a project, there should be an analysis to see how the project actually worked out so that improvements can be made during the next project. Here is some terminology that's used in the management of software projects. A deliverable. A deliverable is some work product that's provided to the client. It can be a mock-up, a demonstration, a prototype, a report, a presentation, documentation, code, or anything that's actually delivered to the client. The most important deliverables of all are the release of a system or a subsystem to customers and to users. A milestone is related to deliverable. It's the completion of a specified set of activities. For example, the delivery of some deliverable, or the completion of a process step. I've used the term activity before. It's a general term for a part of a project that takes place over time. It's sometimes known as a task. So, coding a section of a program, completing a report, delivering a presentation. All these are activities. An event is when a group of activities are completed. For example, if several parties have to agree on a budget and a plan, when they all agree, that's the event that the plan has been agreed. Very often, an activity cannot begin until some event is reached, and this is called a dependency. Resource is a general term for anything that's needed to make the project work. This can be staff time, equipment, or any other limited resource required by an activity. Until recently, all methods of project management followed the same standard approach. With this approach, the scope of the project is defined early in the process. The development is divided into tasks and milestones. Estimates are made of the time and resources needed for each task, and these estimates are combined to create a schedule and a plan. Progress is continually reviewed against the plan, perhaps weekly. And the plan is continually modified by changes to scope, time estimates, resources, and so forth. Typically, the plan is managed by a separate project management team and not by the software developers. I hope you can see that this approach fits very well with the modified waterfall model and fits quite well with iterative development, though with iterative development, the changes that are going to take place during the development could be quite substantial. The agile approach to project management is rather different. It's based on the assumption that a great deal is going to change during the development, and therefore you cannot make a full plan right at the beginning. So you divide the planning into high-level release forecasting and low-level detailed planning. The release planning is a best guess. It's a high-level view of what can be achieved in a sequence of time boxes. And the assumption is that these plans are going to be continually modified, perhaps as often as daily. The clients and developers work together and have joint control of the release plans and the choice of what is carried out in each sprint. For the detailed planning, for each time box, the team provides the plan of what it can achieve. Since the sprints which take place in an individual time box are quite short, the team can use simple tools such as Gantt charts or other conventional planning tools, and there doesn't need to be a separate project management team. Project planning requires estimates of the time for each activity, and this is not easy. Experienced staff are quite good at estimating the actual time to carry out a single task, but they tend to underestimate the little bits and pieces. For example, with programming, an experienced programmer can usually estimate how long it will take to write the code for a specific part of a program. But from almost done to completely done takes longer than they expect. There's always something to be tidied up. They may want to put the comments into better shape, or there may be a patch that they feel they ought to rewrite before the program is complete. Then there are distractions. For example, they may have trouble with their computer or decide to upgrade the software. They may have family commitments, such as a child's school is closed because of snow. Or they may have administration, such as spending a day interviewing job candidates. Finally, some things just have to be done twice. The administrative computing department at Dartmouth, which I was responsible for at one stage, used activity graphs for the program design and implementation of major projects. That is, they developed a plan after the project was well understood. At the end of the project, they would analyze how long things took compared with the plan. And their experience was that the elapsed time to complete projects was consistently 30 to 40% longer than predicted by the model. The analysis showed some common themes. Some tasks were not anticipated. There was incomplete understanding of the project at the time that the plan was produced. Some tasks had to be redone. There might be changes of requirements, there might be technical changes, and so forth. Key personnel were not able to work 100% of their time on any project. They might be called off to help with other areas, and this produced schedule conflicts. Finally, there are always non-billable hours. There were hours which the people spent doing administrative tasks, anything from vacations, sickness, to interviewing job candidates. Agile methods use team-based estimating. The idea here is that for each time box or sprint, the team has the best understanding of what it can achieve, and the team makes a commitment to the outcome of a sprint. The team needs an internal schedule to allocate tasks within the sprint. And since different teams work at different speeds, it's common to estimate effort in terms of a numeric scale, not as time. For your CS5150 projects, you can think of them as being a single sprint and use team-based estimating for your project management. The startup time at the beginning of a project is consistently underestimated. On a big project, the startup time is typically several months, maybe as much as 6 months. Here are some of the reasons. The personnel may not be available. They may have to complete previous projects, they may be tired, or they may have to be recruited for the project. Specialized hardware and software may have to be acquired and installed. The staff may have to learn new domain areas and software, and people are slow while they're learning new areas. Finally, the clients may not be ready to start at the day that the development team is ready. Underestimating startup time is a particular problem with new companies. A new company will raise funds and wish to get started, but it may find it takes several months to hire the staff, to find buildings, and to get to a stage in which they have a productive development team. I mentioned that there are several methods for doing project planning, and project planning makes use of tools. I'm going to look at two methods, the critical path method and the Gantt methods, but there are other methods such as activity bar charts. They all have the same general form. You build a work plan from activity data and you display the work plan in graphical or tabular form. Then you use project planning software, for example Microsoft Project, to manage the plan. And that means to maintain a database of the activities and related data, to calculate and display schedules, and to manage the progress reporting.
Lecture 5, Project Management. End of Part 1. Lecture 5, Project Management. Part 2.
The first method we're going to look at is a Gantt chart. Here is a very simple Gantt chart. Time runs from left to right, and you can see the dates across the top of the chart. Each row represents a task, and the green bar shows the date at which it's expected the task will begin and the planned date in which the task will come to an end. Gantt charts are very good for small projects, such as single time boxes, sprints, and small parts of a large project. They all have the same shape. Dates run along the top, and they can be days or weeks or months. Each row represents an activity. Activities can be sequential, parallel, or overlapping. The schedule for an activity is a horizontal bar, and the left end marks the planned beginning of the task. The chart is updated by filling in each activity to a length proportional to the work accomplished. I might mention in passing, this is probably the most difficult part of using Gantt charts, as it's often very difficult to estimate what proportion of a task has actually been done. You can compare the progress to date against the plan by drawing a vertical line through the chart at the current date. Most CS5150 projects use Gantt charts. The projects are fairly small and it's possible for a single Gantt chart to cover the entire project. Here is a more complex Gantt chart. It has been drawn using Microsoft Project. This chart shows some extra information. The red bars are the so-called critical path, and the black lines show the slack in non-critical activities. We will talk about the critical path and slack later in this lecture. Larger projects often use activity graphs. Activity graphs are actually a group of scheduling techniques that emphasize dependencies. They're very widely used in the construction industry, in all forms of engineering, as well as in software development. Here's the notation that I use. An arrow with a solid line represents an activity or a task. An arrow with a dotted line is a dummy activity. That's a dependency that's not actually tied to a real activity. An event is shown as a circle, and a milestone is shown as a square. The first time I used activity graphs for a large project was actually for a distance learning course at the British Open University, very much like the materials for this course, only on a much larger scale. Here is a tiny part of what was a very large activity graph. You can see three types of activity. In the middle, in black, there are the tasks for developing the central course materials. At the top in red, there is the development of the projects to be done by the students. And in the bottom, in blue, there are the tests, the examinations that are going to be taken by the students. So you can see that after the start, you can begin work on planning for the first unit. Then you can provide a draft of that unit. You can create the slides for that unit. And once you've got the slides for that unit, there's several things you can do. One is you can start work on the audio. But the other is there's a dependency that goes back to the second unit. And you can start work on the slides for that unit, but only after you've reached the event at the end of the slides for the first unit. Activity graphs have a long history. The first formal use of them was by the US Navy in the 1950s to support the development of the Polaris submarine missile program. And they developed a system called Program Evaluation and Review Technique, or PERT. The basic technique, PERT time, assumed that you could not estimate activities accurately, and so they provided three estimates: a shortest, a most probable, and a longest. But it turned out that this was so difficult that in practice everybody used just a single estimate. And using a single estimate comes up with the technique which is widely used today called the critical path method. There's a related version of PERT called PERT cost, which is an activity graph where you put resources as well as time onto the graphs. So I'm going to talk about the critical path method. It uses an activity graph with a single time estimate for each activity. As I say, it's a standard method for managing large construction projects, and on big projects, activity graphs with more than 10,000 activities are common. In the following slides, I'm going to work through the calculations in using the critical path method for the example that I've just shown you of a distance learning course. Once the activity graph has been drawn, the next step is to put time estimates on each of the activities. So here, each of the activities on the last graph have a time estimate measured in weeks. Now the calculations follow automatically. The first calculation is to calculate what's the earliest date that is possible to start each activity. And in calculating that, we'll calculate the earliest event date, the date that all activities ending at a specific node on the graph will be completed, assuming that each activity begins at its earliest start date. Finally, the earliest project completion date, which is the date on which the project is completed, assuming that every activity begins on its earliest start date. Remember, these calculations all depend on having the correct graph. They depend on the dependencies represented by the activity graph and the accuracy of the estimates of the time to carry out the individual tasks. Here's how we calculate the earliest event dates and the earliest start date for each activity. To begin with, we start at time 0. We look at the activity in the top left of this figure. It starts at time 0, takes 1 week, so we can end it at time 1. Similarly, the event below we can reach at time 12, the event below that we can reach at time 12, and the event below that we can reach at time 4. If we go now back to the top of the graph, we see an activity that could start at time 1 and take 4 weeks. So we think we could reach that next event at time 5. But there's another activity coming into that event, and we cannot start that before time 12. It's going to take 3 weeks. So the earliest we can reach that event is week 15. If we go down to the event below, we can see that there's an activity which could start at week 12 and take 3 weeks. So we think we can reach that event at week 15. But notice there's a dependency that comes in from the top right above that event, and we need to know when that dependency can be met. The beginning event of that dependency cannot be reached before time 17, because there's an activity that ends there that cannot start before week 15 and will take 2 weeks. Therefore, following down the dependency to the event diagonally below it, we see that we cannot actually reach that event before week 17. Continuing with this sort of calculation, we can calculate the earliest start date for all the activities and the earliest event date for all the events. Finally, we see that the earliest date on which we can complete this project is week 25. We now calculate the latest start date for each activity. This is the latest date that's possible to start each activity and still complete the project on time. That is by the earliest project completion date. To calculate this, we need the latest event date for each event. That's the latest date that all the activities ending at that node must be completed in order to complete the overall project by the earliest project completion date. Here's how the calculation works. The project completion date is week 25. There are 3 activities that have to be completed before this event is reached. Let's look at the one in the middle. It takes 1 week, and therefore it must be started no later than week 24. The latest event date for that event is week 24. To reach that event at week 24, there are 2 activities, both of which have to be completed. For example, the one coming up from below takes 2 weeks, and therefore it must be started no later than week 22. So the latest event date for the node on the bottom right-hand corner of the graph cannot be later than week 22. However, there is another activity that goes from that node to the end of the project, and that takes 8 weeks. If that is going to be completed by week 25, the event at the beginning has a latest event date of 17. We can now follow the other activities and the other events and work backwards through the graph, calculating the latest start date for each activity and the latest event date for each event. And naturally, the latest event date for the start of the project is week 0, so that the project has an overall time of 25 weeks. This slide shows the earliest event dates and the latest event dates that we've already calculated. The earliest event dates are in red and the latest event dates are in blue. You'll notice that some events have the same earliest and latest dates. They're said to be on the critical path, and activities between such events are said to be the critical path. Every activity on the critical path must begin on the earliest start date. If it's not begun at the earliest start date, then the project will not be completed on time. Some activities are not on the critical path. They're said to have slack. Here, for example, is one activity from the graph. If you notice with this activity, the earliest start date for this activity is week 17. But the event at the end of the activity has a latest event date of week 23. Since the activity has a duration of 3 weeks, it can be started at any time between week 17 and week 20, and this gives a slack of 3 weeks. To calculate the slack, which is the difference between the latest start date and the earliest start date of an activity, you make the following calculation. It's the latest event date of the end of the activity minus the earliest event date at the beginning minus the time estimate. The critical path is a path through the graph where every activity has 0 slack. If an activity on the critical path is not started on its earliest start date or takes longer than the predicted time to complete, then the project completion date is delayed. I mentioned that this graph was part of an activity graph for a distance learning course. When we first did the calculation, we found a problem. The problem was that purchasing a key item of equipment was on the critical path, and by delaying when we purchased that equipment, the whole project was running late. But the earlier that a project is known, the easier it is to fix, and we were able to make small changes to the schedule to buy that key item of equipment earlier, and therefore come up with a plan in which the project could be completed on time. Activity graphs and Gantt charts can also be used to plan resources. Here's the basic method. Each activity is labeled with resources that are needed to carry it out. For example, it might be the number of people, such as 2 Java programmers, or a key person, like the chief system architect, or it might be equipment, or facilities, like a video conference center or a new building. There is a separate database of all the resources with their availabilities. So this includes such things as hiring and training, planned vacations, equipment availability, and so forth. The normal calculations are done. So with an activity graph, one calculates the earliest start dates and so forth. Assume that every activity begins at its earliest start date. Then in each time period, you can calculate all the activities that are going on during that time period and see what resources are required and what resources are available. This way, you can identify shortage of resources, or you can find surpluses. And then you can adjust the schedule. For example, you might acquire extra staff by hiring short-term consultants. Or you might rearrange the schedule by asking people to take their vacations at different times. Or you might change the order of carrying out the activities. Either way, you've got a planning tool that enables you to make sure that the appropriate resources are available at the time that they're needed. The book by Fred Brooks Jr. that I mentioned at the beginning of this lecture is called The Mythical Man Month. He looks at a common mistake that people make in planning to believe that you can speed up a project just by adding more people. So, for example, if you have a task that can be done by 2 people in 6 months, it's easy to believe that if you put 12 people on the project, you could do it in 1 month. But as Fred Brooks points out, this is wrong. And here's some of the reasons. First of all, in computing, not all people are equal. Some people are much more productive than others. Some tasks are just too difficult for everybody. So people are different, and you've got to allow for this in planning. Adding more people adds communications complexity. People are going to spend more time keeping each other informed of what's going on. And there's some activities that need a single mind. And sometimes the elapsed time for an activity just cannot be shortened. In fact, Fred Brooks makes a compelling case that when a project is running late, adding more people may actually increase the time to complete a project. In looking at your CS5150 projects, you might look at the role of key people. What happens to the project if a key person is sick or quits on the course? This does happen, and it's something you should bear in mind. To complete this lecture on project management, I want to look briefly at the role of the project manager. The project manager's central job is to create and maintain the schedule and to track progress against it. To minimize risk, the project manager needs to know where there's flexibility and to keep some slack in the schedule, and will almost certainly need to make continual small adjustments, such as starting some activities before previously planned, subcontracting out specific tasks, or renegotiating deliverables with the client. For visibility, the project manager should be keeping the senior management informed of how things are going. To do this, the project manager needs really good communication skills. In particular, needs the confidence and support of the head of the development team and the confidence of the team members who will be frank and honest with how the actual progress is going.
Lecture 5, Project Management. End of lecture. Lecture 6, Requirements Analysis. This is the first of 3 lectures about the requirements process step. Remember, the requirements define what the system does from the client's point of view. If you rush through this step and do not have a good understanding of what the client expects from the system, then you cannot build a system that satisfies your client.
The overall objective is to define the function of the system from the client's viewpoint. To define the system's functionality, constraints, and goals, the development team need consultation with the client and often with potential customers and users. The requirements can be developed in a self-contained study, but increasingly often they will emerge incrementally during the course of the project. At the end of the project, the requirements are the basis for acceptance testing. This is a part of a software project which calls for particularly close working between the development team and the client. And in particular, the method by which the requirements are developed must be understood and accepted by everybody involved. Here is some data from an old study by the Standish Group about why software projects fail. It highlights the importance of getting the requirements right. Here is a list of the 8 principal problems that they found. In this list, things to do with requirements are highlighted in red. You will see that 5 of the 8 problem areas have to do with requirements. You'll notice in particular the second one, lack of user involvement, and right at the bottom, the system no longer needed. In each of these cases, failure to understand the requirements led the developers to build the wrong system. In an earlier lecture, I used this diagram to illustrate iterative refinement. As you can see, each time you go round this loop, there is a requirements process step. So the requirements emerge iteratively with increased detail each time there is a separate iteration. You can contrast this with the modified waterfall model. With the waterfall model, the aim, the target, is to get the requirements right at the beginning of the project and not have to make substantial changes later. But the modified waterfall model accepts that there are going to be changes and the requirements will need updating as the project continues. With incremental development, such as Agile, the emergence of the requirements is not so explicit, but actually each sprint is a miniature software development process of its own. So each sprint will have the requirements development as part of it. Now for some more details about the requirement goals and how to achieve them. The first is to understand the requirements in appropriate detail. This word appropriate is important and we'll discuss it later. Once the requirements have been understood, the next thing is to define them in a manner that's clear to both the client and to the implementers. This may be in the form of written specification, a prototype system, or other form of communication. Finally, it's important that the client and developers really understand the requirements and their implications. Many CS5150 projects use the first presentation and the accompanying report to confirm the requirements with the client. Let me teach you a term that's quite useful in such presentations. When you present the requirements to your client, say, "Our understanding of your requirements is that you want something." The requirements phase can be divided into sections. The first is analysis, to understand the system services and constraints, and this is done by consultation with the client and with customers and users. This often ends up with something that's quite complicated, and we use modeling to organize the requirements in a systematic and comprehensible manner. Finally, we need ways to define and communicate the requirements. With iterative methods, these stages are repeated several times. This diagram is another way of showing this breakdown. After the feasibility study and the feasibility report, which will themselves have something about requirements, an outline of the requirements, the next step is to analyze the requirements in appropriate detail. This may lead to a separate report or an alternative description, but certainly it will feed in to the modeling phase and from there to the definition phase, and at the end is the challenge of recording and communicating the decisions. The rest of this lecture looks at requirements analysis. And the central part of requirements analysis is discussions with clients. Clients often have only a vague concept of the requirements of what they want from the system, and you're going to have to allow plenty of time to meet with them and talk through what they want. Before you meet with them, have a team meeting to discuss how you're going to go about the meeting and what you're trying to achieve. During the meeting, keep full notes. There should be somebody whose job is to be a scribe, to write down what is agreed. During the meeting, you will often not understand quite what the client expects of you, so ask more questions. Delve further again and again. I find a very useful technique to check my understanding is when the client tells me something, to repeat back in my own words what I think I've heard. For your CS5150 projects, you'll need to schedule several meetings. I suggest small groups of maybe 3 or 4 team members rather than the entire team. To understand the requirements in depth, you need to put in a lot of effort. Often, the project will be in an area that you don't understand. I remember a very experienced software developer working on a production system for manufacturing light bulbs. He could not understand the requirements as the client described them, so he simply went and worked on a production line for a week making the light bulbs so he could really understand what was going on. The real requirements of all the stakeholders may not be clear. They may not themselves understand them, or they may express them in strange ways. Very often, they are close to the old way of doing things, and it's difficult for them to conceive of what a new system might do for them. Finally, beware of terminology. Clients often use specialized terminology, and you may be shy about asking for an explanation, but you must do that, because if you don't understand the terminology, you cannot reach agreement. So the basic rule of client interviews is keep asking questions. Why do you do things this way? What is essential? What are the alternatives? I don't understand. Please explain it again. Take your time and make sure you really understand the requirements before you end the interview. Sometimes you may have the opportunity to work on an entirely new system, but this is rare. More often, you will be replacing an existing system, improving it in various ways, adding new functionality and so forth. At other times, there will be a legacy system that you have to interface to, which is not being replaced, but has to work with the new system. Clients often get confused about the requirements for the new system and confuse them with features of the current system, which may or may not be important for the future. So in your requirements analysis, you're going to spend quite a lot of time talking to the client and analyzing features of the current system that really are needed in the new system, and distinguishing them from features of the current system that are not needed in the future. Unspoken requirements. There are sometimes requirements that the client doesn't tell you about. This may be things that are such second nature they don't even think about mentioning them, but they're often organizational. There may be resistance to change within the organization. There may be departmental friction. For example, a sensible way to develop a system might involve taking staff away from one manager and assigning them to a different manager. Then everybody has strengths and weaknesses. They have things that are important to them which may not actually be of importance to their organization. I've already mentioned stakeholders. Any complex system affects many groups of people. For example, the client and the client's senior management. There's the production staff, the people who will run the system, the computing staff, the operators. There'll be the customers, there'll be users, and there can be many categories of users, and there can be many other types of stakeholders. For example, if you're developing a web shopping site, clearly the shoppers are stakeholders, and there can be different types of shoppers. But there'll also be the people who administer the site, there'll be finance people, there'll be the warehouse, and so forth. CS5150 projects that build web applications usually find that the part of the system seen by the users is actually smaller than the administrative system that is not visible to the users. Viewpoint analysis is a useful technique whereby you look at the requirements from each group of stakeholders in turn. For example, if you're developing a university admission system, one group of stakeholders are the applicants, the people applying to the university. What are their requirements? But there are also people at the university, the admissions office. What do they require to do their job well? Financial aid office and special offices like athletics. And finally, of course, the academic departments. What do they require from an admission system? Below the line here, I've mentioned the computing staff, the operations and maintenance. They're easy to forget, but it's important that they should be able to use the system and that their requirements are thought about in advance. Understanding the requirements may need special studies. For example, if a product is to be sold, there'll be market research like focus groups, surveys, or competitive analysis. The project manager for Windows XP did competitive analysis of Apple strengths and printed T-shirts to highlight areas in which Apple operating systems were strong. Technical evaluation is often useful with experiments or prototypes. The same project manager reported experiments with Windows XP to see ways to make Microsoft operating systems boot faster.
Lecture 6, Requirements Analysis, end of Part 1. Lecture 6, Requirements Analysis, Part 2.
Software engineers disagree about the best ways to define and communicate requirements. Before looking at the various ways of doing this, let's look at the objectives. The first thing is there needs to be a record of the agreement between the clients and developers. This is used as a basis for acceptance testing. It also provides visibility to everybody involved and is the foundation for the program and system design. It also is used to communicate with other teams who may work on or rely on the system, and it informs future maintainers of what the system sets out to do. As you define your requirements, it's important to be realistic. For example, there is no purpose achieved by stating for a requirement something that cannot be done. So if you write the system must be capable of doing X, but there's no known computer system that can do X at a reasonable cost, that's not a realistic requirement. Next, since the requirements are going to be the basis for acceptance testing, they must be verifiable. It must be possible to test whether a requirement has been met. So it's no use to say the system must be easy to use. You must define what is meant by being easy to use. For example, after 1 day's training, an operator should be able to input a certain number of orders in a fixed time period. Defining and communicating requirements is an area in which heavyweight software processes differ substantially from lightweight processes. Heavyweight processes expect detailed specifications. This is usually a written document that specifies each requirement in detail. This document has to be checked by the client and developers, often with a formal sign-off, and may turn into a contractual document. The difficulties are fairly obvious. This is time-consuming and difficult to create, and is equally time-consuming and difficult to maintain. Checking a detailed specification is difficult and tedious, and the details may obscure the overview of the requirements. In practice, the clients never or very rarely understand the implications of all the details, and they rarely check the details as thoroughly as is necessary. These difficulties are one of the reasons that many organizations are attracted to the lighter weight development processes. The idea with the lightweight processes is, as far as possible, to use an outline specification and use other tools for creating the detailed requirements. There will be documentation describing key requirements which has to be reviewed by the clients and developers, but as far as possible, this will be kept quite short. The details will be provided in other ways. For example, user interface, mock-ups or demonstrations, or models such as a database schema or a state machine. In general, clients understand these prototypes and models better than specifications, and iterative or incremental developments allow the client to appreciate what the final system will do, and hence the proposed requirements in a way that's much easier to understand. The challenge is to distinguish those details that do have to be specified carefully, and it requires experience and judgment to know what is necessary and what can be left for later in the development process. Here are some examples where detailed specifications are usually needed. Business rules like accounting standards, they've just got to be right. Legal restraints like laws on retention of data or privacy. Data flow, like where does data come from and how is it validated. I think in general, the danger with lightweight processes is to miss some important details, and this can lead to misunderstandings between the client and the developer. The whole intent of lightweight processes is to have minimal intermediate documentation, but some is needed. As I'm sure you know, government systems in the United States and abroad have a reputation for poor functionality combined with delays and cost overruns. My personal opinion is that the method of contracting is a major contribution to these problems because it leads to heavyweight development processes when they're not appropriate. Responsible use of taxpayers' money leads to contracts in which each process has a defined deliverable at an agreed price. In particular, contracts will demand a detailed requirement specification before the contracts for design and implementation are placed. And this leads to a waterfall model of development, often with penalties for modification of the requirements. But in many government systems, the requirements are not well understood. In that case, you cannot use a sequential process. The departments should use a development process in which the requirements are flexible and the design evolves iteratively. Contracts for such processes are difficult to write, but they're necessary and they lead to better software. You will sometimes hear the terms functional requirements and non-functional requirements. The functional requirements are what you think of when you're thinking of requirements. They describe the functions that the system must perform and include topics such as the underlying functionality, the data that's maintained, and user interfaces. Non-functional requirements are not directly related to the functions that the system must perform, but they're often quite important in practice. For example, there may be product requirements like performance, reliability, or portability. There may be organizational requirements like delivery, training, standards, and so forth. Or external requirements such as legal or interoperability. Market and public relations often have their own requirements. As an example, We developed a system called the National Science Digital Library for the National Science Foundation. And the client wanted a live system that could be demonstrated to senior managers 6 months after the grant was awarded. Here's an example of a project I worked on some years ago, developing a repository for the Library of Congress. The non-functional requirements were quite extensive. First of all, since they were going to be maintaining the system, they wanted technology that their staff were familiar with. So the hardware and software systems that they used were the IBM Unix systems. Their database system was Oracle, and their preferred programming languages were C and C++. So there was non-functional requirement to build a system that was compatible with this technology. There were also some non-functional requirements to do with the fact that this client was a federal library. There are regulations covering government systems. For example, the systems have to be accessible to people with disabilities. Finally, and it was an important requirement, that the library developed a system that other libraries would consider to be a modern, well-engineered system that they could all look up to. Satisfying the client is a fundamental goal of all software development, but that doesn't mean that you should automatically accept every proposed requirement. Sometimes you need to negotiate with the client before you can reach agreement about what can be done. Sometimes the client will make requests that conflict with others, and you've got to recognize and resolve these conflicts. Often they involve the trade-off between functionality, cost of the system, and the time to implement it. I used the example of the boot time for a Windows operating system earlier. It turned out that the Windows system could be made to boot faster by using a shorter timeout on the checking for equipment. But there was a risk that some equipment that was connected to the computer might not be recognized. What does the client want, and what is the optimal trade-off? So what do you do if the client requests functionality that's very expensive or impossible? Well, the first thing is to talk through the requirement with the client. What is really wanted, and what are the alternatives? Explain the reasoning behind your concern. There may be a technical or an organizational or cost implication that's not obvious to the client. Be open to suggestions. There may be a gap in your understanding. Then perhaps a second opinion might come up with other alternatives. But before the requirements phase is completed, the client and the development team must resolve these questions. You've got to have agreement. Early in my career, we worked on a system for the National Science Foundation to manage the grant proposals. The client originally asked for every format that had ever been used in proposals, which would have been an enormous project. After considerable negotiation, they agreed for a first phase in which we would only support a single format, and this eventually was PDF, and it's turned out in practice that that's all that's been required. To end, let me emphasize the difference between the requirements analysis and the system design. The requirements look at the system from the client's point of view, not from a technical point of view. And the requirements analysis should make minimal assumptions about the system design. But there's a dilemma here. In practice, while you're working on the requirements, in the back of your mind, you're thinking about possible systems that might satisfy the requirements. And the requirements definition has to be consistent with computing technology and the resources available. So in practice, the analysis and design do overlap. However, do your utmost not to allow assumptions about the design to influence the requirements analysis, and don't allow the requirements analysis to be done in such a way that it prejudices the system design.
Lecture 6, Requirements Analysis, End of lecture. Lecture 7, Scenarios and Use Cases.
This is the second of 3 lectures about how the software development team and the client work together to establish the requirements for a project. Scenarios and use cases are 2 excellent techniques that are widely used in developing the requirements.
First of all, scenarios. A scenario is a scene that illustrates some interaction with a proposed system. So it's a tool used during requirements analysis to describe a specific use of a proposed system. Scenarios capture the system as viewed from the outside, for example by a user, using specific examples. I might mention that the terminology and the definitions of scenario and also use cases vary and different people use them differently. Some authors restrict the word scenario to refer to a user's total interaction with the system, and other authors use the scenario to refer to parts of the interaction. In this course, the term is used with both meanings. We need some way to represent a scenario, and some organizations have complex documentation standards for doing this. At the very least, your description of a scenario should include the following: a statement of the purpose of the scenario, the individual user or transaction that is being followed through the scenario, and assumptions about equipment or software. Finally, the description has the steps of the scenario. To create a scenario, the development team has an interview with the client. Here's an example. The requirements are being developed for a system that will enable university students to take exams online from their own rooms using a web browser. And you want to create a scenario for how a typical student interacts with the system. In the next few slides, we have a very artificial example of an interview. The questions in blue are the types of questions to ask the client while developing a scenario. So we have the purpose: a scenario that describes the use of an online exam system by a representative student. You might ask the client, who is a typical student? And the client might suggest a senior at Cornell majoring in computer science. You can ask, where can the student be located? Do other universities differ? Then you'll need to ask questions about equipment. Is there a list of supported browsers? Are there any network restrictions? Now for the actual scenario. The first step is authentication. You ask the client, how does a Cornell student authenticate? Then the student starts a browser and types the URL of the exam system. How does the student know what URL to type? Then you get a list of options. Is the list tailored to the individual user? Here's some more typical questions as you go through the scenario. For example, with a list of questions, can the questions be answered in any order? Is it possible to edit a previous answer? What type of questions are they? Text, multiple choice, and so forth. And if the student submits a file, what types of files are accepted? Here's some more questions to ask your client. When changing a solution, can the student edit a previous answer, or must it always be replaced with a new answer? Does the student have to do the entire exam in a single session? Or can the student save completed questions and come back later? If the student comes back later, is the process any different from the initial work on the exam? What's the procedure for submitting the exam to the graders? What if the student has not completed every question? And should the graders be notified? If the student submits the exam can the student still see the solutions? What's the procedure for logging in to check the grades? When are the grades available? How does the student know? Is it possible to ask for a regrade? What are the policies and what are the procedures? Developing a scenario with a client in this way clarifies many of the functional requirements that must be agreed before a system can be built, such as policies and procedures. The scenario will often clarify the requirements for the user interface, but the design of the user interface should not be part of the scenario. Although this scenario is quite simple, many details have been left out, and you'll need many more scenarios before you've got all the functional requirements for a real system. Scenarios are particularly useful for analyzing unusual or special situations. For example, reversals. In a financial system, it's quite common for a transaction to be credited to the wrong account. Create a scenario that describes the sequence of steps that are used to reverse the transaction. Errors. A mail order company may have several copies of its inventory database. Sooner or later, these copies will become inconsistent. Create a scenario which describes the recovery procedure in this situation. Malfeasance. In a voting system, a voter has houses in 2 cities. What happens if he attempts to vote in both of them? You'll notice that several of these scenarios involve error recovery. As Murphy's Law says, if anything can go wrong, it will. As part of your requirements analysis, you need to think about everything that can go wrong and how the system is expected to handle it. Each scenario describes one interaction with a proposed system. Scenarios are very useful in discussing the system with a client, but requirements need to be more precise, more generalized before a system is fully understood, and this is the purpose of modeling. The model that we're going to concentrate for requirements is called a use case. If you want to read more about use cases, I suggest you look at Wikipedia. The approach that I use in this course is less complex than the Wikipedia article. In essence, a use case consists simply of an actor and a task. So here are 2 examples. In the first, somebody wishes to borrow a book, and the task is to borrow a book. In the second, the actor is a device, a pressure sensor, and the task is to record some pressure. So the actor is a user of a system in a particular role, and it can be either human or an external system or some sort of device like the pressure sensor. And the use case is the task that the actor needs to perform with the help of the system, so to borrow a book or to record pressure. People sometimes get confused about actors. An actor is a role, not an individual. So a certain individual, like a librarian, could have many roles, and the actor must benefit from the use case. So a librarian who processed a book when borrowed is not the actor. The actor is the person who is borrowing the book. When you're naming actors, choose names that describe their role, not generic names like user or client. Earlier, we developed a scenario for a student using an exam system. To model the student's interactions with the system, we need 3 separate use cases. In each, the student's role is an exam taker, so we call our actor exam taker. The first use case is to take the exam, the second is to check the grades, and the third is to request a regrade. As with scenarios, we need a systematic way to record a use case, and some organizations have complex documentation standards. At the very least, the description should include the following: the name of the use case, which should summarize its purpose, the actor or actors, the flow of events, and any assumptions about the entry conditions. So let's do the take exam use case. The name of the use case is take exam. There's one actor, and that's the exam taker. And here's the flow of events. I won't read them out, you can look at them for yourself. Continuing the flow of events, you see that it ends with the exam taker logging out. There's some entry conditions. The exam taker must have authentication credentials, and the computing requirements are that the exam taker has a supported browser. Most systems have more than one actor. For the exam system, a second actor will be an instructor. And here are 3 use cases for the instructor: set the exam, grade, and regrade. Note that actor is a role, so an individual may be a student on one course and a grader on another course. So this individual has the role of exam taker on some of the use cases and the role of instructor on other use cases. Use cases can make use of other use cases. Here, for example, we have a use case, authenticate, that can be used in many contexts. In particular, our 2 use cases, take exam and check grades, both use the authenticate use case. Here's another example. We have a use case, connection fails, and this extends the take exam use case. Includes is used for use cases that are in the flow of events of the main use case, and extends is used for exceptional conditions, especially for those that can occur at any time. This slide summarizes the use of scenarios and use cases in the development cycle. They both have the advantage of being intuitive. They're very easy to discuss with clients, including non-technical clients. Scenarios are fundamentally a tool for requirements analysis, but in addition, they're useful to validate use cases and to check the design of a system. At the end, they can be used as test cases for acceptance testing. Use cases are a tool for modeling requirements, and the set of use cases can provide a framework for the requirement specification. They're the basis for system and program design, but in practice it's often quite hard to translate use cases into class models. Use case diagrams show the relationships between various actors and their interactions with the system. Here is an example based on a use case diagram from Wikipedia. It shows the interactions involved in dining at a restaurant. So the actors are a waiter, a diner, a cashier who takes the money, and a chef. And the use cases are ordering food, which includes ordering wine, serving food, eating food, paying for food, and cooking the food. If we look at, for example, the use case order food, we can see the waiter, the diner, and the chef all interact with this one use case. To repeat, a use case diagram shows the relationships between actors and their interactions with a system. A common mistake is to think that the use case diagram should also show the logic of these interactions, and this is wrong. To emphasize this point, here's an old examination question. It's about a pizza ordering system. The system allows the user of a web browser to order pizza for home delivery. To place an order, a shopper searches to find items to purchase, adds items one at a time to a shopping cart, and possibly searches again for more items. When all items have been chosen, the shopper provides a delivery address. If not paying with cash, the shopper also provides credit card information. The system has an option for shoppers to register with the pizza shop. They can then save their name and address information so that they do not have to enter this information every time that they place an order. So the task was to develop a use case diagram for a use case for placing an order, place order. The use case should show a relationship to two previously specified use cases: identify customer, which allows a user to register and log in, and pay by credit, which models credit card payments. Here is a correct solution. There is a single actor, shopper. The main use case is place order, and that includes the use cases pay by credit and identify customer. This diagram also shows an optional link between the shopper and identify customer. Here's a wrong solution. There are three logic steps: search menu, add to cart, and pay. These are not use cases. These are logic steps within the place order use case. If you can understand why this is wrong, then you have a good understanding of how to use use cases in requirements modeling.
Lecture 7, Scenarios and Use Cases, end of lecture. Lecture 8, Models for Requirements Analysis and Specification.
This is the third and final lecture about the requirements process step. It looks at a variety of models that can be used for requirements analysis and how they can be used to provide a precise specification of the requirements.
As you build your understanding of the requirements through techniques such as viewpoint analysis, scenarios, and use cases, you use the models to analyze and specify the requirements. The models provide a bridge between the way the client looks at a project and the developer's viewpoint. And the craft of requirements analysis is to decide which models, which tools are appropriate for a particular task. In any given project, you may use several of these models or you may not use any of them. There are a variety of tools and techniques. You have to decide which to use. You'll find that some of them you already have seen from other courses. But always remember, there's no correct technique that fits all situations. You have to choose what's appropriate for a given project. Most of these models are related to the Unified Modeling Language, UML, and here's some books that I find good introduction to the subject. Booch, Rumbaugh, and Jacobson are the three founders of UML. And the first book here is the definitive book. I like this book a lot. There's another book by Booch and a number of his colleagues which goes into some of these techniques in more detail with an emphasis on object-oriented analysis and design. And I like the book by Pooley and Stevens as having lots of practical examples for you to get to know the language better. During the 1990s, Booch, Rumbaugh, and Jacobson developed alternative ways to model software systems. We are fortunate in that instead of competing, they worked together and developed UML, which combines ideas from all three of their approaches. We're also fortunate that the three of them write very well, so their books are excellent and easy to read. The next few slides are based on their ideas. First of all, what is a model and why do we have them? A model is a simplification of reality. We build them so that we can better understand a system that we're developing. And this particularly applies to complex systems, because we cannot comprehend a complex system in its entirety. Models can be informal or formal, but the more complicated a project, the more valuable a formal model becomes. Some principles of modeling. First of all, the choice of what models we use has an influence on how a problem is attacked and will almost certainly shape the solution. For this reason, no single model is sufficient. Every non-trivial system is best approached through a small set of nearly independent models. This is rather like viewpoint analysis that looks at a system from various viewpoints. Again, every model can be expressed at different levels of precision. But whatever level of precision you use, it's important that good models are really connected to reality. UML is a language for modeling software systems, and it serves as a bridge between the requirements and the implementation, and it's a means to specify and document the design of a system. It is supposed to be process and programming language independent, but parts of UML are particularly suited to object-oriented program development. The three authors created a system called rational rows, which is used to create and manage UML models, both the diagrams and the specifications. Rational rows is now owned by IBM. I will show examples of rational rows when we talk about object-oriented programming. I mentioned that UML consists of diagrams and specifications. So a model consists of a diagram and a specification. A typical diagram is a graphical representation of certain elements, usually a set of vertices and arcs showing relationships between the elements. In the lectures, I will often only show you the diagram, but the diagram has to be supported by technical documentation that specifies in much more detail than the model what is being represented. For practical software development, a diagram without a specification is of little use. The first model we're going to look at is the data flow model. Data flow models are not actually part of UML. Data flow is an informal modeling technique, and we use it to show the flow of data through a system. It's typically used for data processing systems. In the diagrams, I will use 4 symbols. I'll use a small circle for an external entity, a curved box as a processing step, and a rectangle as a data store or a source of data. Arrows represent data flows as they move between these steps. So for example, let's look at a university admission system. Here is a very crude data flow model which might be a first attempt. At the left there's an applicant, and the applicant fills in a form, and there's a processing step to assemble the application from various inputs. Then a completed application is sent to an evaluation processing step, which produces either a rejection or an acceptance. This first attempt shows the basic information flow, but there's a great deal missing. Where is the data stored? What about supporting information? As you talk through the requirements with your client, you'll find there's much more data in the system. This diagram shows part of a data flow model for the application system. On the left, there is an applicant who submits an application form. There are also supporting documents like transcripts and recommendation letters. These are handled by a process called Received Documents. This process sends out an acknowledgement letter for each document and stores the documents in a pending database. When there's a completed application, the application is forwarded to the begin evaluation process. This sends out an acknowledgement that all the documentation has been received and stores the completed application in the applicant database. It then passes an evaluation request to the next stage in the processing. This slide shows a continuation of the data flow model. The evaluation requests are handled by a process called evaluation. There can be special requests which also go into the evaluation process. For example, at Cornell, any descendant of Ezra Cornell will trigger a special request. This evaluation process makes use of the application database, and it results in either a rejection or an acceptance. If it's an acceptance, it's passed to the financial aid, and the financial aid will be combined with the other material and form an offer to the student. A data flow model shows data passing through a system. We need a different model to look at the logic of processes such as the evaluation process in the admission system. One such model is a decision table. Here is a very simple decision table that might be used for a university to decide whether to accept or reject an applicant. In the model, each column is a separate decision case. So the first column says, if it's true that the SAT is greater than some threshold, S1, then accept. The next column says, if it's false that the SAT is greater than the threshold, but true that the grade point average is greater than G1, then accept. The next column says, if they're both below some threshold, but the SAT is between S1 and a lower threshold, S2, and the grade point average is between G1 and a lower threshold, G2, then accept. The three other columns show the other possibilities, and they all result in a decision of reject. A flowchart is a model that shows both the logic of part of a system and the paths that data takes through the system. There are various notations used for flowcharts, but almost all of them have an operation or a process in a rectangular box and a decision in a diamond-shaped box. Here, for example, is a flowchart for the University Admissions Assembly application. I won't go through this in detail, but you can see that it combines part of the logic and part of the data flow. Some people like to use pseudocode for modeling the logic of requirements. Here, for example, is pseudocode for the university admissions decision. The notation used for pseudocode can be informal or a standard used by your software development organization, or it can be based on a regular programming language. What matters is that it's clear. Personally, I don't think you should use pseudocode unless you have a technical client. If you have a non-technical client, the notation may be confusing.
Lecture 8, end of Part 1. Lecture 8, Models for Requirements Analysis and Specification, Part 2.
Many of you will have come across finite state machines as a design tool. They're also extremely useful for requirements modeling. and have the great advantage that the requirements model can be used directly for the design and the implementation of a part of a system. Finite state machines start with a transition diagram. You model a system as a set of states, SI, and transitions from one state to another. Then you have a set of conditions, and each condition causes the transition from one state to another. Formally, this is represented by a transition function, f of SICJ. In the example, there are three states, S1, S2, and S3, and conditions 0 and 1 from each state. So, for example, if you're in state S1 and have condition 0, you go to state S2. Here's an example of a finite state machine model that shows how you use the technique in requirements. Unfortunately, I took this scenario and state diagram from a published example many years ago, and I have no record of the source. If you know where this example comes from, please let me know so that I can acknowledge the author. Here's the example. It's a radiation therapy control console. Suppose that you are developing requirements for the operator's control console. In an interview, the client describes the procedures the operator must follow when operating the machine, and you decide to use a finite state machine model to specify the procedures. The purpose of this model is to show the client that you understand the requirements and to specify the procedures for the developers. Here's a scenario. The client gives you the following rough outline of how the machine is used. The setup is carried out before the patient is made ready. The operator selects the patient information from a database. This provides a list of radiation fields that are approved for this patient. The operator selects the first field. This completes the setup. The patient is now made ready. The lock is taken off the machine, and the doses with the field are applied. The operator then returns to the field selection and chooses another field. From discussions with the client, you determine that the operator's console can be in one of 5 states. There is the state in which the console is receiving data about patients, the one in which it's receiving data about fields, the state in which the console is set up, the ready state, and the state in which the beam is on and actually delivering radiation. This diagram also shows the various transitions. For example, if you're in the field state, hitting enter takes you to the setup state. Also from the field state, you can go back and select patient. You sit down and discuss this diagram with your client, and when you have total agreement about the states and the transitions, then you have a model that you can go on and work with. Sometimes it's more convenient to use the state transition table instead of a diagram. This table has exactly the same information as the diagram. On the left-hand side, there are the states, and across the top there are the various transitions, so that, for example, if you're in the field state and you select patient, then you go back to the patient state. This table can be used throughout the software development process for requirements definition, program design, and acceptance testing. A very useful way to use transition diagrams are very useful for specifying and designing user interfaces. For example, with websites, they show how you can navigate from one page to another. Here is part of the CS5150 website. Each state is a page or a group of pages, and the arrows show the transitions, how you can get from one page to another. If you've ever worked on relational databases or taken a database course, you will have come across entity relation models. An entity relation model is the standard methodology for doing requirements and design for relational databases. What you have is a database of entities and relations and tools for displaying and manipulating the diagrams and the database. The models can be used both for requirements and for design. There are various notations used for entity relationship diagrams. This is the notation used by Chen, who introduced the models way back in 1976. He uses a rectangle as an entity, which you can think of as a noun, and a diamond as a relationship between entities. He uses the oval box as an entity or relation attribute. Here is a very simple entity relationship diagram for the projects on this course. There are three entities. In the middle, there's a project. On the left, there's a CS5150 student, and on the right, a client team member. A student could have an attribute such as a major. A student who has a relationship to a project of is member. So a student is member of a project, and there can be 6 to 8 students on one project. Client team members have a choice of relationships. One client team member has the relationship is client. But there may be other contacts, like technical contacts, and so that you have the client team member, one client team member has a relationship between 0 and any number of projects. Here is the actual database schema that we used for a large research project using huge amounts of web data. It's an example of an entity relationship diagram used as a design tool. In this diagram, each table represents an entity. So there is an entity which is a page, or a URL, or a crawl number, or a host. And each arrow represents a relation that was modeled in the database. So if you look at the page entity at the top left, you see its principal key is the page ID, and there are the various metadata like the URL protocol and so forth. This is a very typical database schema using entity relationship diagrams. If you want to be really certain that you and your client agree on requirements, there is nothing better than a prototype. Rapid prototype is a modeling method for specifying requirements in which you build part of a system to demonstrate the functionality of those parts. It's particularly valuable for user interfaces, and we will talk about prototyping when we discuss user interfaces. One thing to remember as you develop requirements is the importance of definitions. You must be absolutely certain that there is agreed definition for all the terminology that you use. And a data dictionary is a list of names used by the system, which is an important part of the specification of many systems. Each item in a data dictionary typically has the following fields. Its name, for example, start date. A brief definition, what is date? Then you may have other information like what is it? Is it an integer or a relation? Where is it used? And it might be part of a glossary. If you start your data dictionary while you're working on your requirements, you'll find that you can add to it and expand to it steadily as you develop the system, and it can become part of the final documentation. One last note before we finish requirements. Class and object models, which are very important in program design, are sometimes recommended as modeling tools for modeling requirements. I find it's very difficult to use class and object models at the requirements level because it constrains the system design too much. Flowcharts and finite state machines are supported by UML as design models, but I find that they're also very useful for requirements.
Lecture 8, End of Lecture.
Lecture 9, Usability and User Interfaces.
This is the first of several lectures about usability, the user's experience of your system. This lecture concentrates on user interfaces. Then we have a lecture on the special challenges of web applications and mobile apps. Then finally, there is a lecture about evaluation and user testing. It's convenient to think of user interface as part of the design, but usability is a theme that you have to think about throughout the software development. As part of the requirements, you may provide the client with mock-ups or even with a demonstration. Sometimes you will provide mock-ups as early as the feasibility study to help the client decide whether to do a project.
A computer system is only as good as the experience it provides to its users. If a system is hard to use, the users may fail to find important results, or they may misinterpret what they do find. And some users will give up in disgust. So appropriate functionality, easy navigation, elegant design, and fast response times make a measurable difference to a system's effectiveness. As you work on the user experience, remember that usability is more than user interface design, and that good support for users is more than a cosmetic flourish. Developing good user interfaces is difficult, it needs skill, and it needs time. First of all, some terminology that you'll come across. I've already used the term user experience, which is often abbreviated UX. The user experience is the total of all the factors that contribute to the usability or otherwise of a computer and its systems. You'll also hear the term human-computer interaction, or HCI. Human-computer interaction is the academic discipline that studies how people interact with computers. At Cornell, you're lucky. The Information Science Department and the Communication Departments offer a series of courses in HCI and have major research programs in this area.
The development processes for user interfaces have to be iterative. It's almost impossible to specify an interactive or a graphical interface in a textual document, and requirements need sketches, comparison with existing systems, prototypes, and so forth. Designs should include graphic elements and benefit from a mock-up or other form of prototype. And user interfaces have to be tested with users. Expect to change the requirements and design as a result of testing, so your schedule should include user testing and time to make changes. So whatever process you use to develop a software system, the actual user interface development is always iterative. This diagram shows the iteration. You start by analyzing the requirements, and from this you come up with a design of the user interface. You then build a mock-up or a demonstration or a production system, and you evaluate it with users. As a result of the user testing, you will change your requirements, very likely change the design, and build an improved version of the system, which you then evaluate again. Here are some of the tools you might use for your requirements and also for your evaluation. On the left-hand side, you can see you might ask the client for opinions. You might do competitive analysis. How have other people tackled this problem? Expert opinion is often useful. Focus groups
are a technique from market research, which can be very useful. And then when you have a system that actually exists, you can observe users and take measurements on a production system. The table shows which of these techniques you can use initially, which you need a mock-up for, and which require a prototype or a production system. This slide is an example of a mock-up. This is an actual mock-up that was used in the design of the National Science Digital Library. It looks like a web page, but actually it's just a graphic created using Photoshop. It shows proposed colors, logos, layout of menus, snippets, and so forth. This can be created very quickly and used with clients or potential users before working on an actual operating system. I mentioned focus groups. Focus groups are a standard technique in market research. A focus group is a group interview. It needs a skilled interviewer. The interviewer will work with a group of potential users, typically up to about a dozen. And they should be chosen to have similar characteristics. For example, you might choose people who are the same age or have the same technical background. Then the interviewer poses a structured set of questions, may show mock-ups or even prototypes, but encourages group discussions. The idea that the individuals of the group talking to each other will bring out ideas. The focus group is then repeated with contrasting user groups, and the interviewer summarizes the conclusions. Accessibility. Accessibility is the term used for supporting users who have poor eyesight, lack of hearing, poor manual dexterity, and so forth. Requirements about accessibility are most likely to arise in the user interface, and you may have a legal requirement to support people with disabilities. For example, if you are working on a government system in the United States, you may well have a requirement to comply with Section 508 of the US Rehabilitation Act. There may also be usability requirements associated with equipment. There may be requirements to support computers with poor performance, limited screen size, bad network connections, and so forth. You need to be explicit about equipment assumptions and how you're going to handle failures, and you should do user testing with both good and bad equipment. As developers, you probably will have good equipment with good network connections, but don't just test your software with those machines. I came across an interesting bug with Mac Mail recently. I've been traveling in Eastern Europe where sometimes the internet connections are not very good, and I found that its behavior is erratic if the network connection becomes extremely slow. To repeat, usability is more than user interface design. I find the following diagram helpful in thinking about these things. On the right at the top, we have the user interface. The user interface depends upon the functions provided by the underlying software. These functions depend upon data structures and metadata stored in the computer, and they depend upon the computer systems and networks. Bringing all these things together from the user's point of view, we have the concept of a mental model. A mental model is what a user thinks is true about a system, and it's not necessarily what is actually true. But the mental model should be similar in structure to the system that is representing, because it allows a user to predict the results of his or her actions. The mental model is simpler than the represented system. It only requires the information to allow reasonable predictions. You will often find mental models are called conceptual models.
The mental model is the user's internal model of what the system provides. The computer model is how the computer actually provides those services, and the computer model may be quite different from the user's mental model. As an example, consider the desktop metaphor used by operating systems like Microsoft Windows and Mac OS. This has the metaphor of files and folders sitting on a desktop. Internally, the computer organizes and manipulates the files and folders in a totally different way. Another example is web searching. Many people have the mental model that the web is one vast collection of pages, and that when they do a search on, for example, Google, the search goes out and searches those pages on request. Of course, you know that actually the computer model is different. There is a central index, and the search is searching the index. Here is another example where the mental model and the computer model are different. On the left, you see a page, the front page, of the printed issue of the New York Times. And the mental model that you have is that the photograph is embedded in the text of a document, which is certainly the case with paper. But on the right, you see the digital version. Here, your mental model may still be that this photograph is embedded in the page, but it is not. On the web, that photograph is a separate file, and it's possible that the file could be changed independently without changing the page itself. Lecture 9, end of Part 1. Lecture 9, Usability and User Interfaces, Part 2. Now let's look at user interface design. The user interface is the appearance on the screen and the actual manipulation that's carried out by the users. So it includes things like fonts and colors and logos, keyboard controls, menus, buttons, and so forth. The controls may be mouse controls, touchscreen, or the keyboard. And the user interface is likely to make a lot of use of conventions such as back and help, scroll buttons, and so forth. Typically, there are user interface design choices. For example, to leave the full screen of a video, you may have two options. You may be able to use the keyboard on a laptop computer, such as an escape key or Control F. Or there may be icons which you can use with your mouse or touchscreen, and those icons themselves can be very different. There are three different designs that are commonly used. To give you some more examples of design choices, a page reader like Adobe Reader clearly will use a large portion of the screen to display the page that is being read. But it also has various controls, indexes, and so forth. The designer has to choose how much of the page is used to display the page that's being read and how much is given to the controls. Another example from web search, such as Google. When you do a search, the search program returns a number of short records, commonly known as snippets. The designer has to choose, will you have very short snippets and then you can get many on a page, or will you have longer snippets and then you'll get fewer on a page? Google seems to have decided that snippets of about 4 lines in length are convenient, and that usually gives about 10 snippets per page.
The user interface functions are not the same as the user interface. The interface functions are the actions that are available to the user. For example, select part of an object, search a list or sort the results, view help information, manipulate objects on a screen, pan or zoom. You can have alternative user interface designs for the same interface functions. For example, most versions of the Microsoft Windows desktop have different user interface designs, but they have basically the same interface functions. Applications such as Microsoft Word that run on both Windows and Macintosh computers have to support different hardware. The Macintosh has a one-button mouse, whereas Windows uses a two-button mouse. So same functions, but different user interface design.
Now for the data and metadata. The interface functions and the interface design provide an interface to the data and metadata stored by the computer system. For example, the desktop metaphor has the concept of associating a file with an application. This requires metadata to specify the file type stored with each file. One way of doing this is an extension to the file name, such as .txt and .pdf. Inexperienced clients and graphic designers sometimes don't realize that they cannot specify user interface features that are not supported by the data or the metadata, and it's your job as developers to explain this to them. We will talk quite a bit more about data and metadata when we look at the Model View Controller system architecture. Consider this example. This is an iPad app that plays the game of Go. One of the user features is undo, take back a move. For this to take place, the app has to store the data that says what the previous moves have been. The interface function is undo, take back a move. For this, the user interface is a gesture and perhaps an accompanying beep followed by the change of the board position. The final aspect of usability are the computer systems and the networks. And I think it's fairly obvious that the performance, the reliability and the predictability of computer systems and networks are crucial factors in the user experience. For example, for mouse tracking, you've got to have instantaneous response times. On the other hand, the response times for some activities, such as complex transactions, may determine the action taken by the computer system. For example, credit card approval systems sometimes have the convention that if the response is too slow, the card will be approved automatically. You will sometimes see response time requirements like the following. For actions which take place in less than 0.1 second, the user feels that the system is reacting instantaneously. If it takes a second, the user will notice the delay, but his or her flow of thought stays uninterrupted. 10 seconds is sometimes reckoned as the limit for keeping the user's attention focused on a dialogue. I think I see a trend that as computer systems improve, users get more demanding. So a response time that's good enough today may not be good enough 5 years from now.
User interface design like this is partly an art, but there are some general principles. The first is to be consistent. Be consistent in appearance, controls, functions. The next is feedback. The user needs to know what the computer system is doing and why does the user see certain results. Users need to be in control, so they should be able to interrupt or reverse actions. Errors should be simple, easily handled. And it's very common to offer skilled users shortcuts whereas beginners have simple, well-defined options. Above all, it's really important that the user feels in control.
One of the easiest mistakes to make when designing an interface is to be too fancy. Look at this page for a sailing boat race. A user might want to ask the question, who is leading the race? That's a simple question, and the information is there. But finding it on this cluttered page is extremely difficult. Pages like this tend to be slow to load and often don't look good on every type of hardware. Contrast it with the following from The Economist magazine. There's a lot of information on this page too, but the layout is very simple and it's very easy to find what you're looking for. As an example of how a simple interface can be a very good interface, here is Craigslist, one of the most popular sites on the internet. You can't have a much simpler interface than this, but it works extremely well for Craigslist's purpose. I want to end this lecture with a few special topics. First of all, menus. Menus have lots of advantages. They're easy for users to learn and use. Certain categories of error are avoided, and you can do context-sensitive help. The major difficulty is how to structure large numbers of choices. And this is a topic on which there's been some fairly systematic research. One method that you can use are scrolling menus, for example, a list of the 50 states of the United States. Another technique is a hierarchy, where a top-level menu leads you to lower-level menus. Some menus reach out to associated control panels, and sometimes you'll find a menu that you use with a command line. All of these methods have their place and all can be good. But there's one thing that the research has shown, that in general, users prefer broad and shallow to deep hierarchical menu systems. And that's why user interfaces like the Craigslist user interface work well. There are a lot of choices on the front page there, and so the hierarchies tend not to be very deep.
One of the most difficult parts of user interface design is help systems. By definition, people are likely to be using a help system when they're confused or in trouble. So you must test and prototype with a variety of users, and you must expect to provide many routes to the same information. So you might provide several categories of help. You might provide overview and general information, specific or context-based information, tutorials, cookbooks, wizards, and emergency I'm in trouble sort of things. Help systems need experienced designers. You should schedule plenty of time in your development and user testing. In my own experience, I find very often that the overview and general information is forgotten. That is, what is the purpose of an application and how do you use it in general? Many systems will have the details but not have this general information. A couple of words about information presentation. The user interface presents information to the users. In general, it's often better to provide it in a very simple way rather than a fancy, complex way. So text is a simple way to provide information. It's precise, it's unambiguous, it's fast to compute and transmit. Graphical interfaces are simple to comprehend and learn, but icons can often be difficult to recognize. With a graphical interface, often you can use color or variations of style and layout show different situations in different cases. We talked about the difference between the user interface and the interface functions. There's a similar distinction in presenting content. So you have the information that's to be displayed, and then you have the way that's displayed it. So we might have a simple page of information we wish to display and have two different ways to display it: by a PDF or an HTML file with different presentation software and different outputs. By keeping the information separate from the presentation, we end up with this sort of system diagram.
Finally, I'd like to say a few words about command line interfaces. Modern graphical interfaces are so good that we sometimes forget that there are alternatives. There are problems with graphical interfaces under certain circumstances. They're not good for really complex interactions, and they can be slow for skilled users. It's difficult to build scripts for automatic processing, and that makes them only suitable for human users. The alternative is sometimes to use a command line interface. And here the user interacts with the computer by typing commands. An example is the Linux shell script. This is actually better if you've got complex instructions to give to the computer. It is much easier to develop formal methods of specification and implementation, and skilled users can often input commands very quickly. Problem with them is unless they're very simple, they require learning or training. They can be adapted for people with disabilities, and they can be multilingual. And they're suitable for scripting. So if you've got non-human users, they may be the way to go. Lecture 9, end of lecture. Lecture 10, user interfaces for websites and mobile devices.
Many of your projects will build applications for the web or mobile apps for smartphones and tablets. The user experience is central to these applications. You need to be very conscious of the devices, their capabilities and their weaknesses, and of the networks that they will be connected to. These applications are so complex that you will almost certainly be using tools and frameworks provided for you by manufacturers or other organizations. And remember, user interfaces need user testing. You must leave time on your schedule for user testing and time to make changes based on the results of those tests.
You will remember this diagram from the last lecture. It shows the layers that make up the user experience. With websites and mobile applications, you need to pay particular attention to the characteristics of the computer systems and the networks. These are examples of applications that have a device-aware interface. The interface has to take into account the physical constraints of the computers and the networks. For example, how does a desktop computer differ from a laptop? What is special about a smartphone? How do you make use of a touch-sensitive screen? Or alternatively, how does an application run without one? What works well with specialized devices such as a digital camera? The constraints that the interface must allow for include the performance of the device. For example, does it have fast graphics? With smartphones in particular, the limited form factor is important. They have very small displays and most of them have no keyboard. Finally, connectivity. Websites by definition need a good network connection. Many smartphone apps will run with intermittent connectivity or no connectivity at all. The important thing to remember with networks is that any operation that transfers data over the network has unpredictable response time and is subject to delay. Large data transfers should run asynchronously in a separate thread. You start them going, and then the application is available to do other things. While data transfers are taking place, provide visual feedback to indicate that the operation is in progress. Here are some typical icons. And finally, you need to provide a way for users to cancel long-running data transfers. Smartphones and tablets have small screens. This screen space is precious, and every small area is important. Here are some things to think about as you're designing your interfaces. First of all, there is a big difference in screen size between the smallest smartphones and a large tablet, and there may need to be different layouts or even different versions for these different screen sizes. People use smartphones and tablets either in portrait or in landscape mode, depending on how they rotate the device. Your apps need to think about this, and there may be different layouts for the different orientations. All this leads to the fact that you need to test your apps with a range of sizes of screen and a range of orientations. You may sometimes decide that an app should be optimized, shall we say, for a large screen, and just simply will not run well on smaller screens. In any event, you need to use a simulator to see how your app looks on the various devices. The development environments that are used for mobile apps provide a variety of simulators so you can try your app out with different configurations. Here is an example of an app that I was writing for my own use being displayed on the Apple's Xcode simulator. It shows how my app would appear on an iPad 2 using the landscape orientation. Since I know that this app is going to be run on an iPad, I've used a layout that just won't work on a smaller screen. It's basically a 19 by 19 grid, and that looks good on an iPad, but is too small for a touch-sensitive screen on a small smartphone. Accessibility is a special challenge with smartphones. Smartphones have small displays and small virtual keyboards. Some apps rely on speech or other sound signals. People who have poor eyesight, or are colorblind, or have hearing loss, or are clumsy with their fingers, may have difficulties using your applications. Android and iOS provide numerous accessibility features and provide online advice about how to build accessible apps, but it's still a challenge. For your user testing, try to find people who do not have perfect eyesight, who are colorblind, who have hearing problems. Have your testers of various ages. You will find that older people are often less able to use touch-sensitive screens than younger people. At the bottom of this screen, there is an example from an Android tutorial. On the left, you see two buttons. One is red and one is green. This causes problems. It's useless for somebody who is colorblind. Much better is the one on the right. Here, each button is identified in three ways: by a color, by a symbol, and by a word. With any luck, most people will be able to identify which button to use and use it appropriately. Responsive web design is the term used for techniques that adjust how web pages are viewed based on the size of the screen or other characteristics of the device or browser used to view the page. There are a variety of techniques, such as media queries in CSS, that allow the page to identify the device and use different CSS styles based on characteristics of the device, in particular the width of the browser window. For example, you develop a website using a laptop computer. How will it look on a smartphone? Browsers such as Chrome, Firefox, and Safari have options that allow you to see how your site would appear on other devices. This Chrome example shows how the development version of the CS5150 website would appear on an older Android device. The ideal for responsive web design is to have a single website that adapts to any device by using a mixture of flexible grids and layouts and careful use of CSS media queries. In practice, this is very optimistic. Mobile devices such as smartphones are so different from regular computers that it's very difficult to create a website that works well on everything. For example, less content can be displayed on a small screen than on a large screen. Smartphones are usually used in portrait mode, whereas computer screens are almost invariably landscape. A touchscreen has different characteristics from a mouse. For example, the user cannot hover over a menu item. And finally, virtual keyboards need screen space, usually at the bottom of the screen. For all these reasons, major websites often have several versions of the site for different devices. They identify the user's device and automatically provide the version designed for that type of device. Here is an example using Safari. This example shows the New York Times mobile version of the website as it appears on a small iPhone. Here, for comparison, is the same web page displayed on the version of the website that is optimized for a regular computer screen. You'll see there's a lot more content and the layout is substantially different. Lecture 10, end of part 1. Lecture 10, part 2. When you begin the user interface design, the first thing to think about is navigation. Applications consist of one or more pages on the web or screens on mobile apps. There's a difference between them. On the web, loading a new page uses the network and is therefore slow. On smartphones or tablets, new screens are loaded from within the memory of the computer and therefore they're usually instantaneous. Either way, getting the navigation right is central to the user experience. And the first step in user interface design is to choose what pages or screens are you going to use. What functionality is provided on each screen? How are they organized? How does the user know what other screens are available? And how does the user move between the screens? If the user is going to feel comfortable with an application, the organization of the pages must match the user's mental model. My fundamental advice to you is to keep it simple. In a web application, the basic building block is a hyperlink. This allows any page to link to any other page in the application or any other page on the web. This is extremely flexible,
but easily leads to confusing applications. And for this reason, many websites use a simple structure such as a hierarchical tree structure. Remember that when a user leaves a page, the state is lost unless it's saved explicitly. Mobile apps are different. Both Android and iOS encourage the use of a stack-based architecture. With this architecture, when a user leaves a screen, the state is pushed onto a stack and is available when the screen is next used. In any event, indicate to the user what pages are available and how to reach them. Since navigation is so important to the user experience, before you actually build the application, test the navigation. You can do this with simple mock-ups, such as rough sketches on paper. You should create a large number of straightforward, simple scenarios. They should show all the main paths through the application, including user mistakes, system problems, and so forth. Step through the scenarios with your client and with potential users. These scenarios can be used later in the development process for user interface design, for program design, and all forms of testing. It is much easier to make changes in the basic navigation before beginning the detailed user interface design and implementation. The development of mobile apps is complex. For this reason, most apps are built using development environments such as Android Studio and Apple's Xcode. These are excellent, but they're big and they take quite a lot of learning. There are good tutorials and there's good documentation online, and I strongly recommend that you work through a tutorial before you attempt to build a real app. If you're new to Android or iOS development, allow plenty of learning time. I mean here weeks or even months before you become a professional quality developer. For your CS5150 project, try to have several team members with previous experience of the development environment that you will be using. The environments are moderately flexible for user interface design. They support a variety of ways to navigate, various user interface objects and so forth. But they have limitations. For example, iOS does not have a radio button. If you're going to build a good experience for your users, you must understand and adopt the style of the development environment that you're using. The advantages of this are many. The users will be familiar with the style of interface from other applications. You know that the interface objects are well designed with good technical implementation. They're designed to be used on a variety of devices. And when new versions of the operating system are released, perhaps with different visual graphic style, the designs will need few modifications. Most modern development environments use one of the many variations of a system architecture called the Model View Controller. In this architecture, the user interface is called the view, and many of the interface functions are implemented by user interface widgets that are provided by the development environment. The development environment may also provide recommended styles for the user interface, such as fonts and graphical elements. In the Model View Controller architecture, the interface functions are invoked by the controller. The controller does many other things, but one of its functions is to invoke the user interface functions. The controller manages the flow of control of the whole user interface and connects the view to the model. The model is where the data and metadata are stored. The model also manages the logic of all parts of the system that are not parts of the user interface. Now for the actual design of the user interface for mobile apps. Here is the challenge. How do you design a user interface with no instructions, no user manual, and no training for the users? Well, there's some techniques that you can use. First of all, the look of the design. Characteristics of the appearance that convey information. Then there's the feel. Use interaction techniques that are intuitive and provide satisfactory experience. Often, you will have metaphors or mental models that help the user. The problem is that there may not always be an intuitive model, but if there is, it helps enormously. We've already said a little bit about the navigation rules. How do you move among data, functions, and activities in a larger space? And finally, make use of conventions. Use familiar aspects that don't need extra training. This is good for the users, good for the designers. Examples are scroll bars, buttons, gestures, help systems, sliders. The users have seen them before and know what they mean. The development environments include standard classes that provide templates for navigation and the layout of screens. They are the basic building blocks of your applications. The designs that use these classes can use the services such as APIs that the operating system provides. This example is the Settings app for iOS. It uses an iOS table view controller. Because the length of tables can be very long, iOS implements a table view controller in a manner that makes efficient use of storage and processing power. This is the sort of benefit you get by using the standard classes. I mentioned conventions. The development environments encourage consistent apps. Take a look at this screen. You may have never used this app, but look how familiar it seems. There are many aspects, icons, and controls here that you've seen before, and you know what they do without having to get any instructions. I want to end this lecture with a few general comments. First of all, some of the design tensions in web and mobile applications. Designers, particularly graphic designers, want to control what the user sees. But users want to control their own environments. Always remember that client computers and network connections vary greatly in capacity, that the client software may run on various operating systems which may not always be the current version. Accessibility requires that designers do not take control of parameters such as font size. In building your systems, be explicit about the assumptions you make about the user's computer, web browsers, etc. And in using style sheets such as CSS, avoid overriding user preference. Finally, a word about cost. User interface development may be a major part of a software development project. Good usability may be expensive in terms of hardware or special software development, and the costs are multiplied if a user interface has to be used on different computers or migrate to different versions of systems. This is a strong reason to design user interfaces that can be built with standard tools. With web browsers, the browser provides a general-purpose user interface, and other people maintain the user interface software. With the mobile app development environments, use the standard classes that the environment provides. Lecture 10, End of Lecture. Lecture 11, Evaluation and User Testing.
This is the final lecture about usability. It's about user testing and evaluation. User testing is an essential part of any project that has a user interface. Be sure that you allow plenty of time on your schedule to do it thoroughly, and be sure to allow time to make changes as a result of things that you discover during the test.
You've seen this diagram before. It's the iteration used to develop user interfaces. In the last two lectures, we've looked primarily at analyzing the requirements and designing the user interface. We now want to look at the evaluation and user testing. These are very different tasks, and I strongly recommend that whenever possible, the design and the evaluation should be done by different people or different groups of people. If your system has users, your schedule must include time for user testing and evaluation, and time to make changes after the testing is completed. So when are you going to do the evaluation? During development, you're going to be doing testing continually and making iterative improvements. When the system is ready to be launched, part of the acceptance testing is to look at the usability. Finally, after the launch, you will almost certainly find opportunities to make iterative improvements. There are three main methods of evaluation. The first is empirical, evaluation with users. This is often called user testing. The second are measurements made on operational systems. And finally, there is some theoretical work, though we're not discussing it in this course, about how to analyze and evaluate systems without users. Usability is more than user interfaces, and evaluation has several aspects. There's even an ISO standard that defines the various aspects. The first is effectiveness, the accuracy and completeness with which users achieve their goals. And this is measured by the quality of solution, error rates, and so forth. The next is efficiency, the relationship between the effectiveness and the resources expended in achieving them. And the measures here are the time to complete tasks, learning time, number of clicks, and things like that. Finally, there is satisfaction. This is the user's comfort with and the attitudes towards the use of the system. And this is normally measured with attitude rating scales. Evaluation with actual users is time-consuming, it's expensive, but it's essential that you do it. If you're going to get good value for your effort, you need to be systematic about it. So your evaluation goes through three stages. One is prepare. What are you trying to achieve? Then conduct the actual sessions. And finally, analyze the results. For the preparation, the first thing is to determine the goals of the usability testing. For example, you might have a question, can a user find certain information in no more than 2 minutes? Then you will have certain tasks that you ask the user to carry out. Given a new customer application form, add this new customer to the customer database. Then you need to recruit the participants. Ideally, the participants should be those who will be using the real system. So use the description of users from the requirements phase to determine the categories of potential users and the users' tasks. For usability testing, you need to monitor the users while they're using the system. It really helps if you have a dedicated usability lab. A basic usability lab has 2 rooms. In one of the rooms is the user. The other room, there are evaluators who are observing the user. There's a one-way mirror between the two, so the evaluators can see the user, but the user is not distracted by the evaluators. Here is a usability lab that we used to have in the information science department. There is a testing session going on. You can see the user sitting at a computer in a simulated working environment and the evaluators watching the user through the one-way mirror. The observations of the user take several forms. One is there are human observers. I strongly recommend having at least 2 people observe the session. It's remarkable that different people tend to see different things. There's a video camera so that afterwards one can look back and see what happened during the session. And there's an audio recording. The user is asked to speak aloud as he or she uses the system, explaining what's going on, questions, problems, and so forth. At the end, inquire of the user how satisfied he or she was with the experience. You don't need a great number of users for user testing. If you do it carefully, you can learn a great deal from testing with as few as 5 people. But you have to be careful. First of all, try to find different types of users. There might be some young people, some older people, some experienced people, and some beginners, and so forth. You must prepare carefully. Try to combine structured tests with free-form interviews. Get the people just to try the user interface and see what they observe. Finally, make sure you have at least 2 evaluators for every test. Different people will see different things. It is surprisingly difficult to analyze the results of user testing. If the development team has put a lot of effort into a design, you want it to be successful. This is one of the reasons that I think it's very important that the designers do not do the evaluation. The evaluator's job is to be neutral, to see what the data says, and to respect the user's responses. Be very careful not to make excuses for designs that failed. Remember, you're testing the system, not the users. Statistical summaries are always useful because they're neutral. But pay close attention to the areas where users have some sort of trouble, where they were frustrated, where they took a long time to do something, where they could not complete tasks. But also pay attention to things that went well. There are going to be aspects of the design that worked, and you want to make sure that they are kept and retained in later iterations. Eye tracking is a very useful form of user testing. It's time-consuming and expensive, but the results you get are very special. This slide and the next are from a talk by Dan Russell of Google. You see a user sitting in front of a computer, and there's electronic instruments looking at the user's eyes and seeing where on the screen he's focusing. This diagram shows how his eyes tracked over the screen and which items on a Google display he actually looked at. Here's another example. This one was done by a master's student in communication at Cornell. And you notice the black circles numbered 1, 2, 3, and so forth. Each circle is a place where the user paused, and the lower number is how long in fractions of a second the user looked at that place. Then the line shows how the eye moved and where next the user paused. If you look at this particular example, you'll see this user never looked at all at the menus down the right-hand side of the screen. If this is typical of other users, it gives you an indication that that part of the display is not being used at all. The next few slides are from a presentation by a CS5150 project team at one of their regular milestones. These particular students had taken courses in HCI and showed a very high level of professionalism in their user testing. These slides are shown with their permission. Here is a description of how they're doing the user testing. It describes their procedure. It's continued on this slide, which talks about the types of questions that they were asking. Here are 5 examples of problems found by the user testing. They're all quite small and they were easily fixed, but they were not anticipated before the tests were done. The first is filling in this form. It appears that users did not know what information to put into the boxes. Next, the user might want to edit some of the data, and there's an option to edit the data, but it's just a small word. There it is on the bottom right-hand side of the upper box, and users didn't see this. They looked for something more conspicuous and were puzzled. Now, here is a message that's intended to be helpful, but it uses a technical term, recorded, which for a computing person is probably totally comprehensible, but apparently was not understood properly by all the users. The next 2 problems were also ones to do with technical terminology. Users did not understand what was meant by category or label or medium. These were terms that the client understood and the development team understood, but were not clear to the user. And finally, this reset button. What does it clear? What does it reset? 5 simple examples of things that users found tricky, were easy to fix, but had not been foreseen by quite a skilled team. For evaluation based on measurement, we need an operational system. The basic concept is to log events in the user's interactions with a system. For example, with a web system, when does the user click? Where on the screen does the user click? How does the user navigate from page to page? What keystrokes are typed on the keyboard? When does the user use the help system? What errors are there? This data may be used for statistical analysis or for detailed tracking of an individual user. The analysis of system logs is a relatively inexpensive way to gather data automatically. You can gather data about such factors as which user interface options were used, when was the help system used, what errors occurred, how often, which hyperlinks were followed, click-through data. But there's another sort of measurement that you get from operational systems, and this is human feedback. Complaints and praise should always be listened to carefully. Bug reports. If you have a customer service organization, what requests are made to it? This screen shows a research project done by a master's student a few years ago. The idea of this project was to look at a search system and to track a request through the system. Which parts of the programs were contributing to the results that the user sees? If you are an evaluator doing user testing, it's your job to identify areas where the user interface doesn't work well and to identify the areas that do work well. It is not your job to redesign the user interface. Designers should not evaluate their own work, and evaluators should not try to become designers. Although designers are poor evaluators of their own work, they're almost certainly the right people to make changes. They know the requirements, they know the constraints, and they know the context of the design. They know that some user problems can be addressed with small changes. They know that some user problems require major changes. And they may know that some user requests are incompatible with others. For example, users may ask for lots of options, but some users may be asking for simplicity. You can't have both. And it's the designer's job to work out which makes sense. So the designers and evaluators need to work as a team, but they should not try to do each other's work.
Lecture 11, End of Lecture. Lecture 12, System Architecture.
This is the first of several lectures about design. It's about system architecture, the major components of a system, both hardware and software, and how they fit together. A good architecture is straightforward to implement, it performs well, it's secure, and it's easy to make changes as the system evolves in the future. The architecture is important, so take your time and do it well.
I want to start by repeating the distinction between the requirements and the design. The requirements describe the function of a system as seen by the client. For a given set of requirements, the software development team must design a system that will meet those requirements. In practice, work on requirements and design are interrelated. In particular, when you're working on design, you will often discover new things about the requirements. This feedback is a strength of the iterative and agile methods of software development. We've already looked at user interface design. Now the next few lectures look at the following aspects of design: system architecture, that's this lecture, program design, security, and performance.
Software development is a craft. Software developers have a variety of tools that can be applied in different situations. And the art of software development is to select the appropriate tools for a given implementation. This is particularly the case in design. System and program design are a particularly creative part of software development, as are user interfaces. Your goal is to create designs that people think of as elegant. They should be easy to implement, test and maintain, but above all, strive for simplicity. The goal is to find simple ways to implement complex systems. System architecture is the overall design of a system. This is the stage of the development process when we're thinking about what computers and networks are we going to use. For example, is this going to be a distributed system? What interfaces and protocols? Will we use HTTP, ODBC, or some other protocol? Where is data going to be stored? In relational databases, distributed databases? How are we going to do security? How are we going to do operations like backup, archiving, and audit trails? While working on the system architecture, you should also be selecting the software environments for development, languages, database systems, class frameworks, and so forth, and the testing frameworks. Our models for system architecture are based on UML. The slides will provide diagrams that give an outline of the systems, but the slides usually will not have the supporting specifications. For every system there is a choice of models, and we will frequently use several models for a single system. Choose the models that are clearest to everybody. Remember, when developing a system, every diagram must have supporting specification. The diagrams are good, they show the relationship among parts of the system, but much more detail is needed to specify a system. For example, if you're specifying a web plugin, even at the architectural level, the specification should include the version of the protocols to be supported and implementation restrictions. Subsystems and components. A subsystem is simply part of a system. There are two terms you'll often hear about subsystems. The first is coupling. It's a measure of the dependencies between two subsystems. If two subsystems are strongly coupled, it's hard to modify one without modifying the other. Cohesion is a measure of dependencies within a subsystem. If a subsystem contains many closely related functions, its cohesion is high. Ideally, you would like to divide a complex system into subsystems with low coupling between the subsystems and high cohesion within the subsystems. Component. A component is a replaceable part of a system, and it conforms to and provides the realization of a set of interfaces. For this reason, the UML diagram for a component looks like a plug designed to go into a socket. You could think of a component as an implementation of a subsystem. Here's the UML definition of a component. It's a distributable piece of implementation of a system, including software code, source binary or executable, but also including business documents, etc. in a human system. If we concentrate on the computing part of that definition, we can see components are replaceable elements. Components allow systems to be assembled from binary replaceable elements. So a component is bits, and a component can be replaced by any other component that conforms to the interfaces. A component is part of a system, and it provides the realization of a set of interfaces. Some people confuse components and classes. We're going to talk about classes when we discuss program design, but they represent logical abstractions. They have attributes, data, and operations, methods, whereas components have operations that are reachable only through interfaces. Now for some notation used in UML diagrams. First of all, a package. A package is a general purpose mechanism for organizing elements into groups. Any types of elements can be combined into a package, and this is how we show it on a diagram. A node is a physical computing device, like a computer, a network router, a smartphone. It's a physical element that exists at runtime and is available to run programs on. Typically, components live on nodes. To show how the relationship between nodes and components, here is a very, very simple web system. We have a web browser running on a personal computer and a web server running on some remote computer. The web server serves static pages to the browser, and all interactions require communication with the server. So here is what is known as a deployment diagram. It shows the two nodes, the two computers, the personal computer and the departmental server, and two components, one called a web browser and the other called a web server. Here is how we represent interfaces. It's called a component diagram in UML. We have a component called a web browser that depends upon an interface called HTTP, and we have a component called a web server that provides a realization of that interface. Application Program Interface, this is a term that many of you will know. It is simply an interface that's realized by one or more components. The seminal work on software architectures was done by Mary Shaw and David Garland during the 1990s. They noticed that similar software architectures recur in many different applications. They call this an architectural style. We're going to look at several architectural styles. The first is a very simple style called a pipe. Here, the output from one subsystem is the input to the next. So, a 3-pass compiler might have the following architecture. There is a lexical analysis, and the output from that goes to a parser, and the output to that goes to code generation. Another very well-known architectural style is the client-server. Here we have two components, and the control flow in the client and the server are independent. Communication between the two components follows a protocol. The example we have here is a mail system where one component is a mail client like Microsoft Outlook and the other component is a mail server like Microsoft Exchange. A peer-to-peer architecture is a variant in which the same component acts as both a client and a server. The repository architectural style is a very flexible style for managing large amounts of data. There is one subsystem, the repository, which stores and manages the data. There's another subsystem, which are the transactions that make use of the data, and another subsystem that are components that are used for inputting data. It's a very flexible architecture for data-intensive systems, but it has the disadvantage that it's difficult to modify the repository since all the other components are coupled to it. For this reason, the repository with storage access layer architectural style is very appealing. Here, the repository is divided into two parts. There's a storage access component, and this supports interfaces that are known to the input components and to the transactions. The storage access component talks to a data store. It's sometimes called a glue layer because it glues the input components and the transactions to the data store. I have twice in recent years worked on systems where we wanted to change the repository system. In both cases, we had started off with a full-scale Oracle database. This proved complex to manage and provided more capabilities than we needed for our application. So we replaced the data store, in one case with a MySQL database, and the other case merely using the Unix file system. Because we were using this architectural style, we did not have to change any of the input components or the transactions. There are a number of architectural styles that apply to time-critical systems. A time-critical system, often called a real-time system, is a software system whose correct functioning depends upon results being produced within a time window. It's convenient to divide them into two types. A hard real-time system fails if the results are not produced within specific time constraints. For example, a fly-by-wire control system for an aeroplane must respond within specific time limits. There are also some so-called soft real-time systems which are degraded if the results are not produced within required time constraints but continue to work. A network router is a good example. If a network router is overloaded, it can time out or drop a packet, but the network as a whole still continues to work. One architectural style that is used in many time-critical systems is a daemon. A daemon is used when messages arrive at intervals which may not allow time to process them. An example is a web server. The daemon listens at a port 80 usually, and when a message arrives, it immediately spawns a process to handle the message and then returns to listening at port 80. Time-critical systems with distributed data need special techniques also. And the normal technique is to replicate the data in some way. So you hold several copies of the data in different locations. I think you're familiar with the two main techniques. With a mirror, you completely replicate a data set. With a cache, you have a dynamic set of data which you replicate, usually the most recently used data. With replicated data, the biggest problems are concurrency and consistency, and that is an area beyond the scope of this course. If you'd like a really interesting example of a huge system that uses replication to achieve its goals, look at the domain name system. This is the system that takes domain names like cs.cornell.edu and translates them into IP addresses of physical machines. It makes very wide use of mirroring and of caching. For details of the protocol, read the IETF request for comments that's listed here. It's a very readable and interesting document. Here is an old exam question about system architecture. A company that makes sports equipment decides to create a system for selling sports equipment online. The company already has a product database with description, marketing information, and prices of the equipment that it manufactures. To sell equipment online, the company will need to create a customer database and an ordering system for online customers. The plan is to develop the system in two phases. During phase 1, simple versions of the customer database and ordering system will be brought into production. In phase 2, major enhancements will be made to these components. As you read this question, notice the plan to have two phases. The architecture that you use in phase 1 must allow the system to move to phase 2 easily. Here is the first part of the question. For the system architecture of phase 1, draw a UML deployment diagram. A deployment diagram shows the nodes and the components on the nodes. So we have two nodes, a personal computer and a shopping server. The personal computer just has a web browser. The shopping server has the three components described in the question: the ordering system, the product database, and the customer database. Part 2, also for the system architecture of phase 1, draw a UML interface diagram. So we have the same components, but here we're showing the interfaces, not the nodes that the components are on. For part B, also for phase 1, what architectural style would you use for the customer database? And the answer given is the repository with storage access layer. Why is this? Why do you choose this style? Because it allows the database to be replaced without changing the applications that use the database. This is shown in the answer to the final part of the question. Draw a UML diagram for this architectural style, showing its use in the application. Here we see the customer database divided into the storage access and the data store. The expectation is that in phase 2 the data store will be changed, but hopefully the storage access interfaces will not be changed, and so the input components and ordering system will not have to be changed.
End of Lecture 12. Lecture 13, 3 popular architectural styles. Here are 3 examples of widely used system architectures. The first is 50 years old. It's the master file update, which is still widely used in data processing applications. Next, the 3-tier model, which is the basic architecture of many web systems. Finally, Model View Controller, which has become the standard system architecture for mobile apps. Each of these architectures has many variations. In a particular application, you will need to choose the variation that's appropriate for your application.
Our first example is batch processing with master file update. This is very widely used for large data processing systems. Our example will be electricity utility billing for a company like NYSEG here in New York State. Other examples are telephone call recording and billing for companies like Verizon, car rental reservations, banking, and a university-grade registration system such as we use at Cornell.
For the example, we'll look at electricity utility billing. Requirements analysis has been carried out, perhaps using a data flow model, and has identified several transaction types. For example, creating an account or closing an account, reading a meter, receiving payment, other credits and debits, transactions when a check is cleared or a check bounces, queries of an account, corrections of errors, and so forth. Here is a first attempt at a system architecture. Transactions are assumed to come in a single stream, represented here by a postal envelope. Each transaction is processed by a clerk who inputs the data into the system. There is then a master file which is updated and bills and other reports are written. So each transaction is handled as it arrives. So what is wrong with this first attempt? First of all activities are triggered by a transaction. A bill is sent out for each transaction, even if there are several per day, and not on a monthly cycle, which is more typical for an application like this. It's awkward to answer customer queries. There's no process for error checking and correction, and it's inefficient in staff time. We can do better than this. The solution is the architectural style known as batch processing. Groups of transactions are processed together in batches. The first step for each batch is data input, followed by editing and validation. The validation program can read the master file, but cannot change the master file. Any errors are immediately fed back to the data input and corrected before the batch is ready for processing. Here is a deployment diagram showing this validation step. The next stage is to take the validated transactions in their batches and sort them by account. Then we'll have batches of input data ready for updating the master file. The master file will be updated, possibly more errors will be found, in which case there will be new transactions generated to correct them. Reports are generated and bills are generated. So the batch processing architectural style has three parts to it: input and validation, sorting, and master file update. This is a great improvement. All transactions for an account are now being processed together and can be done at appropriate intervals, for example monthly. Backup and recovery have fixed checkpoints. If there's any error, such as a computer failure or a network failure, the system goes back to the last checkpoint and puts in the current batch again. There's much better management control of operations because the management know where each batch is. It's efficient in the use of staff and hardware, and error detection and correction is done systematically. Batch processing with master file update is an efficient way to process batches of transactions. The disadvantage is the information in the master file is not updated immediately. There's no good way to answer customer
inquiries. You may have sometimes had the experience you will call a company asking for information, and they'll tell you that they have the information from yesterday, but they don't have today's records. The architecture needs an extension for online inquiries. Suppose a customer calls the utility and speaks to a customer service representative. The customer service representative must be able to read the master file. This is the standard arrangement. The customer service representative can read the master file, can make annotations, and can create transactions, but cannot change the master file. So if a discussion with a customer leads to a change of the data, the customer service representative creates a new transaction which feeds into the batch updating. Here is the use case. The customer representative has the use case answer customer, and it can spin off a new transaction, but it cannot update the master file. This diagram shows the full batch processing with master file update and customer services. It's an efficient way to answer customer inquiries, but still it has the disadvantage that the master file is not updated immediately. Our next example is the web. We're going to look at how the web has evolved from a very simple basic architecture to the complexity that we have today. And in particular, we're going to look at the very popular three-tier architecture. The basic architecture of the web was a very simple client-server architecture. There was a server that delivered static pages in HTML format, and a client, known as a browser, that rendered those pages. Both the client and the server implement the HTTP interface. The first problem is to extend the architecture of the server so that it can configure HTML pages dynamically and not simply serve static pages. Here's how it's done. The server runs a script, perhaps using the Common Gateway Interface, CGI. It reads data from a separate data store, uses that data to configure web pages, and then presents those pages to the web browser. This has several advantages. The server-side code configures pages which to the web browser just look like static HTML, but the server can access data, validate information, and so forth. This architecture continues to have the disadvantage that all interactions require communication with the server. This is an example of the architectural style known as a three-tier architecture. In the center, there is an application tier. This is a component that talks to a database tier and to a presentation tier. Each of the tiers can be replaced by other components that implement the same interfaces. In the web example, the central component, the application tier, is a web server, and it talks to a database server and a web browser using standard protocols. The components do not have to be on separate computers. For example, the web server and the database server are often on the same physical node. Here, the three-tier architecture is being used for broadcast searching. The user interface service, the application tier, is talking to several databases. This is an example of a multicast protocol, where the user talks to the user interface service, and the user interface service broadcasts a message to the databases. The primary difficulty here is to avoid troubles at one site degrading the entire system. For example, every transaction cannot wait for a system to time out if one of the databases is not operating properly.
Lecture 13, end of Part 1. Lecture 13, Three Popular Architectural Styles, Part 2.
Using the three-tier architecture in this way, the web has a server that delivers dynamic pages in HTML format instead of static pages. The client, known as the browser, still renders HTML pages, and both server and client implement the HTTP interface. This brings us to our next problem. Every interaction with the user requires communication between the client and the server. So the problem is to extend the architecture so that simple user interactions do not need messages to be passed over a network between the client and the server.
The solution is to extend the web so that the server can download executable code to the browser. The executable code will be in a scripting language such as JavaScript.
This has the advantage that the scripts can interact with the user and process information locally. It still has the disadvantage that all interactions are constrained by web protocols.
Many, if not most, large websites use some version of the three-tier architecture. That is, they assume a client that renders HTML pages and executes scripts. They have a server that delivers dynamic pages in HTML format and a data store. Over the past 20 years, however, there have been very many extensions to the web architecture. Here are some of them. Protocols, HTTPS, FTP, proxies, and so forth. Very wide range of data types, with helper applications, plugins, and so forth. Many other versions of executable code, such as applets and servlets, and style sheets, of which CSS is the best known. Most of these are compatible with the three-tier architecture, but some require different architectures altogether. Now for our third main example of a system architecture, the Model View Controller, often abbreviated to MVC. First of all, a warning. The definition of Model View Controller is in a state of flux. The term is used to describe a range of architectures and program designs. Some are system architectures, where the model, view, and controller are separate components. But some of the variants are really program designs, with classes called model, view, and controller. We will look at three variants. The first is an MVC system architecture used in robotics. The second is a general-purpose MVC architecture used for interactive systems such as websites and mobile apps. And the third is Apple's version of MVC, which is a program design intended for mobile apps.
The Model View Controller architectural style has been used for many years for robotics and other control applications. This example is a CS5150 project from several years ago. It shows the control of an unmanned model aircraft. And you can see there are three subsystems. There's a controller that receives instrument readings from the aircraft and sends control signals to the aircraft. There's a model that translates the data received from and sent to the aircraft and has a model of what's happening. How high is the aircraft? Where is it? What's its speed? And so forth. It needs domain knowledge about the aircraft and the flight and data from the controller. Finally, there's a view which displays information about the aircraft to the user on the ground, and the user has a control panel which can be used to send commands to the model and hence to the controller of the aircraft. Many of the standard web development frameworks are based on a model view controller architecture, and this architecture has become the standard for mobile apps. There are many variations, but here is the general concept. Notice that this diagram has three components. Components, as you'll remember, are replaceable binary elements. Therefore, the three components can be implemented separately, and it's possible to replace one component without changing the others. At the top of this diagram is a model. A model records the state of an application. In the bottom left, you see a view. A view represents the state of the application to the user as part of the graphical user interface. And on the bottom right, there's a controller that controls the user's interactions and changes the state of the model accordingly. We'll look at each of these three components separately. The model has two functions. It records the state of the application, and it notifies subscribers when that state changes. As I mentioned, it does not depend upon the controller or the view, and should be entirely independent. To store the state of the application, it will almost certainly maintain data. This data can be in data structures or in databases, but an important part of the model is to keep this data up to date. It responds to instructions from the controller to change the state information, and it notifies subscribers, particularly the view, of events that change the state. It shares some responsibilities with the controller for such activities as the validation of information. The view has a simple task. It's to represent the state of the interface to the user. So it subscribes to the model, which notifies it of events that change the state, but it does not change the state itself. So it renders data from the model for the user interface. It provides editors for properties such as text fields, scroll bars, and so forth. It receives updates from the model, and it sends user input to the controller for subsequent updating of the model. A given model may support a choice of alternative views, and this is very useful when you're implementing a system that has to support a variety of devices. The controller is the part of the user interface that manages user input and navigation within the application. As such, it defines the application behavior. It maps user actions to changes in the state of the model and transmits those states to the model. It interacts with external services via their APIs, and it may be responsible for validation of information. Different frameworks are very different in how they handle the controllers. In particular, there are several ways to divide responsibilities between the model and the controller. For example, data validation and external APIs may be handled by the model, though I prefer to see them handled by the controller. In addition, some frameworks, and Apple is a good example of this, put the controller at the center of the architecture with no direct connection between the model and the view. I mentioned external services. Many mobile apps make use of external services, typically cloud-based services like validation services. And they have to be attached to the architecture through their API. The normal way to do this is that the controller supports the API, but you will find situations in which these services interact directly with the model. Here is Apple's version of the model view controller. Notice that there is no connection between the view and the model. Everything passes through the controller. This leads to a very clean design. All updating is initialized by the controller, whether it's changing the view or updating the model. The view can pass user actions back to the controller, and the model can notify the controller when it receives external changes. But the central logic lies in the controller. This diagram shows the model, view, and controller as components. But in practice, this MVC is a program design or part of a program design, and the model, view, and controller are three classes in the program. When you come to use this in practice, you will find that it is very elegant and that it's very appealing, but there are two major challenges. Typically, each screen in a multi-screen app will have its own controller, and they will share the model. For this reason, and because all communication has to go through the controller, you'll find it is often very easy to put extra methods or extra code into the controller, and the controller gets bigger and bigger and bigger with program code that should be in the model or perhaps in the view.
There are many variants of the common architectural styles. Do not be surprised if you encounter a variant that is different from the one described in this course. This is particularly true with the model view controller style. Several programming frameworks call classes that implement a variant of the style a design pattern. In this course, we distinguish carefully between architectural styles and design patterns. Architectural styles are part of system design. They're defined in terms of subsystems, components, and deployment. Design patterns are part of program design, and we will study them later in the course. They're defined in terms of classes. So don't be surprised if you see the model view controller style referred to either as an architectural style or as a design pattern.
Lecture 13, end of lecture. Lecture 14, security.
This is not a course about security, but security is always important in software development. And in this lecture, I highlight some of the issues. Cornell's Computer Science Department has excellent courses in security, and I hope you'll find the opportunity to take one.
Here is my definition of the goal of security in software development. The security goal is to make sure that the agents, that's the people or external systems who interact with a computer system, its data and its resources, are those that the owner of the system would wish to have such interactions. Security considerations need to be part of the entire software development process, but they have a particularly major impact on the architecture that's chosen. Butler-Lamson gives the following security needs and dangers. The first need is secrecy. There is often need to control who gets to read information. Then there's integrity, control of how information changes or resources are used. Availability, making sure that there is prompt access to the information and resources. And accountability, which is knowing who has had access to resources. He also looks at some of the common dangers. First of all, there's damage to information. This is integrity. There's disruption of service, which is availability. the so-called denial of service attacks, whereby outsiders try to swamp a service so that it's no longer available. Theft of money is always a consideration, and that's part of integrity. Theft of information is related to secrecy, and loss of privacy is related to secrecy. Most security needs can be grouped within this framework. Butler Lamson has a fascinating section on the economics of security. He poses the question, how secure should your system be? The reasoning behind this question is that building secure systems adds cost and time to software development. We actually know how to build very secure systems, but do we always want to spend the money? Good security has got to balance the cost of protection and the risk of loss, which is the cost of recovering from a loss times its probability. When the risk is less than the cost of recovering, it's actually better to accept it as a cost of doing business than to pay for better security. In practice, many companies have discovered that although people complain about inadequate security, they won't actually spend much money and certainly won't sacrifice many features or put up with much inconvenience to improve security. In other words, in practice, organizations will accept lower security than they're prepared to admit in public.
Here's an example of the economics of security. Credit cards. Banks in the United States have traditionally used what I call option A. The card is a plastic card, and all the data, that's the name, the number, the expiration date of the owner of the card, is readable by anybody who has access to the card. A copy of the owner's signature is written on the card. This is a cheap system to implement, but does little to discourage fraud. Banks in Europe have for many years used a much more secure system called chip and pin. Here the card has an embossed security chip, and to use the card, the security chip must be read by a special reader so that the user can type in a confidential 4-digit number. This provides much greater security against fraud, but is more expensive and slightly less convenient than option A. When the banks in the United States wanted a more secure version than option A, they chose a system between option A and B. It's less secure than option B, but it's cheaper to install. This is a trade-off between security and economics. I now want to look at security within an organization. Many security problems are internal, and usually they come from the people who are part of the organization. In any large organization, there are going to be some dishonest and disgruntled employees. Dishonest employees will look for a way to exploit the system. This is particularly true if there's money involved. Disgruntled employees will be malicious. They will try to harm the organization, or they may use the system to harm other people. Remember that security relies on trusted individuals. It relies on system programmers, system administrators, and anybody who has access to privileged information. What if these people are dishonest? Finally, everybody, all people, are intrinsically insecure. And people are careless. They leave computers logged on, they share passwords, and they ignore basic security procedures. When I was at Dartmouth, I discovered that the master password to the financial systems had been shared amongst many, many people who should not have had access to that password.
So you're designing systems and you need security. Let me give you some general guideline. The first thing is make it easy for responsible people to use the system. For example, make security procedures simple. There are some organizations that are so obsessed by wanting to appear secure that they make their systems very difficult to use. I came across an example in a large bank where they had so many security procedures and so many passwords that the only way the employees could get their job done was to have a list of all the passwords taped to every computer. This, of course, destroyed the security system. So if you're making it easy for responsible people to use the system, you clearly want to make it hard for dishonest or careless people to use the system. Training. Train people in responsible behavior. And don't just train them once, train them repeatedly. Test the security thoroughly and repeatedly. Many organizations will have a security officer who runs periodic tests. In particular, after you make changes to the system, make sure you check the security. Finally, if you do have violations of security, make them public, explain what's happened, and punish the people who are responsible for it.
Now let's look at external security problems. All network systems are vulnerable to security breaches by external intruders. Their motives may be financial, they may be malicious, they may be looking for secret or confidential information, or even worse. Modern software is so complex that it's impossible to guarantee that you've eliminated all vulnerabilities. And there are many skilled individuals and organizations, including government organizations, that are continually seeking to discover and exploit new vulnerabilities. Here's a list which I got from Wikipedia of some types of external security vulnerabilities that you must be prepared for. Unauthorized access. If somebody has access to a system, they may be in a position to modify the software, to install listening devices, or to do all sorts of other harm. One of the things they can do is install backdoors. They can bypass authentication so that they can do other things in the future. Methods of overload and other forms of blocking, of which the denial of service attack is well known, are very difficult to defend against. Networks are vulnerable to eavesdropping, and there are a whole range of spoofing, phishing, and other related security problems. There is no way to guarantee security from external intruders, but there's a lot that you can do. Careful software development can make a major difference. So how do you minimize the risk? It begins with system design. The techniques that you have here include secure protocols, authentication, and various barriers to access. Next, programming. Practice defensive programming. Avoid dangerous constructs and be rigorous in your testing. Operating procedures are very important. They include backing up regularly, auditing, and testing for vulnerabilities. Finally, since people are a source of security problems, training and monitoring personnel is essential. In the rest of the lecture, I will talk about these 4 topics. End of Part 1. Lecture 14, Part 2. First of all, the system architecture. A good system architecture can minimize risks in many ways. For example, if you are building a website, you have secure protocols, of which the best known is HTTPS. This eliminates many of the spoofing and eavesdropping problems that come with unsecured transmission over the network. Next, authentication. Authentication is crucial to almost all methods of security, and therefore looking after passwords is very important. You should be absolutely certain that you always encrypt passwords, particularly if you're transmitting them across networks or when you're storing them in your systems. Two-factor authentication is becoming popular, but it has problems with user convenience. Next, barriers. There are various sorts of barriers. I'm going to look at firewalls, but there are also private networks and virtual private networks. The idea here is to separate the secure part of your network from the outside world. Finally, data security. In some systems, this is very, very important. And you have techniques such as encryption of stored data and a whole range of backup systems so that if your data should get damaged or compromised, you can at least recover.
One of the basic security techniques is to place barriers that separate parts of a complex system. In particular, separate potentially insecure parts of a system from crucial parts of a system that must be kept secure. The most extreme way of doing this is to totally isolate components. For example, do not connect certain computers to a network. This is certainly secure, but it makes the computers much less usable. A less strict way of isolating components is to use firewalls. Another alternative is to require authentication to access certain parts of a system. Every barrier imposes restrictions on the permitted use of a system, so it's a trade-off between inconvenience and security. And barriers are most effective when the system can be divided into subsystems with simple barriers. A classic example of getting the barriers in the wrong place was the decision to integrate Internet Explorer into Windows. A browser such as Internet Explorer is intrinsically difficult to make secure, whereas the core operating system of a system like Windows needs to be very secure. By putting the two within the same security boundary, Microsoft ended up with a system that was notorious for being insecure. I mentioned firewalls. Firewalls are a very widely used technique for barriers. The idea is quite simple. You have a computer at the junction of two network segments, typically a public network and a private network managed by the organization. The firewall is simply a computer that inspects every packet that attempts to cross the boundary, and it rejects packets that do not satisfy certain criteria. So an incoming request to open a TCP connection or an unknown packet type will be rejected. Firewalls are often a good trade-off. They provide increased security at a loss of flexibility, but there are inconveniences for users and there is extra system administration. Authentication and authorization are standard techniques for creating barriers. Authentication establishes the identity of an agent. Are you the person you claim to be? There are various ways to do this. One is, what does the agent know? Do you know a password? What does the agent possess? Do you have a smart card? What does the agent have physical access to? For example, the Control-Alt-Delete combination on a keyboard is one that cannot be mimicked in software, and so proves that the agent is physically at that keyboard. And finally, what are the physical properties of the agent? Fingerprints are a good example. Once an agent has been authenticated, authorization establishes what the agent can do. And there are various techniques here, like access control lists or group memberships used with file systems. Here is a model that we used for access to digital content in a digital library. At the top, we have a user and an authentication process. The authentication process not only identified an individual, but identified a role. So the individual might be a student at Cornell University. On the left, you see digital materials, and they have attributes. An attribute might be that this is a journal for which Cornell University has a license to provide access to all authenticated users. In the middle, there's authorization, and this is controlled by policies. So a policy might be that if a person had a certain role, such as being a Cornell student, then they could use the digital materials in certain ways. And on the right, you see the actions that are permitted. If you take a course in security, you will study encryption. The mathematics of encryption are beautiful. It is remarkable that data can be stored and transmitted securely, even when the bits are viewed by unauthorized agents and the algorithms are known. In fact, even the code that implements the algorithms are known. The diagram shows the basic flow. On the left, there is some document X which is not encrypted. The encryption software, in combination with a key, is used to create an encrypted document Y. Decryption reverses the process. The encrypted document Y is converted back to its original form X. The algorithms are public. The security lies in the keys, and you will study private keys and public keys and methods of key management. You will also study digital signatures that are used to authenticate that a document comes from the source that it claims to come from. Now let's turn to programming. The software development challenge has two parts. The first is to develop secure and reliable components. The second is to protect the whole system so that security problems in parts of it do not spread to the entire system. Any large system will have many agents and components. Each is potentially unreliable and insecure. And in particular, components acquired from third parties may have unknown security problems. This leads to the commercial off-the-shelf problem. Consider the incentives that developers of off-the-shelf software have. They have considerable incentives to supply software that has many options and features. But in developing such software rapidly, they have fewer incentives to be thorough about security. I would like to recommend two websites about programming secure software. The first is from the MITRE organization. It's about programs that interface with the outside world, such as websites and mail servers. These are particularly vulnerable to intrusion because they have to accept all sorts of data that comes across the networks. The site lists 25 top programming errors and arranges them into groups such as insecure interaction between components,
risky resource management, and porous defenses. The overall conclusion is to emphasize that project management and test procedures have got to ensure that programs avoid these errors and the risky constructs.
The second website is from the SAND Security Institute, which teaches essential skills for secure programming and focuses on Java. Here are a list of some of the problems that they very frequently see. Once again, I suggest you look at the website.
Now let's turn to operating procedures. The operating procedures must anticipate security problems. In any organization, it's important that some member of staff, preferably a senior member of staff, has responsibility for overall security. Here are some of the things that person might think about. First of all, equipment. All system software should be kept up to date with latest security patches. All systems should run up-to-date virus checking software. And rules about passwords, personal equipment, and non-standard software should be explicit. The security person should run routine checks, should run network security tests regularly, and should run password checkers. When I was at Carnegie Mellon, every summer we would give a group of talented students the charge of seeing if they could crack all the passwords on the university systems. They always managed to break a lot of them. Finally, training. Training is a very important part of security. And it's important to keep the staff informed about security. Don't just train the staff, consult them. Ask their advice about how to make the systems more secure and more convenient for them to use. Sooner or later, every system fails. This can be because of hardware problems, software problems, operational mistakes, or security problems, as we've discussed in this lecture. The operating procedures must anticipate this. They must anticipate loss of data and damage to the systems, which can happen at any moment. Here are some of the techniques. First of all, at regular intervals, checkpoint the system. At regular intervals, back up all the data. Keep full audit trails of all important transactions. And then have recovery software. Know how you will recover from a major disaster. Recovery software is complex. It needs to be tested regularly in realistic situations. If you have the opportunity, it's a good practice to rebuild the entire system, including loading the databases completely from scratch. But this is not always possible with large collections of data. You have to do the best that you can. To conclude, you can never guarantee that a system is completely secure. But as software developers, you can do a great deal to minimize the risks and to be able to recover from problems. Lecture 14, end of lecture. Lecture 15, performance.
This lecture is about performance. Performance is a factor that you need to consider throughout the software development process, but it particularly affects system design and program design. As usual, we start with economics. In most computer systems, the cost of people is much greater than the cost of hardware, and usually your design will emphasize ways to use people efficiently. But performance is very important. A single bottleneck can slow down an entire system, and future loads may be much greater than predicted. There are some types of system where performance always matters. Real-time systems are an example. Here the computation must be fast enough to support the service provided. For example, fly-by-wire control systems in aeroplanes have type-to-response time requirements. Very large computations may stress the performance of even supercomputers. Elapsed time may be measured in days. For example, if you're calculating weather forecasts, your calculations must be fast enough for the forecasts to be useful. User interfaces also require high performance because humans have high expectations. We expect almost instantaneous response, and some operations such as mouse tracking must appear instantaneously. Then there are transaction processing systems where staff need to be productive and customers not annoyed by delays. An example is an airline check-in system. A few words about high-performance computing. Some of today's best-known computer systems require very high-performance computing. Amazon's large collection of data and very high volume of transactions make it one of the biggest computer systems in the world. Google, with its huge numbers of users, sophisticated algorithms and very good response time, has enormous computing facilities. I've already mentioned weather forecasting. Basically, the ability to forecast weather accurately is constrained almost entirely by the computing resources available. Even with these systems, however, we must balance the cost of hardware against cost of software development. Some types of configuration are very difficult to program and debug, and it's important to isolate application programmers from the system complexities. Most of the people who are writing code for Google or Amazon do not need to be aware of the high performance aspects of their systems. There is a very interesting computer science course at Cornell. It's 5300 Architecture of Large-Scale Information Systems. Personally, I find this a fascinating area. Here are the performance challenges for all software systems. The first task is to predict the performance problems before a system is implemented. When I started work, the very first job I had was doing mathematical calculations to predict the performance of large transaction processing systems, and it's an area that has always fascinated me. The next task is to design and build a system that's not vulnerable to performance problems. Sometimes this will be straightforward. You know that you have plenty of hardware capacity, but other times it may be quite tricky. Finally, when you have a system, you may find that there are problems, and so you've got to identify the causes and fix problems after a system is implemented. The basic technique for addressing these performance challenges begins with an understanding of the underlying hardware and network components and how they interact with the software. In a complex system, this is not an easy task. Even the people who've developed the system software may have only a hazy understanding of what is actually happening at a hardware level. Then, divide your system or your planned system into subsystems, and for each subsystem separately, calculate the capacity and the load. The capacity will typically be a combination of the hardware and software architecture. Then you look at the subsystems that are near peak capacity. These are likely to be your problem areas. For example, you might have calculated the capacity of a search system is 1,000 searches per second. You now look at the anticipated peak demand. If you don't see the demand going over 10 searches per second, you know that you have plenty of capacity. But if your peak demand is likely to approach the capacity, then you have to be very careful. The next thing you need to do is look at interactions, particularly interactions between hardware and software. So in a distributed system, what messages pass between the nodes? How many messages are passed for each transaction? Disk reading is often a bottleneck. How many times must the system read from the disk for each transaction? What buffering and caching is being used? Which operations are in parallel and which have to be sequential? Are other systems competing for a shared resource? For example, are you sharing a network or a server farm with other applications? And given that there's going to be competition for resources, how does the operating system schedule tasks and how are your tasks going to be affected? You now start looking for bottlenecks. Usually CPU performance is not the limiting factor, but we'll come back to that. Here are typical hardware bottlenecks: reading data from disk, shortage of memory, including paging, moving data from memory to the CPU, network capacity. Any one of these can slow down an entire system. Then you have your software bottlenecks. You have algorithms that do not scale well. This is very common in a legacy system. It will be implemented with an algorithm that does fine on a small scale but doesn't scale well. And then you have software that does things sequentially where you could be using parallel processing. CPU performance is a limiting constraint in certain domains. For example, large-scale data analysis, some aspects of search algorithms, mathematical computation such as engineering, compression, encryption, multimedia, for example, video format conversions, perception such as image processing. You'll notice that some of the most interesting parts of modern computing are on this list. The performance of different hardware components varies tremendously. Here are some examples. Notice the huge difference between the CPU performance and the disk latency, the time it takes for a disk to begin reading. Again, networks may have theoretical performances of a gigabit, but whether they can actually reach that performance depends upon circumstances, and you may find that the actual performance is much less than the theoretical peak. If you suspect that some part of a system might be a bottleneck, the first thing to do is to calculate the utilization. The utilization is the proportion of the capacity of a service that is used on average, and the service could be hardware or software. So utilization is the mean service time for a transaction divided by the mean inter-arrival time of transactions. As a useful rule of thumb, if the utilization of any hardware component exceeds about 0.3, you've got to be prepared for congestion, because peak loads and temporary increases in demand can be much greater than the average. There are three main methods for predicting system performance before you build a complete system. The first is direct measurement on a subsystem or a prototype. This is often called a benchmark. The next are mathematical models from queuing theory, and the third is simulation of part of the system. All these methods require detailed understanding of the interaction between software and hardware systems, and in particular, you need very good understanding of how each subsystem affects the overall system performance. First, mathematical models. Much of the early work in queuing theory was by Erlang, who modeled congestion in the Danish telephone network. Following his work, we know how to make good estimates of congestion for single server queues, so long as we can make some assumptions about the distributions of arrival and service time. In particular, most of the theory works with arrivals that are independent random events, Poisson processes. Again, service times that follow certain families of distributions are particularly easy to do the mathematics. The distributions normally studied are negative exponential and gamma distributions. Many of the results can be extended to multi-server queues, and many of the results can be used cautiously, even if the arrival and service time distributions do not follow these simple formulae. Here is a single server queue. On the left, transactions are arriving. They wait in line, they receive a service, and they depart. An example might be requests to read from a disk with no buffering or other optimization, or in a physical situation, customers waiting for check-in at an airport with a single check-in desk. Here is a multi-server queue. As before, transactions arrive on the left. They wait in line, but now there are several servers, and each transaction is processed by the first one to become available. An example might be tasks being processed on a computer with several processors, or customers waiting for check-in at an airport when there are several check-in desks. Most systems are too complex to be modeled exactly by queuing theory. You either have to make some very broad simplifying assumptions or use another technique. And the normal technique to use is simulation. A simulation builds a computer program that models the system as a set of states and events. The inner loop is below. You advance the simulated time, you determine which events have occurred, and you update the state and event list. In a discrete time simulation, you advance the time in fixed steps, perhaps 1 millisecond, whereas in the next event simulation, time is advanced to the next event. The events can be simulated by random variables, arrival of the next customer, completion of a disk latency or so forth, or by using data which has been collected from an operational system. Simulation is a time-consuming and expensive way to model a system, but in some situations, it's the only way to get good information. In queuing theory, and with simulation of queues, it's normal to plot the mean delay before service begins against the utilization of a service. So the utilization runs from 0 to 1. Almost every time you do this, you get a curve shaped like this diagram. The exact shape of the curve depends upon the type of queue, whether it's a single server, and the statistical distributions of arrival times and service times. But notice that when the utilization is low, the mean delay before service begins is low, and for the utilization less than a quarter or a half, the mean delays are quite small. Then as the utilization builds up, the mean delays increase very rapidly. This is the reason I give the rule of thumb of utilization of 0.3 as being the level at which you start getting worried about delays.
End of Part 1. Lecture 15, Performance, Part 2.
If you have an operational subsystem or a prototype, you can experiment with the performance using a simulated load. The basic technique is a benchmark. You run the system on a standard problem set with sample input or with a simulated load on the system, and then you use instrumentation to clock specific events. The following example is from our web laboratory. This is actual results from a student MEng project. We were loading a very large amount of web data onto a symmetric multiprocessor which had 8 CPUs. And the question was, what was the optimum configuration? So here we see the throughput in megabytes per second plotted against the number of CPUs. The white boxes are the average throughput per CPU, and the grey boxes are the total throughput over the entire system. As you would expect, as the number of CPUs goes up, because of interference between the processes running on the various machines, and in particular the use of the disk farm, the actual average throughput per CPU goes down. What is interesting, however, as the number of CPUs goes from 1 to 2 to 4, the total throughput goes up, as you might expect. But once it goes past 4, the total throughput actually goes down. The congestion, the interference between the various processes slows down the overall performance of the system. Here's a case study from my own experience. In configuring a disk farm, how many disks should be placed on each I/O channel? When many transactions use a disk farm, each transaction goes through a set of hardware and software steps. Here is the list for this particular farm. You wait for a specific disk, you wait for a channel, you send a signal, you wait for this I/O channel, you pause for latency, and you read the data. We actually studied this from 3 points of view. First of all, we did the mathematical estimation from queuing theory. We did a simulation. And finally, we actually did direct measurement on an operational system. We were pleased to find that the 3 approaches gave very similar results, within about 15%. Sooner or later, you're going to have to fix a system which has bad performance. Sometimes the system will perform badly when it first goes live. Sometimes the system that has been running well will slow down for no apparent reason. If a system performs badly, you've got to begin by identifying the cause. Instrumentation is your first thing to do. You can add timers to the code, and often this will reveal that delays are centered in a specific part of a system. Try running the system with test loads. For example, try very high transaction rates, try very large input files or very many users. This may reveal the characteristics of when the system runs badly. Then go back and review the design and the code. We're going to talk about reviews later, but the idea here is to have a team review the system design and the program design and suspect sections of the code. With many team members looking at it, they may see things that one individual has missed. You may find an algorithm that's running very slowly, for example a sort or a locking procedure, or you may find just a simple coding problem is the root of the problem. The important thing is you've got to find the underlying cause and fix it, or the problem will return a few weeks or a few months later. A major system may be in production for 5 years, 10 years, even 20 years. And during this time, hardware is going to change a lot. So how do we predict the impact that performance change is going to have on your computer system? Well, we start off with Moore's law. This is named after Gordon Moore of Intel, who in 1965, a long time ago, observed that the density of transistors in an integrated circuit is doubling every year. A more modern version of his law is that the cost performance of silicon chips doubles every 18 months. We can argue about the 18 months, but the general principle is right. Moore's law is only approximate, but here are some rules of thumb that you can use for planning assumptions. Assume that the cost performance of silicon chips improves 30% per year. So in 12 years, the cost performance will improve by 20 to 1, and in 24 years it will improve by 500 to 1. Magnetic media, historically the cost performance has improved rather more rapidly, perhaps 40% per year, which in 12 years is an improvement of 50 to 1, and in 24 years 3,000 to 1. Historically, these assumptions have been conservative. During some periods, the increases have been considerably faster even than these numbers. Recently, the rate of performance increases in individual components, such as CPUs, has slowed down, but the overall rate of increase has been maintained by placing many CPU cores on a single chip. What does this mean for system design? Suppose you're doing a feasibility study in 2013. For a large system, it probably will not be in production use until about 2016, and assume that it's withdrawn from production 10 years later. This chart gives some estimates of how the processor speeds, memory sizes, and disk capacity will improve over that period. Notice the system cost. By the time the system is withdrawn from service, the hardware costs will be about 3% of the costs while you were doing the feasibility study. From this, you might think that hardware costs are going to be so low that you can ignore them. But we need to think again. Perhaps this will be a typical laptop 10 years from now. The processing power, the memory, the disk, the network capacity will all be much, much greater than we have today. Surely there will be some fundamental changes in how this power is packaged and used. And this has been the historic experience. Whenever the computers have got more powerful, people have found interesting and valuable ways to use this extra capacity. There is another law known as Parkinson's law. The original version was that work expands to fill the time available. He was particularly talking about bureaucracies. But there's a software development version. Demand will expand to use all the hardware available. Low prices will create new demands, and therefore you have to assume that your software will be used on equipment that you have not envisaged. Nobody can predict the computer systems of the future, but you can be careful about the assumptions that you make. Here are some past assumptions that caused problems. Unix file systems will never exceed 2 to the 32 bytes, that's 2 gigabytes. Apple took networks, used 8-bit addressing on the assumption that no network will ever have more than 256 computers. GPS software was assumed that it would last no more than 1,024 weeks. And 2 bytes were used to represent a year, so 1978 was represented by the number 78 on the assumption that no software was going to last very long. Finally, here's something you might think about for the long term. Since 1965, the performance of hardware and the costs have improved exponentially. They seem to be going up and up and up forever. But eventually, this curve has got to turn down. At some stage, we will stop seeing these improvements. When will this be? I don't know. Will it be within my working life? Probably not. Will it be within your working life? It probably will be. At some stage, we're going to stop getting this advantage of ever improving hardware at lower costs.
Lecture 15, end of lecture. Lecture 16, Models for Program Design. We now want to look at program design in particular object-oriented program design. Some people like to keep program design and coding completely separate. That's the theme of this lecture: program design using models such as UML, diagrams and specifications. The next lecture looks at an alternative approach, using modern development tools to combine program design and coding. This works well with the agile style of development.
The task of program design is to take the software architecture and to represent it in a way that can be implemented as one or more executable programs. So given a system architecture, the program design specifies the programs, components, packages, classes, class hierarchies, etc. Interfaces and protocols, where not part of the system architecture, and the algorithms, data structures, security mechanisms, operational procedures that are going to be used. If you do the program design properly, all the important design decisions are made before the implementation. Implementation should focus on the actual coding. Though of course in practice, as you start coding, you will find ways to improve the program design, or you'll find areas that have not been addressed. UML provides models that can be used for almost all aspects of program design. Typically, you use the diagrams to give a general overview of the design, showing the principal elements and how they relate to each other, and the specifications provide the details about each element of the design. The specification should have sufficient detail that they can be used to write code from, and the level of detail will depend upon the experience of the programming staff. In heavyweight software development processes, the goal is that the entire specification is completed before coding begins. In lightweight software development processes, you start with an outline specification made before coding, but you complete the details as part of the coding process, often using language-based tools such as Java docs. I think it's fair to say that nowadays it's very rare to use the full heavyweight software development process. Almost always people add to the specification while they're doing the implementation. Here is a list of UML models and when you might use them. The first model we looked at were use case diagrams, and they're used mainly for requirements. They show a set of use cases and actors and their relationships. For system architecture, we looked at two models: the component diagram, which shows the organization and dependencies among components, and the deployment diagram, which shows the configuration of processing nodes and the components that live on them. We're about to look at two models that are used mainly for program design: class diagrams and object diagrams. Here is how we draw class diagrams. There are 4 boxes. The top one has the name of the class, which always begins with a capital letter. The next has the local instance and class variables, which in UML are called attributes. Then we have the methods, and finally there is an optional box for text describing the responsibilities, what the class does. Notice that I use the term methods to describe the operations that a class supports. This is the normal term used in programming, but UML uses a less familiar term, operations, for this purpose. So in this class, where you see the word methods or the word operations, they are referring to the same thing. Here is an example from Buch, Rumbaugh and Jacobson. It's a Java applet that paints the phrase "Hello World" on the screen. There is a class called Hello World which extends the standard applet class. It has a single method, paint, which uses an instance of the graphics class. And what it does is it draws the string hello world on the screen. So let's start with our class diagram. Here we have just the three top boxes. We haven't got a responsibilities box. We've got the name, hello world, and a method, paint. Here we have an annotation. So the method paint has extra information which shows how it's going to be implemented. Annotations are notes that can be used almost anywhere in the UML model. Next, we look at relationships between classes. There are three, each with its own distinctive type of arrow. A dependency is a semantic relationship between two things in which change to one may affect the semantics of the other. A generalization is a relationship in which objects of the specialized element, called a child, are substitutable for objects of the generalized element parent. I will often use the term parent-child relationship. A realization is a semantic relationship between classifiers wherein one classifier specifies a contract that another classifier guarantees to carry out. We will see examples of all three types of relationship. First, let's look at our Hello World class. The Hello World class is a child of the applet class, so we have the generalization relationship. And it depends upon the graphics class. Notice in this diagram we've shown a simplified notation for the applet and graphics classes. The diagrams are showed as elided, just the name of the class, not the attributes or operations. An association is a relationship that describes links, and a link is a connection among objects. Notice there are counts on this. So here is a relationship. You could imagine a parking lot that has a large number of parking spaces. So the parking lot class is associated with the parking space class according to this relationship. In an earlier lecture, I recommended rational rows as a system that can be used to create UML models, both designed and specifications, to store them and lead into the implementation. Rational rows is particularly good for managing class diagrams and specifications. Here is a typical class diagram. You can see it's very similar to the diagrams we've just been looking at. Here is an associated specification. The specification is language dependent, in this case Java, and you see the specification has two parts to it. There's the class information and there's the Java doc information. So in building your model, you're also preparing for your implementation and subsequent documentation. In a big program for a real-life system, deciding what classes to use is the most difficult part of program design. Get it right, and the program will go together smoothly. The first step is to identify possible classes, candidate classes, that represent the system design. In doing this, a good place to start is with the terms that the users and implementers use to describe the system. These terms are candidates for classes. So come up with your list of candidates for classes and ask some questions about them. Is each candidate class crystally defined? For each class, what is its sense of responsibilities? Are the responsibilities evenly balanced among the classes? You don't want one huge class and lots of little classes. Then you can say what attributes and methods does each class need to carry out its responsibilities. The next step is to look at your list of candidate classes and to modify them. So what you're trying to do is you're trying to improve the clarity of the design. If the purpose of each class is clear, with easily understood methods and relationships, developers are likely to write simple code, and moreover, future maintainers will understand the code and can modify it. So you're looking to have coherence within classes and weak coupling between them. A good design will often be a combination of two types of classes: application classes and solution classes. Application classes represent concepts from the application. They're the sorts of terminology you will find in the requirements. We're about to look at a technique called noun identification, which is useful in generating candidate applications classes. Solutions classes are system concepts. They're things like user interface objects, databases, and so forth. These are not part of the requirement terminology, but they're fundamental to the implementation.
End of Part 1. Lecture 16, Models for Program Design, Part 2.
Here is an example of how you use noun identification to identify candidate classes. You start with a simple 1 or 2 paragraph description of the program. So, I'll read it out. The library contains books and journals. It may have several copies of a given book. Some of the books are reserved for short-term loans only. All others may be borrowed by any library member for 3 weeks. Members of the library can normally borrow up to 6 items at a time, but members of staff may borrow up to 12 items at one time. Only members of staff may borrow journals. The system must keep track of when books and journals are borrowed and returned and enforce the rules. Now go through the description and mark every noun or noun phrase. Here they are marked in red. These nouns and noun phrases are our first candidate classes. Here they are with some comments. First of all, the noun library is the name of the system, and therefore it's not a good candidate. The next 3 nouns, book, journal, and copy, do seem to be good candidates. Short-term loan is an event, and probably it's not going to be a candidate class. Library member is a good candidate. Week is a measure which we're probably not going to use as a class. Member of library is just a repeat of library member, and so on. Notice near the bottom, system and rule are general terms, and those are typically not good candidate classes. Next, we look at relationships between these classes. So we see a book is an item and a journal is an item. This makes us ask the question, do we actually need item class as well as book and journal class? We see a copy is a copy of a book, and a member of staff is a library member. We don't have any relationships involving item apart from those involving book and journal. Now let's look at some of the methods we might need. We know that a library member can borrow a copy and a library member can return a copy. So a member of staff can borrow a journal and a member of staff can return a journal. It appears that we don't need the item class. Now we try a possible class diagram. Here it is. It's certainly not the only class diagram we could think of, but this seems to represent the description that we have, and therefore we can use it as our starting point for our program design. Now we have a set of candidate classes and a possible design. We want to move to the completed design. Don't be surprised if this takes quite a long time and a lot of experimentation. Here are some of the methods you might use. First of all, reuse. Wherever possible, use existing components or class libraries. They may need extensions, but they save you from having to write new code. Restructuring. Can you change the design to improve the understandability or the maintainability? The two basic techniques here are to merge similar classes or to split complex classes. Optimization. You may need to change the design to meet the performance requirements, so you may need different algorithms or a different structure. And finally, completion. It's quite normal at an early stage in the design to leave gaps, but eventually you've got to fill all the gaps and specify all the interfaces. Remember that design is iterative. As the process goes from preliminary design to specification to implementation and testing, you will often find weaknesses in the design, so be prepared to make major modifications. Some programs can be modeled entirely with class models, but more often you will need to model the dynamic aspects of a system or a program. And for this we use various types of interaction diagram. They show sets of objects and the relationships, including the messages that are dispatched amongst them. We're going to look at the UML sequence diagrams, which show the time ordering of messages. But before doing that, here is an informal model that I find very useful at a preliminary stage of a diagram. It's used for client and server interactions. Here, for example, is the execution of an HTTP GET command. If you think about what's involved in executing such a command, there's clearly a client and a number of servers. And the interactions are going to go through three phases. First of all, there's the domain name service, to take the domain name and turn it into an IP address. Then there needs to be a TCP connection established, and then the HTTP GET is carried out. In this diagram, time runs downwards, and the line shows the messages and the responses that have to be carried over a network. A model like this is particularly useful for anticipating performance problems before you get down to actual development. Sequence diagrams in UML need notation for objects. So here side by side are the notations for classes and for objects. A class has a name that begins with a capital letter. An object has a name that begins with a lowercase letter. And the class that it belongs to is indicated by a colon. The names of objects are always underlined. So an object colon any class shows the name of an object and its class. Alternatively, colon any class is any object of that class, or we can simply write an object. The principal interaction between objects is a message, and it's shown with this simple arrow. Here are some more actions on objects. Call is indicated by having the type of message with its parameters in parentheses, and local calls we show the message arrow doubling back on itself. A return, the arrow is a pect line. Asynchronous symbols, we use this half arrow ahead, and they're special stereotypes to create and destroy objects. To end this lecture, here are 3 sequence diagrams. In each of these diagrams, time runs downwards, and for each object there is a box that shows when it's created and when it's destroyed. So here we have our library example, and the objects are a library member, an object of class copy, and an object of class book. The book borrower sends a message, which is the form of a call to borrow. There's a check that it's okay to borrow, and then we have the borrowing, which is done by a message to the copy, and then from there a message to the book. Here's a different example showing the creation and destroying of objects. Imagine that there is a MEng student who is, we're calling here as an actor called a Cornellian, and this MEng student transfers to the PhD student. In our program, we will want to delete the record for the MEng student and create a record for a PhD student. And this is how it's done. Notice that we've added sequence numbers to the messages to clarify the diagram when we start writing the specification. Finally, here's a sequence diagram for the painting mechanism used by our Hello World class. So an object of that class, which we're calling target, relies upon various objects that form part of the Java runtime environment. Here they are, and here are the messages that are passed among them. Lecture 16, End of Lecture. Lecture 17, Program Development.
This lecture is about some of the tools that are available to help you with program development. They include integrated development environments such as Eclipse and application frameworks such as Django. Some tools, such as Apple's Xcode, combine features of both. These tools are so powerful that it is tempting to skip the program design and go straight to coding. But take care.
The basic software development requires only a text editor, such as the VI editor traditionally used for Linux, compiler for individual files, and some way to build the system, such as Make for Linux. In practice, however, we're all of us more productive if we use an integrated development environment. The typical development environment has a source code editor that understands the syntax of the language we're using, an incremental compiler that can check some of the semantics as we go along, tools to automate the build process, and a debugger. Many of the integrated development environments have many more facilities, but these are the basic ones. Here, for example, is Eclipse. This shows a program written by a student for the Cornell Web Lab. In the center, you see the source code of the program. On the left, there's a panel which shows how that program fits into the project. At the bottom, there is a panel with errors and warnings. And on the right, there's a choice of panels. Here we have a task list and an outline of the program. Eclipse is typical of a modern integrated development environment. It was originally created by IBM's Rational Division, but has been open source for a long time. There are versions for many languages, including Java, C and C++, Python, and so on. As an example, the Java system provides a source code editor, a debugger, an incremental compiler, program documentation, build automation tools, version control, XML editor and tools, and web development tools. It has a plug-in architecture, and there are many, many more facilities available via plugins. Development environments such as Eclipse are tremendously useful, but they provide little help in designing a program. They assume that you already have a design, that you've chosen the classes, the methods, the data structures, and interfaces. So what are your options for program design? We've already looked at program design using modeling tools such as UML. The idea here is that you do a complete design before you start coding. As an alternative, and for simple programs this sometimes works well, you can design while you're coding. You start off with a simple design, you write code, and you redesign as you go along. This can be done entirely within the development environment. Another alternative is to base your program on an existing framework. Here, the bulk of the design has been done for you, and all you have to do is to extend it. Finally, there are advanced environments that combine frameworks with development tools, and you can work entirely within these advanced environments. These four options are not necessarily alternatives, and in a large program, you may use aspects of several of them. First, we will look at how you can do small programs working entirely within the development environment. Here, what you do is you create an outline of the class structure and interfaces. With a simple program, you may even do this in your head. You then start writing code. And as you write the code, you may find you want to make changes, so you modify the structure as needed and rework the code as necessary. This is only possible with small teams with close communication. The maximum size of program that you can do in this informal way depends upon the experience of programmers and the complexity of the program. Experienced people can write remarkably good programs this way, but they cannot write big programs. As a rule of thumb, I would say it may be possible to complete a single agile sprint like this, but no more. Eventually, the problem with this approach is the amount of rework becomes overwhelming, and you need something more systematic. One of the more difficult parts of program design is getting the class hierarchies right. This is one of several reasons why it's good practice to use existing frameworks wherever possible. An existing framework will have already designed the class hierarchies, and many of the classes will have been written for you, or abstract classes are provided that you can use as a basis for your own subclasses. Here are some examples. Almost every modern programming language provides a rich set of class hierarchies. There are toolkits, for example, for graphical user interfaces, that are intended to extend the classes that are part of the programming languages. In a future lecture, we will look at design patterns. Now we want to look briefly at frameworks for web development and for developing mobile apps. As an example of a programming language, consider Java. Java is actually a relatively straightforward language, but it has a very rich set of class hierarchies, and Java programs derive much of their functionality from standard classes. Learning and understanding the classes is difficult, but once you do learn them and become an experienced Java programmer, you can write complex systems quickly. Conversely, inexperienced Java programmers often don't fully understand the hierarchies, and this leads to inelegant and buggy programs. Unfortunately, languages such as Java and Python are steadily changing their class hierarchies over time. Very often, the changes are to replace special purpose functionality with more general frameworks. And these more general frameworks are not always very easy to understand. If you design your programs to use the class hierarchies in the style intended by the language developers, it will help with the long-term maintenance. Probably, your classes will still fit together well even when the language changes over the years. If you're building a simple website, such as the CS5150 website, you don't need a complicated framework. But if you're building any more advanced website, I strongly recommend that you use one of the existing web development frameworks. They provide a skeleton for building complex web applications. Probably the first was Cold Fusion, which implements a 3-tier architecture and is still used today. But more modern examples, such as Ruby on Rails and Django, more often use a model view controller architecture. As an example, Ruby on Rails provides a database, a web server, web pages, and many tools to be used with them. It's intended to be used with web standards such as XML, HTML, CSS, and JavaScript. Many recent CS5150 projects have used Django. Django is a Python framework for developing websites. It's written in Python, and the code that you have to write is all in Python. So you take the framework that's provided and you add extra Python code to make it into your website. It's loosely based on an MVC architecture, though it has its own version. It supports a variety of web and database servers. It uses what they call web templates as a fundamental design concept. It provides authentication system for you. It provides an administrative interface, and it comes automatically with software designed to mitigate security attacks on the web. Projects that have worked with Django report that it's a complex framework. It takes a lot of time to learn, and if you're one of the teams that use it, you should allow plenty of time for learning. However, once the teams have learned Django, they produce good websites, and I've seen a lot of good projects using this framework. Many application frameworks can be used with any program development environment. For example, Django is simply Python code, and you can use Eclipse to develop your website. More advanced development environments combine these two functions. So you'll have an integrated development environment and an application framework which are combined in some way. They may have other tools such as a user interface layout manager and may have very sophisticated facilities designed for a specific area of applications. A good example is Apple's Xcode, the version that's used to develop mobile apps under iOS. This slide shows Apple's Xcode being used to develop a mobile app. This is actually a simple app that I wrote to manage my own photographs. It has many panels, and in practice you would not use as many panels at the same time. On the left, there is a panel with the resources used by the application. Next to it is the place where you design the layout of the various screens. And beside that is the code that implements that graphical layout. On the right, there are attributes of some of the visual elements, and at the bottom there's a menu giving the choice of widgets. An advanced development environment is intended to provide everything that a developer needs. But in return, the developer is given little choice. The developer is expected to follow the program design and frameworks that are provided. For example, when Xcode is used with iOS, it has a very specific purpose: mobile apps for Apple devices such as iPhones and iPads. The programmer is expected to use the programming languages provided, which are Swift or Objective-C, and to work within Apple's version of the MVC framework. If the programmer accepts this overall design assumptions, Xcode is extremely powerful. It provides auto layout of graphical interfaces which are designed to be flexible for a variety of devices. It has a comprehensive set of classes for user interfaces and navigation, and provides excellent simulator for all Apple devices. Development frameworks such as Django and Xcode are powerful and flexible. If your application fits the framework, they do much of the program design for you, and they provide high-quality code for many of the standard parts of any application. Some parts of the application will almost certainly have to be designed and implemented separately, but many of the most difficult parts will have already been done for you. But beware, there are disadvantages. You are forced to build your application within the framework that's provided. Once you choose a framework, the structure of your program is designed for you. As I mentioned earlier with programming languages, the frameworks are continually modified, which may be a problem for long-term maintenance. And finally, these frameworks are complex. They take a long time to learn, and you need to allow lots of time in your schedule for learning and getting up to speed. I want to say a few words about production programming. There is a big difference between a good, well-tested program in an academic setting and what is needed in a production environment. The starting point is Murphy's Law. If anything can go wrong, it will sooner or later. Here are some of the challenges. The code has to be maintained over the long term, with different compilers, different system software, and different people doing the work. All the interfaces between classes and components will be used in new and unexpected ways. Every possible external error will eventually occur, often at the worst possible time. This might be bad data, failures of hardware, or failures of system software. And finally, you must be prepared for security attacks against your programs. What is involved in writing robust programs? Perhaps the most important thing is to write simple code. Avoid risky programming constructs, and if your code is difficult to read, rewrite it. If it's hard for you to read now, it'll be much harder for future maintainers. Incorporate redundant code to check system state after modifications, and test implicit assumptions explicitly. For example, do not assume that all parameters received from other routines are actually valid. You should eliminate all warnings from source code, and you should have a thorough set of test cases for all your code. Overall, you must expect to spend more time writing each section of code and testing it than you have done in the past. Lecture 17, End of Lecture. Lecture 18, Reuse and Design Patterns.
Software is expensive. Therefore, most systems make extensive use of existing code. Avoid writing new code if there is something good that will do the job for you. When you design a program, it may be worth taking extra time and effort to make it easy to modify in the future. Design patterns are standard program designs that are intended to be extensible and modified in the future. They make extensive use of inheritance and abstract classes. This lecture ends with an important topic: legacy systems. How do you build new code on top of old systems?
Reusing existing components can often lead to better software at lower cost. Here are some of the potential benefits. Reusing software often reduces the development time and the cost. If you can reuse mature components which have been thoroughly tested in the field, you're likely to improve the reliability. Finally, if many programs use the same code, maintenance costs can be reduced. But there are also disadvantages. Perhaps the biggest challenge is finding appropriate components and really being sure that they are appropriate. The components may be a poor fit for the application, and you may not discover this until you're quite far advanced in development. Again, with components that you get from third parties, you may not know the quality control and the security that was used in their development. Software from well-established developers or good companies is likely to be well written and tested, but it will still have bugs and security weaknesses, and these are most likely to appear if you use the software in unusual applications. In another lecture, I will talk about some major bugs that I have encountered in my career. In almost every case, the software was being used in slightly unusual circumstances where it had not been as thoroughly tested as one might hope. Overall, software is likely to be much better when it comes from an established developer than a new development team would write. But sometimes it's sensible to write code for a narrowly defined purpose rather than use general-purpose software. Big general-purpose frameworks get very complicated. If you only have a simple application, it may be better to write it from scratch. Maintenance is an important factor when you're using software from third parties. When you're evaluating it, whether it's commercial or open source, pay attention to maintenance. Is the software supported by an organization that will continue maintenance over the long term? You might also ask the question, what are you likely to have to pay for the maintenance? This could be a major factor. Open source software is often a good alternative to writing your own software, but open source software varies enormously in quality. The best systems, and I've listed here Linux, Apache, Python, Lucene, and so forth, tend to be very robust and free from problems. Because of the process for reporting and fixing problems, they are often better than commercial equivalents. There are also some excellent experimental systems. The Hadoop distributed file system is an example, which will have very solid cores, but you may find that the lesser used features have not been subject to the rigorous quality control of the best software products. Then there is an enormous quantity of open source software that is of very poor quality and should not be incorporated in production systems. You're going to have to use your own judgment and decide whether to use the software or not. For larger organizations, applications packages for business functions are provided by companies such as SAP and Oracle. These packages provide enormous capabilities, and they relieve an organization from major tasks such as updating financial systems when laws change. However, they are very expensive. If you commit your company to one of these packages, you're going to be paying license fees to the vendor, modifications to existing systems and special code from the vendor. You must expect disruption to the organization when installing them. You must expect long-term maintenance costs. And these packages are designed so it's very difficult to change your mind. If you wish to change to a different vendor, you've got a huge problem. In about 1990, Cornell decided to move all its major systems to PeopleSoft, which is now part of Oracle. This decision has cost the university literally several hundred millions of dollars. If you are involved in evaluating such a decision, insist on a very thorough feasibility study. Think in terms of taking at least a year with your very best staff and be prepared to spend several millions of dollars before you make your decision. For any major system, you must expect large changes over its life cycle. This will involve replacement of components and rewriting of components. Here are some of the reasons. First of all, new vendor or new technology. You'll replace components because the supplier goes out of business or doesn't provide adequate support, increases its price, or because you can get better software from another source with better functionality, better support, and so forth. This can apply to either open source or vendor-supplied components. You may decide on a new implementation of a component. The original implementation may be problematic. It might have poor performance, bad backup and recovery, difficult to troubleshoot, or unable to support growth. For example, when we were doing the portal for the National Science Digital Library, the original implementation used a system called uPortal, which just did not support the extensions that were requested, and it was awkward to maintain. So we re-implemented the portal using PHP and MySQL. When a system goes into production, it's almost inevitable that there are going to be changes to the requirements. Use of the system in production will reveal weaknesses and opportunities for extra functionality, and very often lead to requests for changes in the user interface design. As an example, in any data-intensive system, it's almost certain that there will be requests for extra reports and new ways to analyze the data. This should not bother you. Requests for enhancements are signs of a successful system. Clients recognize latent possibilities and hope to have them. A final reason for replacing components is that the application domain changes. For example, an organization may move into different business areas. There may be external changes such as new laws. The organization may be involved in mergers or takeovers. There may be new groups of users, new technology, and so forth. When the application domain changes, you rarely have the opportunity to implement a completely new system. Therefore, existing systems may be modified, and this may involve extensive restructuring, but it's important to reuse existing code as much as possible. We now want to look at design patterns. These are template designs that can be used in a variety of systems. They're particularly useful in situations where classes are likely to be reused in a system that evolves over time. The definitive book on design patterns was written by Gamma and colleagues in 1994. The title is quite interesting: Design Patterns, Elements of Reusable Object-Oriented Software. The discussion in this lecture is based on that book and also based on the book by Brugger and Detroit. For many of the individual design patterns, if you want more information, you should go to Wikipedia. Wikipedia has good discussions, typically using UML and other notation with code samples. Design patterns make extensive use of inheritance and abstract classes. As you know, classes can be defined in terms of other classes using inheritance. The generalization class is called the superclass, and the specialization is called the subclass. Here is a definition of an abstract class. Abstract classes are superclasses which contain abstract methods and are defined such that concrete subclasses extend them by implementing the abstract methods. Before a class derived from an abstract class can be instantiated, it must implement concrete methods for all the abstract methods of its parent classes.
Several of the standard design patterns make use of delegation. A class is said to delegate to another class if it implements an operation by resending a message to that class. And delegation is an alternative to inheritance that is very useful when reuse is anticipated.
Here is the notation that we will be using. Class names, as usual, begin with a capital letter. If the name is in italic, it indicates an abstract class. A dashed line with an arrow indicates dependency. A straight line is for delegation, and a straight line with a white arrowhead is for inheritance.
The first pattern we're going to look at is called an adapter. It's sometimes called a wrapper because it wraps around legacy code. The problem is as follows. Suppose you have a legacy class with its interface, perhaps on a server, and you have a client with a different interface, and you want the client and the legacy class to work together without changing either. This might happen during a transitional period when the long-term plan is to phase out the legacy system, but you want to use this client. As an example, how do you use a web browser to access an information retrieval system that was designed for a different client? This diagram shows the problem. On the right, you have the old system. You have the legacy class with its interface, which was designed to work with an old client. On the left, you have the new system. You have a new class, and you have a new client which are designed to work together. So the new class has a method called request, and the legacy class has a method called existing request, and they're not the same. So during your transition, how can the new client be used with the legacy class? Here is the solution. What you do is you have this abstract class called client interface, which defines the interface that the client expects. And then you have this class called an adapter, which subclasses the client interface and takes a method such as request and delegates it to the existing request method of the legacy class. So you can think of it as a class that adapts the interface of request to the interface of existing request. The following consequences apply when you use the adapter design pattern. First of all, you achieve your goal that the client and legacy class work together without modification of either. Adapter, in fact, will work with the legacy class and all of its subclasses. If, on the other hand, you change the client or you replace it by a subclass, then you'll typically need a new adapter. We now look at the bridge design pattern. This allows for alternate implementations. Here's the problem description. Decouple an interface from an implementation so that a different implementation can be substituted, possibly at runtime. For example, you might be testing different implementations of the same interface. People sometimes confuse bridge and adapter design patterns. Remember that with bridge, you have defined interfaces that don't change, whereas with adapter, you have a legacy interface and a new interface that you're trying to get to work together.
Here's the beginning of the bridge class diagram. On the left we have a client, and on the right we have two concrete implementations, concrete implementer A and B. We want them to work together as alternatives. This is done in two parts. First of all, we define an abstract class implementer which has the interface provided by the two concrete implementations. Then we have a class called abstraction, which is an abstraction of the interface supported by the client. Notice that abstraction is not an abstract class. This is somewhat confusing. So the abstraction class defines the interface visible to the client, whereas implementer is an abstract class that defines the lower level methods available to abstraction. So an abstraction instance needs to maintain a reference to its corresponding implementer instance, but abstraction and implementer can be refined independently. So the consequences are that the client is shielded from the abstract and concrete implementations, and the interfaces and implementations can be tested separately. Lecture 18, end of Part 1. Lecture 18, Part 2. The strategy design pattern is an extension of the bridge design pattern. Here's an example. A mobile computer can be used with a wireless network or connected to an Ethernet, and you have dynamic switching between networks based on location and network cost. So the problem description is you have a set of mechanisms and you want to decouple a policy deciding class from the set of mechanisms so different mechanisms can be changed transparently. Look at this class diagram. You have an application on the left, think of it as a client, and on the right you have two mechanisms, Ethernet and wireless network. Think of these as separate implementations of an abstract class network interface. This is exactly the starting point for the bridge design pattern. Continuing the model as before, we now have a class called network connection, which is equivalent to the bridge abstraction, but we have a new class, location manager, and the location manager is a policy class which determines which of the mechanisms, Ethernet or wireless net, is going to be used at any given moment. If we leave the example and look at the strategy design pattern in general, we see the following solution. We have a client that accesses services provided by a context. The context services are realized using one of several mechanisms, and that's decided by a policy object. The abstract class strategy describes the interface that's common to all the mechanisms, and the policy class creates a concrete strategy object and configures context to use it. This leads to the following class diagram, and you can see the similarity to the bridge design pattern with the addition of the policy class. So the consequences: concrete strategies can be substituted transparently from context. Policy decides which strategy is best given the current circumstances. And you can create new policy algorithms without modifying context or the client. We now look at a very different design pattern, the facade design pattern. The goal here is to reduce the coupling between a set of related classes and the rest of the system. For example, you might have a compiler that's composed of several classes, a lexical analyzer, parser, code generator, etc. A caller invokes only the compiler, which contains the contained classes. So the solution here is we have a single facade class which implements a high-level interface for a subsystem by invoking the methods of the lower-level classes, and the rest of the system knows nothing about the lower-level classes. Here's a class diagram. You have the facade, which shows an interface to the outside world, and it actually provides services by invoking various classes, class 1, class 2, and class 3, but they are hidden behind the facade. Some very good consequences follow from this. A client is shielded from the low-level classes of the subsystem. The use of the subsystem is simplified by providing higher-level methods, and the lower-level classes can be restructured without changes to the clients. Using the facade pattern repeatedly yields a layered system. The composite design pattern tackles a problem which almost all of us have wrestled with. When you're coding a recursive hierarchy like a tree, you often find yourself writing one set of code for the leaves and another set of code for the nodes, despite the fact that they are very similar. So the problem description is how to represent a hierarchy which can be variable width and depth, so that the leaves and the composites, that's the other nodes, can be treated uniformly through a common interface. And the solution is to define an abstract class component that has the shared attributes of leaf and composite, so that the component interface specifies the services that are shared between leaf and composite. A composite has an aggregation association with components and implements each service by iterating over each contained component. The leaf services do the actual work. Here are the consequences. The client uses the same code for dealing with leaves or composites. Leaf-specific behavior can be changed without changing the hierarchy, and new classes of leaves can be added without changing the hierarchy. The final design pattern we're going to look at is an abstract factory. The abstract factory design pattern is used if you wish to shield the client from different platforms that provide different implementations of the same set of concepts. For example, a user interface might have several versions that implement the same set of concepts for several different windowing systems. For example, scroll bars, buttons, highlighting, done different way in the different versions. A user may have the option of, would you like the classical user interface or would you like the modern user interface? The solution is to make use of a concept called a platform, which is the application for a specific windowing system. And you represent the platform by a set of abstract products, each of which represents a concept. For example, one abstract product would be a button. You have an abstract factory class that declares the operations for creating each individual product. Then, for a specific platform, you realize it by a concrete factory and a set of concrete products. So here we have a client, and we have abstract product A, which might be a button, an abstract product B, which might be a slider, and you have an abstract factory which creates product A and creates product B. Notice these are all abstract classes. We now need concrete classes that implement the methods of these abstract classes. So here we have a concrete class, product A, and a concrete class, concrete factory 1. There could be several concrete factory classes, but each of them is a subclass of abstract factory. So here we have added the concrete class for product B. So what are the consequences? The client is shielded from concrete product classes. You can introduce an entirely new windowing system without the client knowing about it. You can substitute the families at runtime if you want it. However, adding new products is difficult since new realizations must be created for each factory. So if you had a new user interface widget, you have to create many versions. There's an interesting discussion in Wikipedia on this topic. Use of this pattern makes it possible to interchange concrete classes without changing the code that uses them, even at runtime. However, employment of this pattern, as with similar design patterns, may result in unnecessary complexity and extra work in the initial writing of code. This is a general statement that applies to many of the design patterns. The use of the abstract class and inheritance from the abstract class adds extra complexity to your programming. You have to decide whether it is worth the extra complexity to provide you with the future flexibility. Here is an old exam question. We looked at this system before in the lecture on system architecture. A company that makes sports equipment decides to create a system for selling sports equipment online. The company already has a product database with specification, marketing information, and prices of the equipment that it manufactures. To sell equipment online, the company will need to create a customer database and an ordering system for online customers. The plan is to develop the system in 2 phases. During phase 1, simple versions of the customer database and ordering system will be brought into production. In phase 2, major enhancements will be made to these components. In the previous lecture, we looked at system architectures that could help this planned development from phase 1 to phase 2. Now let's ask the question, how can design patterns help the transition from phase 1 to phase 2? For the interface between the ordering system and the customer database, select a design pattern that will allow a gradual transition. If you look at the description of the bridge design pattern, you will find that this fits very nicely. Draw a UML class diagram that shows how this design pattern will be used in phase 1. So here we see it on the next slide. This is exactly the class diagram for the design pattern we saw before, though there's one thing that may have confused you, and that is the ordering system is actually playing the role of the client in this case. So how does this design pattern support enhancements to the ordering system in phase 2? You can do that by subclassing the ordering abstraction. And how does it support a possible replacement of the customer database in phase 2? It allows several concrete database implemented classes, and you can switch between them. To end this lecture about software reuse, I want to say a few words about legacy systems. Many large data-intensive systems, such as those used by banks and universities and electricity companies and telephone companies, are legacy systems. They may have been developed 40 years ago as batch processing master file update systems, and then they've been continually modified. Recent modifications might include customer interfaces for the web, smartphones, and so forth. The systems will have migrated from computer to computer, across operating systems to different database systems and so forth. And the organizations themselves may have changed through mergers. Unfortunately, when these changes are made, they're typically add-ons to the existing architecture. And maintaining a coherent system architecture for such legacy systems is an enormous challenge. But the complexity of building new systems is huge and is very rarely attempted. The worst case described on this slide is very similar to the situation I found with the financial systems at Dartmouth when I was first in charge of computing there. We have a large, complex system that had been developed several decades ago. It was widely used throughout the organization by an unknown number of customers. All the people who developed it had retired or left. There was no list of requirements. It was uncertain what functionality the system provided and who used what functions. The system and program documentation were incomplete and not kept up to date. In fact, in the case of the Dartmouth system, there was essentially no documentation. It was written in out-of-date versions of programming languages using system software that was also out of date. Over the years, there had been numerous patches that had ignored the original system architecture and the program design. There was extensive code duplication and redundancy, and the source code libraries and the production binaries were incompatible. So what do you do if you're faced with such a system? Well, the first thing is you have to have the confidence of the client. The development team and the client are going to have to develop a plan for rebuilding the system together. The first thing to recognize is that although there are no documented requirements, the system is actually satisfying some implied requirements. So by looking at the system, looking at how it's used, you can answer questions like, who are the users? What do they actually use the system for? Does the system have undocumented features that are important or bugs that users rely on? How many people use the fringe parts of the system? Where are they flexible? The system design will give you some clues about these implied requirements. So is there any system documentation, and what does it say? Does the source code include any hints about the requirements? Is there any code to support obsolete hardware or services? If so, does anybody still use them? At Dartmouth, we put a good person for 1 year looking at the existing system and analysing the implied requirements. Even if you're rebuilding the system, you're going to have to reuse much of the legacy code. So the first thing is to get control of the legacy code, and this is a question of source code management. So you use the source code management system to establish a starting version of the source code and to build your binaries from this version of the source code. You also need to create a test environment so that the rebuilt system can be compared with the current system. And at this stage, you can begin to collect test cases. You should also check the licenses for all the vendor software to make sure that you do actually have the software you're entitled to and that you have licenses for it all. To rebuild the software, you will usually follow an incremental software development process, with each increment released when completed. Here's some of the tasks you're going to have to tackle. The order will depend upon the condition of the code. And typically, you will work on different parts of the system in a series of phases. The first thing is to understand the original system architecture and program design. From that, you establish a component architecture which is the target you're aiming for. It'll have defined interfaces, even if much of the current code does not match the architecture and needs adapters. You should then make sure that you're using current versions of programming languages and system software. If there are any subsystems that you don't have source code for, and that's quite common, carry out a development cycle to create new code that implements the requirements. Often you will find there is duplicate code patched across a system. If so, replace it with a single version. Remove redundant code and remove obsolete requirements. Above all, clean up as you go along, don't rush, and be prepared to take many years in rebuilding a system.
Lecture 18, End of Lecture. Lecture 19, Reliability.
Building reliable software is much more than writing bug-free code and testing it thoroughly. You need to be considering reliability at every stage of the software development process. In this lecture, we look at how to do this, how to build reliable software. In the next lecture, we look at testing and the various techniques that you can use to check that you have indeed built a good software system.
First of all, some terminology. Anybody who's ever written a computer program knows what a bug is. It's a programming or a design error where the system as written does not conform to specifications. Typically this will be a coding error, but it could be things like an error in a protocol or an interface. Sometimes this is called a fault, though we will usually use the more common word bug. But there's another sort of problem, and that's called a failure. That's when the software does not deliver the service expected by the user, even though there are no bugs in the programs. This could be a mistake in the requirements, a confusing interface, or something like that. Here's a real example from my own experience. When I was at Dartmouth, one time we paid the president of the university the wrong monthly salary. The reason was that the trustees had given him a salary raise which took his salary over the maximum that was allowed by the program, and the program paid the wrong amount. There were no bugs in this program, it was the requirements that were wrong. You will sometimes hear the expression, "That's not a bug, that's a feature." Users will often report that a program behaves in a manner that they consider wrong, even though it's behaving as intended. Usually that's not a bug, that's a failure. Whether the failure should be corrected is a decision that needs to be made, and it needs to be made by the clients, not by the developers, because it's fundamentally the client's decision what the users of the system should see. Here is some more terminology. Fault avoidance. This is building systems with the objective of creating fault-free, that's bug-free software. That's one of the themes that runs throughout this course. The next is fault detection, and that is typically considered testing and verification. The aim here is to detect the faults, the bugs, before the system is put into operation or when they're discovered after release. Finally, fault tolerance. Here the aim is to build systems that continue to operate when problems occur. These problems might be bugs, but they could also be overloads, bad data, or other expected problems. Here is a case study of a system that had no bugs, but showed a variety of failure types. It's based on a historical incident. A passenger ship with 1,509 people on board grounded on a shoal near Nantucket Island in Massachusetts. At the time, the vessel was about 17 miles from where the officers thought they were. The vessel was actually coming from Bermuda going to Boston. This was a modern ship, well equipped with good navigation aids. The officers and the crew were well trained and the weather was good. The report from the National Transportation Safety Board about the accident found the following. The ship was being steered by an autopilot, and the autopilot relied on position information from a GPS system. If at any stage the GPS could not obtain a position from satellites, it provides an estimated position based on dead reckoning, which is the distance and direction travelled from a known point. This works well if the GPS fails for just a minute or two. But what happened was the GPS failed 1 hour after leaving Bermuda, and did not recover. In fact, the problem was that a cable had become disconnected. The crew failed to see the warning message on the display, or they did not check the instruments, and almost 2 days later, and 600 miles later, the dead reckoning error was 17 miles. Let's look at this report from a software point of view. First of all the software worked as specified. There were no bugs. But after the software had been specified, the requirements for the GPS had changed. It had been planned as a standalone system, but was now expected to be integrated with the autopilot. Next, there was a design problem in that the manufacturers of the autopilot and GPS had adopted different strategies about the communication of mode changes, such as failure of the GPS. Next, the programming of the autopilot had not specified that all of the status bits in messages from the GPS should be observed. Next, the user interface was faulty. The warnings provided to the crew were not conspicuous, and they only stayed on the screen for a short while. Finally, although the officers had been well trained in general navigation, they had not been trained on this particular equipment. The conclusion is that reliable software needs all part of the software development process to be carried out well, from requirements all the way to training. If you want to build reliable software, here's some key factors. First of all, the management and senior technical staff must create an organizational culture that expects good quality. Next, you've got to get the requirements right. There's got to be agreement, and that agreement has got to be precise and unambiguous. Next, avoid complexity. The design and implementation should hide complexity by using techniques such as structured design, object-oriented programming, and so forth. The programming style should also emphasize simplicity, readability, and it should avoid dangerous constructs. There are very good software tools that restrict or detect our errors, and that you should use them. Things like strongly typed languages, source control systems, and debuggers. At all stages of the development, there should be systematic verification. This means verification at the requirement stage, system architecture, program design, implementation, and user testing. Finally, pay particular attention to changes and maintenance. Good organizations create good systems. Managers and senior technical staff must lead by example, and they need the support of the senior executives. Software is built by teams, and everybody must accept the group style of working. If there are meetings, people should show up on time, they should be prepared, and they should support juniors. Visibility is essential. Everybody must know the state of the project. Finally, complete a task before moving to the next. For example, put the comments in the code, update the documentation, and so forth. As an example of what can go wrong, I was at one stage asked to look at a large database system being built for a library consortium. The system was continually collapsing under overload, and every new release had serious problems. I found that the technical staff were actually rather good. They knew what the problems were, and they knew how to fix them. The challenge was that their approach was going to take time, and the management would not give them time. So the management kept committing to releasing software that wasn't ready, and it gave trouble. The report that I wrote with a colleague simply said, if you give this technical staff time, they will do a good job, and 2 years from now you'll have a good system. The board of the consortium did precisely that, and the system worked well. The board also changed the management of the team that was building the software for a team that would listen to their staff. Building reliable software needs high-quality management processes. It's almost impossible to build good software without good processes. Much of software development in good organizations involves routine. Good organizations will use standard terminology. For example, in this course, I use the words requirements, design, acceptance, and so on, very carefully with the same meaning every time. Software standards are very important when many people are going to work on a project. This includes coding standards, naming conventions, and so forth. Regular builds of complete system is a very standard form of software integration and testing. The procedures for internal and external documentation will be standardized, and so will be the reporting procedures. This routine is important for both heavyweight and lightweight development processes. For example, the documentation standards may be quite lightweight. The important thing is that everybody follows the same standards. Quality management processes are particularly important when time is short. If you're short of time on a project, pay extra attention to the early stages of the process. Get your feasibility and your requirements and your design right. Because if mistakes are made in these early processes, particularly the requirements, there will be little time to fix them later. Experience shows that taking extra time on the early stages will usually reduce the total time to release a system. Another key to building reliable software is communication with the client. The system is no use if it does not meet the client's needs. It may be free of bugs, but it will fail for other reasons. So the client must understand and review the agreed requirements. It's not sufficient to present the client with a specification document and ask him or her to sign off. Appropriate members of the client staff must review relevant areas of the design, which should include operations and training materials and systems administration. And the acceptance tests must belong to the client. Complexity is the enemy of reliable software. The human mind can only understand limited complexity. Therefore, everything you do must aim for comprehensibility, simplicity, and above all, partitioning of complexity. It's easier to get a simple component right than it is to get a complex one right.
End of part 1. Lecture 19, part 2.
If you're going to build reliable software, you've got to pay particular attention to managing changes. Even if you use a sequential process like the modified waterfall model, there are going to be a lot of changes that have to be fed back into the development cycle from things that you discover as you work your way through the process. Changes can easily introduce problems, and that's why change management is so important. Source code management and version control should be part of all software development projects. Tracking of change requests and bug reports should also be routine. There should be procedures for changing requirement specifications, designs, and other documentation. These can be quite lightweight, or they can be very formal. Regression testing for testing changes will be discussed later. It also is key. Finally, release control needs to be taken seriously. When you're adding new functions or fixing bugs, it's very easy to write patches that solve today's problem but violate the system architecture or the overall program design. Try to avoid this as much as possible. Sometimes it will be difficult to do, but try to avoid it. And be prepared to modify the architecture to keep a high-quality system as the programs and the system evolve over time. Fault tolerance is another aspect of building reliable software. The aim is to create a system that will continue to operate when problems occur. Examples of the sorts of problems are invalid input data. For example, in a data processing application, if one data record is in error, you do not want the entire system to stop. Another example is overload. In a network system, if the number of packets that arrive at a certain point of the network exceeds the maximum capacity, the network should not crash. Finally, in big systems, there may be hardware failures, and you want the system to be able to continue running even if part of the hardware is not operational. Fault tolerance is a big topic in its own right. The general approach is as follows. First of all, you've got to detect failures. Next, there's got to be automatic routines that assess the damage. What damage has been caused, and is it possible to recover? If it's possible to recover, then there needs to be code for the recovery, and then, if possible, there should be code to repair the problem. One of the standard techniques of fault tolerance is backwards recovery. The system records the system state at specific events called checkpoints, and after failure, recreates the state at the last checkpoint. You combine the checkpoints with system logs or audit trails of transactions that allow the transactions from the last checkpoint to be repeated automatically. So if there is a failure, you go back to a known point and rerun from there automatically. This type of recovery software is difficult to test, and you need to schedule special tests and special time in your acceptance testing to check these out. As an example from my own experience of the difficulty of testing recovery software, on one occasion I was responsible for a large campus network which was hit by severe lightning storms. After the lightning storms had passed, essentially every router and major component had to restart. And the restart process crashed because of overload. We had tested the system with small numbers of reloads, but because of incremental growth, we had not realized what would happen if we tried to restart the entire network instantaneously. A final thought about building reliable software. It's easier to build small projects with small teams reliably. Small group communication cuts the need for intermediate documentation and reduces misunderstanding. Small projects are easier to test. Small projects have shorter development cycles. Mistakes in requirements are less likely and less expensive to fix. And when one project is completed, it's easier to plan the next. Improved reliability is one of the reasons that incremental development, such as Agile, has become popular over the past few years. Though it should be said, although there is improved reliability in the individual increments, it may be even more difficult to build a large system with good reliability in this way. Once a system is operational, you should be monitoring it continually for reliability. In this case, you can define reliability as the probability of a failure occurring in operational use. Traditionally, for online systems, there have been three measures. One is the mean time between failures. The next is the availability, the uptime. And the last is the mean time to repair. When there is a problem, how long is the system down? There are also some very important market measures. What complaints do you get about the system? Do you retain your customers, or do you find you're losing your customers to competitors? Once you get large distributed systems with many components, these traditional metrics are hard to apply. For example, you may have a system that has excellent average reliability, but gives terrible service to certain users. Those users, for example, might depend upon a specific server or network component. In a big network, at any given moment, something will be giving trouble, but very few users will see it. And when there are many components, system administrators rely on automatic reporting systems to identify problem areas. The problem with this approach is sometimes you will get reports such as, by our normal reliability metric, we had very few failures last week. But some customers saw very, very bad service, and they will complain, and rightly so. Users' perception of reliability depend upon circumstances. It depends upon the user behavior, their sets of inputs, and how much failure hurts them. The distribution of failures is very important. Consider the following. Which is worse? A personal computer that crashes frequently, or a machine that is out of service for 2 days every few years but runs perfectly the rest of the time? Whether one is better than the other depends upon how you use your personal computer. Or consider this one. A database system crashes frequently but comes back quickly with no loss of data. Or it could fail once in every 3 years, but the data has to be restored from backup and the system might be down from a long time. Whether the first is better than the second depends on the circumstances, but it may make a big difference to how you design the system. Finally, what about a system that does not fail, but has unpredictable periods when it runs very slowly? Your metrics may show this as a fault-free system, but the user's perception may be that it's very unreliable. As part of the requirements, the client and the software developers need to agree on the reliability metrics and the targets for each. For example, consider a bank ATM card reader. One failure class is that the system fails to operate and needs to be rebooted. The requirement might be that this should take place no less than once every 1,000 days. Another failure class is the system cannot read a perfectly good undamaged card. And the requirement here might be that this should take place no more frequently than 1 in 1,000 transactions. Finally, there is a very serious failure class. A pattern of transactions corrupts the financial database, and the requirement here should be that that should never happen. If you're in charge of any big complex computer system, you will be perpetually trying to improve your reliability without spending too much money. If you plot cost against any of the reliability metrics, you will often see curves like this, that as the reliability approaches 100%, the cost of improvements gets very high. There are some systems where the reliability metrics are much lower than this. For example, many supercomputers average 10 hours productive work per day. How would you spend your money to improve the reliability? Here's an example. It's based on my own experience, though I've changed some of the details. You're responsible for a central computer system, for example, a server farm, which is vital to an entire organization, for example, an internet shopping site. Any failure is serious, but the system is sufficiently complex that there are going to be failures. What do? Well, the first step is to gather data on every failure. So you create a database that records every failure, and you analyze every failure. In our case, we divided them by hardware, software, environment such as power and air conditioning, and human, typically operator error. Since the analysis was done by the software team, if they could not find what caused the fault, it was blamed to software. The next thing is to analyze the data. Weekly, monthly, and annual statistics of the number of failures, the number of interruptions, the mean time to repair, with graphs of trends by component. For example, failure rates of disks, hardware failures after power failures, crashes caused by software bugs in each component, categories of human error. With this information, we were able to invest our resources so we got the maximum benefit from them. So we had a priority order for software improvements. We could change the procedures for the operators. We knew the order in which we would buy new hardware. And as an example of a special circumstance, we completely changed the procedures for restarting after power failures. Over a period of several years, this systematic approach led to a much more reliable computer system.
Lecture 19, Reliability, end of lecture. Lecture 20, Verification, Testing and Bugs.
This lecture is about the various methods of testing software. Thorough testing is an essential part of software development, but always remember it's only part of the process of building a reliable software system. For building reliable systems, there are two principles. The first is each stage of development must be done well with incremental verification and testing. The word incremental is very important. I'm sure that all of you are too experienced to think you can build a large program and then start testing it. You test each part as you develop it. The same goes for a system. You need to do incremental verification of the requirements, of the design, and then of the programs. Testing and correction do not ensure quality, but you cannot build reliable systems without doing thorough testing. It's convenient to divide verification into two categories. The first is static verification, which are techniques that do not include the execution of the software. They may be manual or they use computer tools, but you don't have to have an operational program. When you have an operational program, you can use dynamic verification, otherwise known as testing, in which you test the software with trial data, followed by debugging to remove the errors. Reviews are a form of static verification that is carried out throughout the software development process. As this figure shows, you can have reviews of requirements, of design, and of programs. Reviews are a fundamental part of good software development. The concept is straightforward. Colleagues review each other's work, and this can be done at any stage of software development, but it's particularly valuable to review the program design and the code. Again, reviews can be formal or informal. It depends a lot upon the style of working of your organization. The first stage of review is preparation. The developer or developers provide their colleagues with documentation, and these can be models, specifications or design, or code listings. And the participants study these materials in advance. There is then a meeting in which the developer leads the reviewers through the materials, describing what each section does and encouraging questions. A review is a structured meeting. Here are the participants and the roles they play. First of all, they're the developers. They're the people whose work is being reviewed. There needs to be a moderator, somebody who ensures that the meeting moves ahead steadily. This will usually be a senior technical person. There needs to be a scribe, somebody who records the discussion in a constructive manner. The word constructive is important there. The reviews will often be wide-ranging. The scribe needs to record the decisions and the consensus. Other interested parties should be part of the meeting, particularly developers on the same project who depend upon the work that's being reviewed. Outside experts can be useful, knowledgeable people who are not working on this particular project, and representatives of the client if there are people who are knowledgeable about this part of the process. Reviews have many benefits. The first is that extra eyes spot mistakes and suggest improvements. You will sometimes see mistakes in other people's work that you miss in your own. And in fact, sometimes when you're presenting your work to others, you will see mistakes. In addition, colleagues share expertise. It helps with training for junior people to see how more senior people work. If there are incompatibilities between components, by having the people who work on those other components present, you can identify them earlier. Developers have an incentive to tidy up loose ends before a review, and review helps the scheduling and management control because everybody knows the state of the work that's being reviewed. For reviews to be successful, they have to be a team effort. The senior team members must show leadership, everybody must have good preparation, and everybody must be helpful, not threatening, even when the material being reviewed has obvious mistakes in it. You should allow plenty of time and be prepared to continue on another day if the review is not completed. Pair design and pair programming are another way to get two pairs of eyes looking at each piece of work. The concept is to achieve the benefits of a review by shared development. So two people will work together as a team, designing and or coding, testing, system integration, and in documentation and handover. The benefits should include two people create better software with fewer mistakes, and there's cross-training so that they learn from each other. I have very little personal experience of pair programming, but many software houses report excellent productivity. There is another form of static verification, which is like a review. It's called a program inspection. It's a very formal program review whose objective is to really drill down and detect all the faults. So the code will be read or reviewed line by line, quite slowly. 150 to 250 lines of code in a 2-hour meeting is typical. There'll be a checklist of common errors, and there'll be a team commitment, often involving trained leaders, to really debug the program together from the code. It's so effective that organizations that do it thoroughly claim that it can replace unit testing. Program analyzers are tools that scan the source of a program for possible errors and anomalies. For example, they look at control flow. They look for loops with multiple exit or entry points. They look for data use, for undeclared or uninitialized variables, unused variables, multiples assignments, array-bound problems, and things like that. They look for interface faults such as parameter mismatches, non-use of function results, uncalled procedures. And they pay particular attention to storage management, unassigned pointers, complex pointer arithmetic, which is always a potential source of problems. Some of these tools include cross-reference tables that show every use of a variable or a procedure or an object, information flow analysis that identifies input variables on which an output depends, and path analysis, which identifies all possible paths through the program. The programming toolkits that we use to write programs contain a large number of analysis tools. This example is the use of Eclipse to write a Java program. You might look at it to see how many analysis tools are being used on this slide and the next. For example, here there is a case of an undefined symbol, my counter, and there are a number of warnings at the bottom about fields that are never read locally. We now move to dynamic verification, otherwise known as testing. Testing is most effective if it's divided into stages. In another lecture, we've already looked at user interface testing, and we will later on look at acceptance testing. In this lecture, we're looking at program testing. And program testing is itself divided into stages. Typically, the first stage is a unit testing in which small parts of a program are tested separately. Then there are various forms of system testing: integration testing, function testing, performance testing, and installation testing. There are several main testing strategies. There's bottom-up testing, where each unit is tested with its own test environment. It's used for all systems. Then there's top-down testing, in which large components are tested with dummy stubs. It's particularly useful for testing user interfaces or workflow, and also for client and management demonstrations. Then there's stress testing, which is to test the system at and beyond its limits. It's particularly useful for real-time systems and transaction processing. Most systems, you're going to use a combination of all these three strategies. The people who develop a program will often know that there are some parts of the code that are particularly complex and need special testing. Open box testing is carried out by these people, the people who know the internals of what they're testing. For example, later in this lecture, I'm going to talk about testing a graphics package. The people who developed that package knew that the code for axes and tick marks on graphs was quite complicated, and therefore they emphasized special tests of that area of the package. At other times, it's useful to have testing carried out by people who do not know the internals of what they're testing. This is called closed box testing, and it's an opportunity for people to use the program in ways that were not anticipated by the people who developed it. I remember an educational demonstration by a leading computer manufacturer that I was asked to look at. Since I did not know how the program had been developed, I'd tested it by typing in random strings of control characters. This is something that no sensible person would do, but there's a chance that a student might eventually put in some of these sequences. And in fact, the program crashed heavily and it was difficult to recover. Unit testing is tests on small sections of a system or a program, for example on a single class or even a routine within a class. The emphasis is on the accuracy of the actual code against the specification, and the test data is usually chosen by the developers based on their understanding of the specification and knowledge of the unit. It can be at various levels of granularity, but typically it's at quite a small unit at a time. Unit testing can be open box or closed box. If it's not done by the developers, there may be special testers who work with the team. If you don't do your unit testing thoroughly, system testing becomes almost impossible. And if you're working on a project that's behind schedule, do not rush the unit testing. System and subsystem testing is where the units are put together. So they're tests on components or complete systems combining units that have already been thoroughly tested. And the emphasis here is on the integration of the interfaces. System testing uses trial data that's typical of the actual data, or it can stress the boundaries of the system by testing things like failures and restarts. It should be carried out systematically, adding one component at a time, making sure that that is passing all its tests until the entire system is assembled. Once again, it can be open or closed box by the development team or by special testers. System testing is finished fastest if you do it systematically, one component at a time, and making sure that each step is completely debugged before assembling the next. Then if any problem is found, almost certainly it's in the unit or component that was most recently added.
Lecture 20, end of Part 1. Lecture 20, Part 2.
How do you design good tests? Well, testing can never prove that a system is correct. An individual test case can only show that either a system is correct in that special case or that it has an error. The objective of testing is to find errors, or, if there is no error, demonstrate the program is correct in specific instances. Testing is never comprehensive, and you must always remember that testing is expensive. Test cases are specific tests that are chosen because they're likely to find specific problems. Test cases are chosen to balance the expense against the chance of finding serious errors. Who should choose the test cases? Well, cases chosen by the development team are effective in testing known vulnerable areas. This is the principle of open box testing. Cases chosen by experienced outsiders and clients will be effective in finding gaps left by the developers. This is part of the principle behind closed box testing. Cases chosen by inexperienced users will find other errors, another form of closed box testing. A test suite is the set of all test cases that apply to a system or component of a system. When you're running a test, you don't necessarily run all the test cases in the test suite, and you certainly shouldn't run them in the same order. There are some errors that occur only under certain circumstances, for example when certain other software is running on the same machine, or when tasks are scheduled in specific sequences, or with unusual datasets. Therefore, it's customary for each test to vary some of the test cases systematically and to change the order in which the tests are made. Incremental testing, typically daily testing, is a common form of development used by companies that use variations of the spiral development process. What they do is they create a first iteration that has the structure of the final system and some basic functionality, and they create an initial set of test cases. Then the developers check in changes to the system on a daily basis, and the organization rebuilds the entire system every evening. They then run a comprehensive set of test cases daily, which identify and deal with any new errors. So test cases are being added continually as the system is developed. Many large software houses, Microsoft is one of them, follow this procedure with a daily build of the entire system and a comprehensive set of test cases. For a really big system, this is a large undertaking that may require hundreds or even thousands of test computers and a very large staff of testers. This daily incremental testing is a form of regression testing. When software is modified, regression testing is used to check that the modifications behave as intended and do not adversely affect the behavior of the unmodified code. So the core concept is that after every change, however small, you rerun the entire testing suite. So, for program testing using regression testing, you collect a suite of test cases, each with its expected behavior. You create scripts to run all the test cases and to compare them with the expected behavior. The scripts may be automatic, or they may involve human interaction, such as user interfaces. When a change is made to the system, however small, for example, a bug is fixed, you add a new test case that illustrates the change, for example, the test case that revealed the bug. And then before releasing the change code, you rerun the entire test suite. Here is a small example of my own, a graphics package consisting of a preprocessor, a runtime package, which was a set of classes, and several device drivers. The starting point was a prototype with a good overall structure and most of the functionality, but hastily coded and not robust. On a daily cycle, we would design and code one small part of the package. This might be an interface, a class, a dummy stub, or an algorithm within a class. We would integrate that into the prototype. We would create additional test cases if needed and run a regression test. This proved a very effective way of developing a package that was highly reliable in practice. Testing needs to be documented. Every project needs a test plan that documents the testing procedures. This is used for thoroughness, visibility, and for future maintenance. It should include a description of the testing approach, a list of the test cases and related bugs, procedures for running the tests, and a report that analyzes the test results. When you find a bug, you need to fix it. This is debugging. The first thing is to isolate the bug. What you need is a repeatable case that shows the bug and that is simple enough that you can understand it. So if you have an intermittent bug, try to find a repeatable case, and if you have a complex example, find a simple example. Then you need to understand the bug and its context. What is the root cause of this bug? Does this section of code have dependencies? What are the structural interactions between the problem you found and other parts of the system? When you fix the bug, you need to design the changes and to document them, and of course code them, but you also need to create a new test case that would show up the bug if it hadn't been fixed. Fixing bugs is an error-prone process. When you fix a bug, fix its environment, otherwise you may well be creating new bugs. You'll need static and dynamic testing, and you need to repeat all tests that have the slightest relevance. This is where regression testing is so important. Bugs have a habit of returning. Unless you really understand the bug and have fixed the root cause, you may find that when a bug is fixed, sometime later it comes back in a different form. So when you fix a bug, add the failure case to the test suite for future regression testing. And then persistence. Most people faced with a problem will work around it, but the best people track down the root cause and fix it forever. Many bugs are simple to fix, but some may be extremely difficult to track down and isolate. This is particularly true of intermittent failures on large systems. Here are three from my own experience. The first was a large central computer that stopped a few times every month with no dump or other diagnostic. The next was a database load that died after running for several days with no diagnostics. And the third was an image processing system that ran correctly but used huge amounts of memory. These problems may require months of effort to track down. The best system programmer I ever worked with took about 3 months to find and fix the first of these three. If you'd like a very nice fictional example, see the novel by Ellen Ullman, The Bug, a Novel. Here is part of the work that was done tracking down the second of the bugs, the database load that failed. A programmer wrote a special program to capture data about the system and to display it graphically. I don't want to explain this graph except to show that once he had this data, it was fairly straightforward to understand what the problem was and to isolate it. This is part of the process of tracking down the image processing bug. It is actually from a CS5150 project from a few years ago. Once they were able to see which function was using all the memory, then they were able to fix the problem. Beginning programmers will often say the computer's wrong or the system's wrong. And in fact, it's almost invariably their software that's wrong. But just occasionally, even good manufacturers will ship system software which contains bugs. Here are 3 examples that I've seen. The first is an embarrassment. A well-known manufacturer shipped a Fortran compiler which calculated the exponential function wrongly. In fact, it calculated e to the 0 as 0. It took them about 2 days to fix this problem, but they did actually ship that. Another one was a program that I was writing that ran very, very slowly, and it turned out that a string to number function was very slow with integers. When I replaced the function with a simple loop that I wrote myself, the program ran in about 1/100th of the time. Finally, there's a system that we had with our web lab when we were loading very large amounts of web data into a database. This was a program that ran for several days or even weeks and went slower and slower and slower as time went on. And it found out that a very simple basic function from a well-known manufacturer had a memory leak which was slowly taking over the entire computer. 3 times in my career, I've actually encountered hardware bugs. The first was early in my career when we were working on a high-speed film plotter with a 1024 byte buffer. The documentation was not clear whether we should address this as 0 to 1023 or 1 to 1024. And when we tested it, we found that actually there were only 1023 bytes that could be addressed. The other 2 examples are both cases where we were running an operating system on hardware other than the operating system that the manufacturer expected and had tested. The first was the microcode for the virtual memory management. The other was a page fault for the window manager on a Sun workstation. In that case, it was possible for a very skilled engineer who was part of our team to reverse engineer the Sun firmware. That is, he read off the content of a ROM, found the bug, burnt new ROMs, and we were able to make the hardware work for us. Sometimes fixing a bug creates a problem for users. Customers may have built applications that rely upon the bug, or workarounds that compensate for it. Fixing the bug will break the applications. The graphics package that I mentioned had a bug in a function that handled rotation about the z-axis. People who used this function had to use a minus angle to get the right graphics. If we fixed the problem, which was merely a question of changing a minus sign, these applications would have failed. Another case was a piece of hardware which actually was not to spec. There was an emulator for this piece of hardware which was correct, but we used an application program that worked with the hardware as built, but not with the emulator as the hardware should have been built. This was compensating bugs in the application and the emulator. The most famous example of this problem came from Internet Explorer. One version of Internet Explorer was shipped with a bug that under certain circumstances rendered images off by 3 pixels. Many of the major websites used by Microsoft's customers had compensated for this bug. If Microsoft had simply fixed the problem, all these websites would have failed. So in each of these cases, the bug was easy to fix from a coding point of view, but releasing it would have caused problems for existing programs. To finish this lecture, a few words about user interface testing. User interfaces need several categories of testing. What we call user testing is done during the design phase. It is carried out with trial users to ensure that the design is usable. Design testing is also used to develop graphical elements and to validate the requirements. During the implementation phase, the user interface goes through the standard steps of unit and system testing to test the reliability of the implementation. This is just program testing. And then finally, acceptance testing is carried out with users on the complete system.
Lecture 20. End of lecture. Lecture 21. Acceptance testing and delivery.
A project does not end when the development team thinks that the system is complete. The client still needs to check the entire system to make sure that it meets the requirements. Then and only then is the system delivered and put into production. If one of the fundamental goals of software development is a happy client, few things are more important than thorough acceptance testing and a good delivery. Acceptance testing is done by the client, assisted by the developers. The complete system is tested, including the documentation, the training materials, installation scripts, and so forth. And the testing is against the requirements. Each requirement is tested separately. Scenarios are used to compare the expected outcomes with what the system does. And particular emphasis is placed on how the system handles problems, errors, restarts, and other difficulties. The question being asked all the time by the development team, is the system we have built the system that you, the client, wanted? Does it meet your requirements? The timing of the acceptance testing depends upon the development process being used. In the modified waterfall model, the development team aim to complete the entire project before the acceptance testing. Of course, if there are any problems found in the acceptance tests, then more development will be needed, but the aim is to minimize this. With iterative development, if the client is properly involved in the development cycle, the client will have tested many parts of the system at the end of each iteration and during user testing. Problems and suggestions for improvement will have been incorporated into the system. But there still needs to be an acceptance test of the completed system before it is released.
Acceptance testing is particularly important with agile development, since each sprint should end with fully tested code. In a large project, this means that the acceptance testing is divided into small amounts, each corresponding to a sprint. So each sprint should be a complete development process and end with acceptance testing by the client. If several sprints build on each other, each sprint may need to repeat the acceptance tests for earlier sprints to check that they're still met.
Acceptance testing is an important part of a software project, and it needs resources. It requires time on the schedule. It may require substantial investments in test data, equipment, and test software. It certainly requires good people. And it's important that help systems and training materials are part of acceptance testing. Acceptance testing is closed box by the client without knowledge of the internals of the system. They're in testing the entire system as a whole, and the emphasis is on whether the system meets the requirements. So the test should use real data in realistic situations with actual users, administrators, and operators. They must be successfully completed before the new system can go live or replace a legacy system. Completion of the acceptance tests may be a contractual requirement before the system is paid for. Acceptance testing may be integrated into the release of the software. The transition from the previous version of a production system to a new release is particularly challenging. There are 3 techniques commonly used. The first is parallel testing. Here, the clients operate the new system alongside the old production system with the same data and compare the results. In alpha testing, the clients operate the system in a realistic but non-production environment. And in beta testing, the clients operate the system in a carefully monitored production environment. Parallel testing is a standard technique for data processing systems such as financial systems and payroll. The old and the new systems are run together for several production cycles to check that the new system replicates the functionality of the old. It requires 2 sets of everything: extra staff, extra equipment, and so on. It requires software to control the changeover. For example, you do not want both the old and the new systems to mail 2 sets of payments. It requires automated scripts to compare the results. Parallel testing often will take several months, and very often the new system will be brought into production in phases. Alpha and beta testing. Alpha testing can be done with software that lacks some functionality. Beta testing requires the fully functional system. In both cases, they must be managed carefully. If you simply make versions of the software available to clients, many clients will never use it. Other clients will use a few features. Only a few clients will test it systematically, and only a few clients will report problems systematically. These clients are very valuable to you, so what incentives can you give them to test your software? Can you give them financial incentives like discounts on products, or prestige like publicity or other recognition? Acceptance and delivery are closely related. A good delivery package results in a happy client, happy users, and less expense in support and maintenance. But many projects rush the packaging and the help systems and training materials, or give them to the least experienced members of the team, do not test them properly, and generally neglect this part of the software process. Although I urge you to put effort into your delivery package, it doesn't have to be perfect. The best is the enemy of the good, and no system is ever perfect. If you insist on perfection, you'll never release anything. You'll never reach perfection because the ultimate test comes from the users. So learn what is essential to satisfy the client and put your resources into that area. Pressures to get products to market and into operation often lead to bad decisions. The client has to make trade-offs between the costs of packaging and delivery and future support and maintenance and the risk of later problems. All are expensive, but in my experience, the pain of being late is usually less than the pain of putting a bad system into operation. Different categories of software products need different packaging and delivery procedures, and the trade-offs are different. First, Let's look at a shrink wrap package, or a package that is downloaded over the internet. This must have good installation scripts. They've got to be automatic, and they've got to be robust to varieties of hardware and operating systems. They must be able to uninstall and reinstall. Support is very expensive when it requires staff. Therefore, the delivery package should include training materials and documentation for users, system administrators, and expert users. For maintenance, the client does not have source code. Therefore, there's going to be no bug fixing except with a new release. Contrast this with the data processing system. The acceptance period may cover several months, and the client should be comfortable with the complete system before taking final delivery. For support, the client should aim to be self-sufficient. This requires documentation and training materials for the system administrators and operators, and well-organized source code for maintenance. There may also be maintenance support contracts with the developers. Embedded systems pose special problems. The hardware and software will have been developed together, and the acceptance tests must be a combination. For maintenance, bug fixes may require servicing the hardware, and errors may be expensive or dangerous. Once again, support is needed in training for support personnel and documentation and training for users. Training is an important part of many systems. Time and money spent on training is usually well spent. This takes many forms. It can be one-on-one. The client may run in-house training courses or send staff to external courses. There may be distance education materials or online tutorials. The development team needs to provide information for these training materials. This might be organized as materials for users, for system administrators, for maintainers, and materials to train the trainers. A well-designed system needs less training, and this is an important goal in the usability. So a good conceptual model with good intuitive interfaces reduce the need for training. Different skill levels need different types of training. Skilled users work much more from the conceptual models, while less skilled users prefer cookbook sets of instructions. Occasional users will forget complex details, but generally will remember the overall structure. Help systems. A good help system is a major sub-project. It's time-consuming and it's expensive. But a good help system saves user time and support staff, so it's time-saving and cost-saving. This is the trade-off. In the design of help systems, remember that users need many routes to find information. They may need indexes by terms, examples, mini-tutorials, and so forth. And help systems need to be tested with real users in realistic situations. Documentation. If you've been conscientious during the development process, you will have a lot of documentation. But even so, substantial effort is needed at the final packaging and delivery stage. Here are some of the categories. You'll need documentation about the software development, requirements, design, source code, test plans, and results. This is primarily for future maintainers. There'll be user documentation. This may be introductory for various audiences, a user manual, or a website of known problems, frequently asked questions, and so forth. System administrators and operators will need system manuals. And finally, very important, do not forget the business side, the software licenses, contracts, and so forth. Installation tools are another part of delivery, and the installation tools need to be part of the acceptance testing. Creating installation scripts can actually be a substantial task. You'll need different scripts, tools and procedures for different categories of software, and the testing must be done really thoroughly with real users in a realistic environment. What materials should you deliver for your CS5150 projects? When you leave, all that the client has is your software and your documentation. Imagine that you work for the client and are asked to take over the system. What would you want? Different projects will have different deliverables, so discuss the delivery with your client. Usually, you will place your materials on a project website. The materials can be in any format, they need not be huge, but they must be current and reflect all changes. Here's a checklist. For the documentation, you should have some requirements updated to reflect the delivered system, the system and program design, again updated to reflect the delivered system, instructions for users, administrators and operators, presentation slides updated to reflect the delivered system, and please do not forget the business documentation, including the copyright license. The system itself will consist of source code and matching binary for all programs, installation scripts, and your test scripts, test data, and test reports. For your projects and for other systems that you develop, think about maintenance. Most production programs are maintained by people other than the programmers who originally wrote them. So think carefully. What factors make a program easy for somebody else to maintain? What factors make a program hard for somebody else to maintain? When you maintain other people's programs, you'll be thankful if they've answered these questions well.
Lecture 21, End of Lecture. Lecture 22, Legal Aspects of Software Development.
This lecture looks at legal aspects of software development from the point of view of a software developer or a computing manager. When I first had a senior position in computing, I was surprised at how much time I was spending with lawyers and how little I knew about the legal framework that controls the environment in which we do our work. This lecture tells you some of the things I have learned.
Software is expensive and it's developed in a complex legal and economic framework. Everybody who works in software needs to be aware of parts of this framework, and a senior manager or a consultant will frequently work with lawyers. You need a lawyer for anything other than the most basic legal issues. I am not a lawyer, though I have discussed the content of this lecture with a lawyer who specializes in the field. So please don't consider this lecture legal advice. If you want legal advice, you need a lawyer. A few words about legal change. You will often find that the law that applies to computing is worded in ways that you find unfamiliar. One reason for this is that changes in law usually follow changes in the world, and in a technical field that's changing fast like computing, the law is always behind what's actually happening. Lawyers and politicians typically have poor technical backgrounds, and the terms they use and the way they think about things are not the ways that you as computing people would find natural. Finally, you have to understand that the interpretation of many laws is unclear, as they may never have actually been tested in court because of the cost of litigation. You'll find strange analogies are often made between new technical paradigms and old world systems. In computing, we're accustomed to reading technical documentation, and it's often useful to read the actual text of a law. For this purpose, Cornell's Legal Information Institute is very useful. The Institute's website has the full text of the entire United States Code, that's the actual wording of the law,
It has all the federal regulations and much more useful information. So read the code, but do not try to interpret the law by itself. You may be reading the wrong law, or you may not know how the court has interpreted the law. Do not assume that the meaning of the law as interpreted by the courts is what you would expect from the wording and reading the statutes. Finally, be careful about legal advice on the web. Some of it is good, but much of it is simplistic and some of it is completely wrong. In this lecture, I'm going to look at the following topics. First of all, jurisdiction, the relationship between international law, federal law, and state laws. Then intellectual property, which includes copyright, patents, and trade secrets. Then contracts and licenses, a little bit about privacy, a little bit about free speech and its limitations, and finally, a few words about employment law. This applies to you personally and to anybody who you hire or who works for you. Statutes and precedents. The United States follows common law. This law is a combination of various types of material. First of all, there are statutes. These are bills passed by the Congress and the 50 states. The statutes often expect that there will be regulations that fill in the details, and these will be issued by the government of the United States and of the 50 states. But in common law, there's also something else, and that is the judgments, the precedents made by courts. The courts will often expand or clarify law in areas where there are no details in the statutes or regulations. And these precedents become additions to the law. Jurisdiction. In the United States, when legal issues arise, they may be covered by federal law or they may be covered by state law. The United States has the federal law, which covers the entire United States with the federal court system headed by the United States Supreme Court. But in addition, each of the 50 states has its own laws and its own court system. In theory, every state could be completely different, but much of the state law that covers computing is based on what is known as the Uniform Commercial Code, and so there's actually quite a lot of standardization between the states, but there are many differences, and these differences can be important. International law is becoming increasingly important, particularly with network systems such as the Internet. And the relationship between United States law and international law is complex. Moreover, this relationship is changing. It's often said that the Internet has no boundaries, and this certainly applies legally. If you break a law in Finland, but you are on the Internet in the United States, what law applies? What if you're in California and you break a law in Minnesota? The same question. Financial things. Where do you pay taxes? Now to the first major topic, copyright. Copyright is federal law. It applies to so-called literary works. The term literary works was originally applied to textual materials such as books, but it's been gradually extended to cover all forms of text, music, photographs, design, and more recently, software. Copyright applies to the expression of ideas, for example, the words in a text. It doesn't apply to the ideas, nor to physical items such as a book. In software, copyright applies to the program instructions, the actual code, but not to the concepts behind the instructions, nor to the files or printouts of the program instructions. In the United States, copyright gives the owner exclusive right to reproduce or copy a literary work, to distribute it, to perform or execute it in public, to display it in public, or to license it to others who can reproduce, distribute, perform, or display. There are two important special exceptions which rarely apply to software. The first is first sale. The owner of an object, like a physical book, can sell the object without permission of the copyright owner. Fair use allows limited use without permission of the copyright owner under strictly controlled circumstances. An example is to quote some text in a review. In theory, copyright lasts for only a period of years, but the period is much longer than the life of any software, and in practice, copyright in software lasts forever. Copyright is an example of what is often called intellectual property. It's different from physical property like a car or a house, but there are some similarities. In particular, copyright has an owner, and the owner can sell or license it to others. In the United States, and the United States is different from other countries, copyright is established automatically when a work is created, and the owner is the creator. There is one important exception, and that is so-called works for hire. When the creator is employed, the employer owns the copyright. There are special rules that apply when the work is created by several people, which is often the case with software. In the United States, copyright is intellectual property, and it can be sold or licensed with very few restrictions. The agreement to sell copyright is written as a contract, and we'll talk about contracts later. You might be interested in the actual wording of the United States Code that describes ownership of copyright. This particular part of the code is quite clear, and I think you can understand the terminology. Notice that the authors of a joint work are co-owners of copyright in the work, and this applies to many of your software projects. To repeat, if you are employed, copyright in the code that you write belongs to your employer, not to you. So if you work for a Cornell department, the department or Cornell owns the work that you do. A particularly important case is if you work freelance. If you do, make sure you have a contract with the organization you're working for that is explicit about who owns the copyright. It may be that you own it, it may be the organization owns it, but write it down in advance. If you do not own the copyright, you need permission to use your own work, to copy it or to use it, even if you actually wrote the code. For example, you cannot make a copy for your personal use or to take with you if you change jobs. There are special rules for academic work. You should read the Cornell copyright policy. There's the URL. The basic policy is that academic work belongs to the person who does it. So you own the copyright in the work that you do for class. Anybody else, including Cornell or your clients, needs your permission before using the software. This is why we insist that in the feasibility study for your project, you include a commitment to your clients that you will provide them with extensive rights to the software. They must be able to use it. You can transfer ownership of the software, you can give them a comprehensive license, or often it makes sense simply to put the code in the public domain, but they must be able to use the software that you create. It is particularly important to clarify the ownership of software if your project is for a startup company or some other entrepreneurial venture. If the venture succeeds, there may be large amounts of money, and you don't want to get into a dispute about who owns the software and whose money it is. If there's any doubt, you should ask for advice. Many of you will have seen the film The Social Network about the early days of Facebook. One of the themes in that film is a legal dispute about who owned the original concept and who owned the original code. On the website, there are various examples of materials from previous classes. For example, there are 2 examples of project agreements on the website. They're on the page on client expectation and business considerations. Before I put examples of previous students' work on the website, I need permission from the student authors. As you understand now, the student authors own the copyright, and I need their permission to put the material in public on the website. In academic life, there's another law that I have to obey, which is the Family Educational Rights and Privacy Act. This gives you, students, privacy in the work that you do for courses, and I need your permission before I show your work to other people. Many programs are built on existing programs. This is called derivative software, and you need to be particularly careful about copyright. When software is derived from other software, copyright in the new code, but only in the new code, belongs to the new developer or the employer of the new developer. The copyright in the old code is unchanged, and conditions that apply to the old code apply to derived work. So if you write a program S, which includes code derived from A and B, you cannot copy, use, distribute, or license this program S unless the owners of both A and B give you permission. And this applies even if you only use 1 or 2 lines of code from A or B. When creating a derived software product, make sure that you have documented rights to use everything from which it is derived. As an example of the problems, some years ago I worked for the organization that made the first open source release of Python. Most of Python was written by the creator, Guido van Rossum, but Guido had used code derived from a number of sources, and he had not kept good records of where this code came from. We had a lawyer working about 6 months, tracking down the derived code and getting permissions. Some of the code we could not track down, and it was necessary to rewrite the code just to make sure that the open source release was in fact open source. To end this section on copyright, here are some old exam questions that have been used on this course. First question: when software is written, who owns the copyright? How can somebody else be permitted to use the software? How can copyright be transferred to somebody else? Answers: the person who writes the software owns the copyright, except works for hire when the employer owns the copyright. How can somebody else be permitted to use it? By permission from the owner, and this is usually a license. The license does not transfer ownership, but copyright can be transferred to somebody else. It's intellectual property that can be sold or even given away, and this is usually in the form of a contract. Next question: you're employed for company X writing software. When you leave, who owns your work, and what use can you make of the work? Answer: when you leave, the company owns your work. It was work for hire. And what use can you make of the work? The simple answer is none, without permission of the copyright owner. Perhaps there's some minor use under fair use, but don't count on it. A rather more difficult question: you do freelance work for a company. When you finish, who owns the work? And what use can you make of the work? It's not clear who owns your work. It depends upon the circumstances. And because it's not clear, you need to have a written contract before beginning the work that makes it clear. What use can you make of the work? Well, if you hold the copyright, you have unrestricted use, unless you have signed away some of your rights. But otherwise, you don't own the copyright and you cannot use it without agreement. Once again, there may be some minor use under fair use, but don't count on it. Often you will create materials that you want to put on the web and make available to others. How do you give them permission? Well, as an example, let's think about the materials on the CS5150 website. I wrote most of these materials, and by the Cornell copyright policy, I own the copyright on them. On the About page of the website, I describe how other people can use it. Basically, I give permission for people to use the materials in any way they want for non-commercial use, but I ask that they should acknowledge that I wrote the materials as part of this course. You will see that I make use of a license from an organization called Creative Commons. I strongly recommend Creative Commons and their licenses. On their website, they provide a family of licenses in which you can select the conditions you want. Do you require attribution? Do you allow commercial use? Do you allow modification? Creative Commons is formed by experts in the field, and their licenses are very valuable and easy to use.
Lecture 22, end of Part 1. Lecture 22, Part 2.
We now move on to software contracts. Legally, there are important distinctions between licenses and contracts, but we're not going to go into those differences. In general, a contract is an agreement to do something in exchange for some consideration, for example, for money. Contracts should be written down and they should be signed by both parties. Very important attribute of contracts is they're enforceable by courts. If things go wrong, either party can ask a court to enforce the contract. For simple agreements, an exchange of letters may be all you need, but make sure that it's written down and signed. The old expression, a verbal contract isn't worth the paper it's written on, which is attributed to Yogi Berra, really does make sense. Contracts are very flexible and you can agree to almost anything, but a typical software contract might include the following. First of all, a definition of what software is covered by the agreement. Who owns the software now? Whether there are any patents or other intellectual property involved and who owns them. There'll be payment amounts and the dates of those payments. There'll be agreement as to whether this is a permanent contract or a temporary contract. There'll be agreement about whether the agreement is exclusive or non-exclusive. Exclusive is when you, for example, license one party to use your software, saying you will not license the software to anybody else. Much of the complexity in contracts is about contingencies. What happens if things go wrong? How can you terminate the contract? What are the problems and difficulties that you expect? But in general, any other sensible terms and conditions that are agreed by both parties can be included in a contract. Open source software is an important part of modern computing that does not fit well into theories of contract law. But there are now several examples of open source licenses that are widely used and seem to work well in practice. One of these is the BSD license from the University of California at Berkeley. It was first used for the Berkeley Standard Distribution of open source Unix, which, for example, introduced TCP/IP to the world. It's very simple, very liberal, and often suitable for academic projects where the aim is to make the code available to everybody. The Apache license is often used for commercial projects with the same goals. It's a permissive license and does not require a derivative work to be distributed using the same license. For example, Google uses it for Android. Perhaps the earliest open source license was the GNU public license. This was used for an alternative to a Unix that developed into Linux. It requires that derived works can only be distributed under the same license terms as the original.
Now to another form of intellectual property, patents. Patents apply to inventions. Whereas copyright applies to the expression of ideas, patents apply to the ideas themselves, to the inventions. Patents should be non-obvious, they should be novel, and they should be useful. It requires a complex process of patent application. This is different from copyright. With copyright, at least in the United States, when you create something, copyright is automatic. With patents, you have to apply for them. Patents last a shorter term than copyright. They last 20 years from the date of the application.
This is all very sensible, but unfortunately software patents are a mess. One of the problems with software is it's usually difficult to know where ideas originate. It's often the case that many people, many organizations develop the same ideas at about the same time. The patent examiners, the professionals who decide on patents, have often not been experts in computing, and they've often allowed patents for routine computing concepts. As a result, there are hundreds, indeed thousands of patents which cover essentially the same ideas, and often you will find that there are patents on things that are routine computing concepts or trivial extensions of long-standing computing ideas. Just to make things more complicated, the international differences are quite strong. The Supreme Court has recently created precedents that may lead to stricter examination of patent applications, and I think everybody in the computing industry hopes for. On the other hand, there's a new law on the first to file for patents that may make the software situation even worse. This huge number of dubious patents leads to serious abuse. Companies often use the threat of litigation as a commercial weapon. For example, large companies harass smaller competitors, and this can delay the introduction of competing products or force them into expensive litigation. Even worse are the so-called patent trolls. These are companies that invent nothing and build no products. Their entire business is to threaten patent litigation. They buy large numbers of patents, many of doubtful value, and extort money from companies whose products use ideas related to the patents. If you have a senior position in computing, almost certainly, sooner or later, you will receive letters threatening patent litigation. Even if they look like nonsense to you, take them seriously. When you get one of these letters, consult a lawyer. Trade secrets. Trade secret is the legal term for confidential business information. For example, before a product is publicly announced, the specification is often secret. Once it's announced, it's no longer secret. Another example, the source code of a commercial product. Companies like Google do not want their competitors to see the source code of their programs. The legal definition from the Uniform Trade Secrets Act is as follows. It's information, including a formula, pattern, compilation, program, device, and so forth, that derives independent economic value from not being generally known and is subject to reasonable efforts to maintain secrecy. You will sometimes be asked to sign a non-disclosure agreement. This is an agreement that allows you to see trade secrets, but in return you agree not to disclose them to others. It's often perfectly reasonable to sign a non-disclosure agreement, but before you sign it, read it carefully. Some more about trade secrets. The owner must make reasonable efforts to maintain the secrecy. For example, label the information company confidential and restrict access to specified designated people. As long as reasonable efforts are made to keep it secret, a trade secret does not expire. And if somebody leaks a trade secret without authorization, it remains a trade secret. So suppose somebody who should not have access to Microsoft Office mounts the source code on the web. As soon as Microsoft sees it, they have it taken down, but competitors had a chance to look at it. Competitors may not use secrets obtained through such extraordinary means. If you learn trade secrets when working for one employer, you must not disclose them to anybody else, including another employer. If you work for some companies, and Apple is a good example, you may be required to sign a non-disclosure agreement that prevents you telling anybody even what project you're working on. Privacy is an area that's been in the news a great deal recently, and I expect it will continue to be so. One of the problems is that laws and social norms about privacy are changing rapidly. Traditionally, the following have been considered invasions of privacy: intrusion into the private life of somebody, appropriation of somebody's name or likeness, unreasonable publicity, or representing somebody in a false light. The area that's particularly under dispute at present is the borderline between appropriate data mining and illegal invasions of privacy. My advice to you is to be very careful about collecting personal data without the knowledge of the individual. This particularly applies to things like medical or financial data. And remember, there are special laws about the privacy of children. This is an area in which European law is stricter in protecting privacy than United States law. Several American companies have recently got into trouble in Europe, such as Google's policy on recording Wi-Fi locations. A few words about privacy in the workplace. Is what you do on your computer in your workplace private? Do you have a reasonable expectation of privacy? Well, one thing is certain. Work-related material on business machines is definitely not private. Some organizations, and most universities like this, treat private material on business machines as private. But this is not law, and I think the legal situation is that anything you do on a business machine is not private. I would certainly behave as though that were the case. Email is a particularly important case. Legally, email is like a postal letter. With a postal letter, there's an expectation of privacy in transit. But mail loses its special protected status once it leaves the letter carrier's grasp. When the postman puts it in a corporate mailbox, it's no longer private. So for email, there's an expectation of privacy while signals travel over the internet. But email loses its protected status at the mail server whether you've read it or not. The rule I would say is never send anything by email that you would not be prepared for your employer to see. The Electronic Communications Privacy Act says that all business communications belong to the business. And in fact, Deleting email can be ruled intentionally destroying company records. In corporate disputes, email is frequently subpoenaed, which is a way of saying that even if your employer wishes to keep email private, the courts may insist that they make it available to others. So the advice here is never send anything by email that you would not be prepared to be seen as evidence in a court of law. Private information. As a software developer, and particularly if you work as a system administrator, you may come across private information. For example, you may come across personal records such as medical records or financial information. You may come across information about dishonest, immoral, or illegal activities that your co-workers or other people are carrying out. Or you may come across corporate secrets that you are not supposed to know. So what should you do if you discover some of this information? The general rule is keep the information private. If you have any doubt whatsoever, for example, the information might imply serious criminal activities, consult your supervisor or senior manager. Do not take actions yourself. Some of these cases are very tricky indeed. Free speech is another tricky area. In the United States, the First Amendment protects most aspects of free speech, including news reporting, religious expression, etc. But there are major exceptions like state secrets, defamation, obscenity, racial hatred. Some aspects of free speech are governed by state laws, obscenity is an example, and there are big differences between states. Other countries may have different laws. For example, in some countries, blasphemy or criticism of the government may be prohibited. If you manage a website that allows users to express opinions on these controversial matters, make sure that you have policies and procedures to control the content. A few final words about employment law, personnel law. This tends to be state law, and every state has strict and complex laws about recruiting, hiring, termination, on-job conditions, and the terms and conditions of employment. If you supervise other people, you need to know the basis of these laws. Most employers run short courses for their supervisors or have a booklet with the key issues, and any organization apart from a very small organization will have a personnel department, a human relations department with experts in this field. My advice to you is if you have any questions, consult an expert, and in particular, consult experts if you ever consider firing somebody or other controversial action. You may not need a lawyer, but you certainly need a human relations expert. Some of this law applies to you. When you get a job, you will very likely have to sign an employment contract. This contract may be quite restrictive. It may restrict your next job. For example, you may not be allowed to work for a competitor. There may be trade secret involved. Non-disclosure agreements may prevent you from including all your experience on your resume. Or there's a question of contamination. Knowledge of trade secrets may prevent you working on similar projects for others. These are very important, and they may make you decide that you don't want to take a job. So ask about them before you accept. Recruiters will consider it perfectly reasonable if you ask about what contracts you have to sign before you accept a job, and certainly read the contracts before you sign them. A few words about internships. There are two ways in which some companies exploit interns. The first is pay. If, as an intern, you do any work for an employer, then you are an employee and must be paid at least minimum wage and overtime, and all the labor laws of the United States apply. Unpaid internships are only legal if they are true training programs. The United States Department of Labor has an excellent page on its website, which is referenced on this slide. The other way in which interns are exploited are employment contracts. Read the contracts, and if they contain unreasonable terms, tell the company which terms you do not find reasonable, do not sign, and if they will not accept a reasonable contract, don't go and work for them. Remember, you have bargaining power. Companies need people like you, and they should be falling over to make themselves pleasant places for you to come to. To end the lecture, here is a summary of the practical advice I want you to have. You need to be aware of the law, but do not pretend to be a lawyer. You need a professional, usually a lawyer, for contracts and licenses apart from very simple ones, for troubles like complaints, injunctions, subpoenas and so forth, for personnel issues, particularly firing. When you're in doubt, consult your supervisor or a senior manager. As a senior manager, there have been numerous occasions when people have come to me with questions that I've not been prepared to answer, and I've had to go to the organization's lawyers for advice. When you become a senior manager, you'll have access to the organization's lawyers. Make use of them.
Lecture 22, end of lecture. Lecture 23, People. Software is built by people, and people are the major expense in any project. This lecture is about how people work together in groups and how to manage people. There's also some discussion of the various possible careers in computing.
Software development staff have high salaries, and professional staff are the major cost of software development. As you know, people vary greatly in productivity. The differences come from several factors, from ability, education and training, motivation, and skill in interacting with colleagues and leaders. The work environment also has an impact on productivity. So how do you lead, motivate, hire, reward, and retain good people? There is a great deal of theoretical work on this subject. If you ever take an MBA, you will take courses in organizational behavior, where you will learn about industrial psychology, group behavior, cognitive fundamentals, and economic motivation. You don't need to know all this theory to be good at managing people, but you need to think about some of the issues. Here's a framework that I find very useful in thinking about people's motivation. It's called Maslow's hierarchy of needs, and you should read it from the bottom. Physiological needs, safety needs, social needs, esteem needs, and self-actualization. Physiological needs are food, water, breathing, sleep, very basic things. If these needs are not satisfied, people cannot think about anything else. Safety needs are security of person, health, and family. They come next. When they are met, people are very conscious of social needs, friendship, colleagues, and intimacy. They're followed by esteem needs, self-esteem, confidence, achievement, respect of others. And when all of these are achieved, people can focus on what's called self-actualization, the opportunity to reach full potential. Software developers, at least in the United States, are rarely troubled by the top two. Hopefully, the amount of money that all of you have satisfies the physiological and safety needs. Therefore, in thinking about people's motivation, you should think about the social needs, the esteem needs, and the self-actualization. Software is built by teams. There's a lot of experience to suggest that the best size for a team is from 3 to 8 people. The team members may include developers, who can be trainees or experts. There may be domain experts, there may be graphic or interface designers, software librarians, testers, and people with other skills. Every team must have an administrative leader, who is often called a manager, and a technical leader, who may be the manager but isn't always. Every team has administrative needs. They include personnel, assigning people to tasks, hiring, promoting, resources, including budgets, space and facilities, and equipment, project management, relationships with other teams, management and clients, project plans, and schedule. Depending on the organization, this administration may be done by a central group, or it may be done by the leader of individual teams. This chart may surprise you, but it's typical of how software developers spend their time. First of all, about 20% of the time it's non-productive. Non-productive in the sense that it's vacations or training or administration. About 30% is working alone. This is such things as doing designs or writing code. But about half the time is interacting with others in various ways. Since interaction with other people is so important, communication skills are a vital part of effective software development. Many organizations have weekly staff meetings for non-technical reasons. This is where the progress against the plan is reviewed. There will be numerous technical meetings. The modern practice is to have very brief technical meetings of the entire group on a daily basis. But there'll also be longer meetings, for example, a review of some design or program. I've always found that informal communication is an important part of managing software projects. For example, many organizations have a kitchen where people get together, or there's a doorway where the smokers meet, or people meet after work and talk informally about their work. I've often found when I have a break that to walk around the building and just talk informally to people is a good way of finding out about things that I didn't know. I was pleased to discover that there's actually a term in management theory for these walks. They're called tours. And finally, it'll often happen that when you talk to people, you discover there's some topic that requires greater discussion. And then it's good just to grab the people and have an ad hoc meeting straight away. Management of teams dispersed across locations requires special care. The first thing is to create a team sense. At one stage I worked for the American firm Tektronix in a small office in England. About once a week, Tektronix would show us a short movie of a different branch of the firm, perhaps the office in Ireland, and this way we felt we were all part of a large organization. Occasional face-to-face meetings are very valuable because the people get to know each other as individuals. They don't have to be frequent, but they should be regular, perhaps once or twice a year. And the entire team, including support staff, should be part of these meetings. Remote meetings on a regular schedule, such as conference calls, can work very well, particularly with technical and administrative groups that know each other and work together regularly. Finally, it's very important there should be a clear division of responsibility between the various locations. Meetings require leadership and a willingness by all team members to be led. If you're leading a meeting, here are some things to think about. Timekeeping. The meeting should start on time, people should not be late, and it should end on time, or earlier if the business is completed. There should be a clear purpose for the meeting with an agenda. For example, this meeting is for progress reports, or a design review, or a budget. Preparation. Materials should be circulated in advance with time for people to prepare, and they should be studied by all participants. Facilitation during meeting. Make sure there are opportunities for everybody to speak, and sum up to check agreement. Finally, it's very important that notes should be taken during the meeting by a scribe and circulated promptly.
There are many sources of advice on how to run meetings. Here is an excellent one. Since it stars John Cleese, it is very humorous, but it's also very serious. You can find a copy on YouTube.
Hiring good people is an essential part of leadership. When you're hiring, you're looking for people who will make your entire team more productive. Now here are some of the factors that lead to productivity. I've divided them into two groups. The group in black are general factors, and the group in red are specific. The black factors are ones that it's very difficult to acquire on the job. If people don't have these factors when you hire them, they're never going to gain them. On the other hand, the red ones, although they're very important, like knowledge of specific operating systems or certain programming languages, are skills that good people can acquire. I think in general there's an overemphasis on specific skills in hiring and not enough emphasis on the general skills in black here. So if you're hiring, really concentrate on make sure that you have people who are fundamentally able and maybe pay a little bit less attention to their specific skills. Once you've hired good people, you want to keep them. Staff turnover is expensive and disruptive. Here are some ways to keep good people. First of all, technically interesting work. Make sure that people have up-to-date hardware and software to work on, and give them opportunities to learn and experiment. Feelings of appreciation. Management recognition can be formal or informal, but make sure if people do good work, you tell them that it's been seen and you appreciate it. Money, benefits and promotion are always important, but they're sometimes overrated. Working conditions. Space, light, noise, parking, flexibility and hours, all are important. Finally, organizational dynamics. If people feel that this is a productive and happy organization, they will wish to remain part of it. You notice I barely mentioned salaries. Any software developer in the United States has plenty of money to live on. So salaries are actually used to satisfy the top level of Maslow's hierarchy. That is the self-actualization and esteem. So the absolute level of salary is less important than its relative value and how it's presented. So if you say to somebody, our average raise is, shall we say, 4%, but you're getting 5%, they feel appreciated. They feel that you think well of them. Or if you say, our salaries are in the top 25% of internet companies, assuming it's true, this helps people's esteem and helps them feel good about what they do and your organization. To build and maintain a strong team, everybody has a different style. Some people are direct, they give instructions and expect to be followed. Personally, I find that good software developers often have a lot of initiative and like to be given flexibility. But whatever your style, stick to it. In my experience, the following factors matter. Be consistent in how you relate to people. Be open about problems and how you're addressing them. Explain your decisions. Do not have secrets. Ask for advice and help. Be constructive in criticism of people outside your team. And support and attend social events. Above all, set high standards. Whatever your style, there are times as a manager when you must be firm. The assignment of tasks must be equitable and open. Everybody will have to tackle some of the dreary tasks. But if you explain why to them, the good people will be willing to do so. It is better to encourage people than to press them. Carrots are better than sticks. But if you see poor performance, you must address it, otherwise the rest of the team will be discouraged. Finally, nobody is indispensable. Sometimes you'll find somebody in an organization who thinks they're so important that they can do as they wish. This must not be allowed. The title of this slide is How to be Led. As a junior member of a team, what can you do to make it productive? Here's some suggestions. Follow the team's style of working. Understand the context of your work. Make practical suggestions. Ask for help if you need it. Accept less interesting tasks. Attend social events. And of course, above all, do good work. If you follow this advice, you'll find that very rapidly you become one of the leaders of the team.
Lecture 23, End of Part 1. Lecture 23, Part 2.
To turn a weak group into a strong one is one of the greatest challenges of leadership. I was fortunate in that the first senior position I had, I inherited a strong, well-functioning organization. But later on, I found myself in the position of taking over another organization which was not working well. Here are some of the things I learned. First of all, the art of the possible. You can only do certain things at any given time. Next, it's necessary to get the best people into the leadership positions, even if it means promoting young people over the old leaders. Next, use opportunities to reorganize. So if people leave or there are other external events, it's possible to use that as an opportunity to make improvements. Finally, very important to respect people. There are people in an organization who may not be functioning particularly effectively, but are doing their best. And it's important to respect those people, even while refusing to accept problem areas. Overall, to be persistent and firm is better than being brutal and abrupt, and to recognize that change takes time. To end this section, here's an old exam question. As leader of a software development team, you have hired 2 new members of staff. The first has just graduated from the Cornell MEng program in computer science with no work experience. The second has 5 years' experience in developing advanced applications, but has never worked on this type of computer. Some of the development tasks are more interesting than others. Some tasks are harder than others. Some are more time-critical than others. What approach would you use in allocating the tasks to these 2 new members? Here are some bad answers. These are actual answers. The Cornell graduate has more expertise to tackle the harder tasks. The Cornell graduate is used to time-critical tasks, course assignments. The Cornell graduate should be given interesting work to make him or her keen to continue with the company. Why do I consider these bad answers? Well, the first one, the Cornell graduate has more expertise. What makes you think that you're so superior to the other people? The Cornell graduate is used to time-critical tasks. Sorry, but course assignments are not real. They're not real time-critical tasks. The Cornell graduate should be given interesting work to make him or her keen to continue with the company. But at this stage, who cares if you leave? A raw graduate is still a trainee, the most junior person in the team, with much to learn and no experience of production quality development. Hopefully, the raw graduate has great potential, but at present it's still just potential. Here's some good answers. Both the people should have the potential to produce excellent software under tight time constraints. But both new employees need to learn the technical environment. Expect them both to work slowly until they learn the environment. The junior, that's the raw graduate, needs mentoring. The senior, the experienced developer, might work independently or might lead a team. The junior should not be put on time-critical tasks yet. The experienced developer might be. Both people should be given a mixture of more and less interesting tasks. You should discuss the allocation with them. Sometimes it's sensible to contract with another organization to carry out some or all parts of the software development process. When is this a good thing to do? First, the other organization might have expertise that your organization lacks. Or your organization might not have a large enough staff for a specific project. Again, sometimes the other organization might have lower costs. For example, it might operate in a country such as India, where costs are lower. For reasons such as these, most software for the US government is built by contractors, and outsourcing is a very sensible way to go in a lot of circumstances. But outsourcing has risks, and you should be aware of them. First of all, the other organization may not be as skilled as you expect. Undoubtedly, the staff of the other organization have their first loyalty to their own organization. The other organization may use different terminology or have a different culture. For example, the organization may not report problems to the client. Communication is a challenge. As well as geographic differences, there may be cultural differences. Unless the task is well understood, it may be difficult to write a contract that manages the costs and the results. For example, government contracts are notorious for cost overruns. Finally, if your organization contracts out all the interesting work, your good staff will leave you. Here is an example of what can go wrong. Company G was the world's leader in a specialized category of mathematical software, and G had successfully implemented several packages for various manufacturers. A computer company H contracted with G to develop a package for its new computer system. The package for company 8 was late, performed badly, and disliked by customers. At the same time, G was developing a package for another company, I. This package was very successful. What went wrong and what can we learn? When work is outsourced, the client must be vigilant. The client must take responsibility for managing the relationship between the project and the client's organization. The client must have a management and technical team that can track the work that's being done, monitor its quality, and review changes to scope. The contract should be explicit about expectations, deliverables, ownership of software, and mechanisms for payment. Above all, the client must be closely involved with user testing and must control the acceptance testing. In the example, Company H was not vigilant, and the contractor got sloppy. They put their less good people on the project, and they did not manage it properly. The result was a technical and financial failure. In the rest of this lecture, I want to talk about careers in computing. What will you be doing 1 year from now? More interestingly, what will you be doing 10 years from now? Well, many of you will be in careers outside computing. Some of you will be in careers in which you personally continue to do technical work, and some of you will be in careers in which you're responsible for the technical work of others. Finally, I hope that some of you will be entrepreneurs and you will have your own organizations. This is a great time to be an entrepreneur if you have computing skills. In recent years, computer specialists have founded many of the world's great companies. Here are the founders of Microsoft, Google, Amazon, and Facebook. You'll need management skills, but it's easier for a computer specialist to obtain management expertise than for a management generalist to become a technical expert. It's also easier to start young before you have family commitments, such as mortgages and children. Finally, don't be afraid of failure. It's quite usual to fail at the first attempt, but succeed later. This is one of the strengths of the American system. If you go into the computing industry, you'll find there are many ways to build a technical career. Here is the CS5150 model. We have a client in the middle with customers and users, and the client has relationships with the course team and with the software development team. Here is the equivalent diagram for a typical commercial organization. The client has communication with the technical marketing, with the product management, and with the development team. In this diagram, the development team is divided into two parts: software development and quality assurance. Each of these areas has its own manager, and leadership and coordination across all the groups is essential. One possible career is to remain purely technical. If you follow this route, you will find that there are very few senior positions which are purely technical. They are, for example, in industrial research or universities, and even these have substantial organizational aspects. However, there are numerous mid-level professional positions which are technical, and these can be state-of-the-art, or of course they can be dead-end if you get in the wrong organization. Computer professionals who stick with technical careers report considerable satisfaction from their work. Another interesting route is to be a product manager. A product manager's job is to ensure that the right product is built and the right trade-offs are made between timeliness, functionality, and cost. This requires an understanding of the marketing and business considerations, as well as technical options and design criteria. Product managers have to be good at communication among groups with different expertise and priorities. Many good product managers have technical and management trainee. For example, there may be a computer scientist with an MBA. Quite a lot of people from the information science department have gone into product manager jobs. A common career progression is from being a technical expert yourself to leading others who do technical work. Senior people must be familiar with both the strategic organizational aspects and the computing aspects of the work. These can include entrepreneurs, the chief information officer of an organization, or senior consultants. These jobs all require good technical insight, but they don't require detailed technical expertise. It's much more important to have organizational, marketing, personnel, and financial expertise. Product management is a good background for such positions. The Chief Information Officer is the senior person in an organization responsible for technology. Usually, this person is a vice president. Other job titles include Chief Technology Officer, and the background is usually a combination of technology and management. The Chief Information Officer may have worked as a consultant, possibly an internal consultant within an organization. It requires technical expertise, but the technical expertise is strategic rather than specific expertise. Many of you will follow careers outside computing. A computing background can be valuable in almost any career, such as general management, government, law, medicine, or philanthropy. Education in computing is an asset. Computing is a vital part of almost every organization, and an education in computing is an education in logical thinking and tackling large tasks systematically. Be careful though, because education in computing is a potential weakness. Not every problem can be solved by rational thinking alone, and you should always remember the importance of skills with people using judgment, and so forth. Some final words about career flexibility. Nobody knows the future of computing, but it's going to change. If you do not learn continuously, you are going out of date fast. So go to seminars and conferences and training courses. Be inquisitive. Discover things for yourself. And remember, technical expertise is most valuable when combined with other skills. So understand the organization that you're part of, its budgets, its marketing, its strategies. And develop organizational skills such as presentations and writing and how to lead a group. If you change organizations, behave in a professional manner. Show respect for the organization that you leave. Respect their trade secrets, though of course public information is not confidential. Take nothing with you except your personal items, and do not poach their customers or their staff. Then show enthusiasm for your new organization. Embrace the new culture, and do not criticize the new organization relative to the old organization.
Lecture 23, People. End of lecture. Lecture 24, Presentations.
Reports and presentations are an important part of software development. If you're ever to have a senior position in computing, you must be able to communicate, particularly with clients and with other technical developers. If you become a project manager, or if you're a consultant, or if you become an entrepreneur, you will frequently have to explain computing to senior executives who do not have a technical background. This lecture is about presentations.
The material discusses software presentations in general, but there's some hints about preparing for the CS5150 presentations. Full instructions for the CS5150 presentations are on the course website on the assignments page, and instructions for the reports are also on the course website on the assignments page. Presentations are an important part of software development. Here are some of the reasons you might do presentations. First of all, marketing to potential clients. Secondly, report of progress to senior management. Third, reports and demonstrations to your clients. And finally, communication with your colleagues on the development team. I know that some of you are uncomfortable making presentations. If you are uncomfortable, take every opportunity to gain experience. It's difficult to have a leadership position in computing if you cannot make decent presentations. I don't expect you to make great presentations. Not everybody is a great presenter. But you'll find that with practice, everybody can be well prepared and do a decent presentation. So presentations begin with planning. The first part of planning is to work out your objectives. What is the purpose of the presentation? What are you trying to achieve? The next thing is who will be there? How much time will you have? How will you use the time? Think about the room. What equipment is available? Will there be a computer and network for demonstrations? The CS5150 presentations are to both the client and the instructor, with the teaching assistant as a secondary audience. When you plan for them, allow lots of time for questions. Expect interruptions. You'll find that I ask questions continually through your presentations, and you've got to have time to answer them. Now think about the topics for your presentation. Every project is different. Every presentation is different. But here are some suggestions. There's some general topics which apply to every project. First, a description of what you are planning to deliver to your client, a shared definition of success. Next, You might want a summary of progress since your last presentation or report. Perhaps this is a good time to talk about your testing, your test plan and test cases. Very likely your audience wants to know about unexpected events and risks. And at the end of your presentation, it's often good to give an overview of the plan to complete and deliver the project. There's some specialized topics that apply to many projects. If usability is important, the results of user testing. If you have a technical client, discuss the technical issues. If you have a demonstration that you can give, this is always good. So if you have a mock-up, a prototype, a demonstration, or part of the system that's operational, show it. And usually it's better to show it first and then discuss it, rather than to talk about it before showing it. The first CS5150 presentation is very important. It's the first time that you as a development team get to discuss your project with the client and the instructor at the same time. Let me suggest 3 general topics that you should try to achieve. One is, now is the time to make sure that the client and the team have agreement on the scope and the goals. So present the assumptions and decisions. You might say, the project will be a success if, and then go into details. Secondly, give a progress report. What have you done so far? Perhaps you have got the requirements and their preliminary designs. If so, here's what you might say. This is an understanding of your requirements. Then you might show mock-ups, prototypes, designs, anything to help the client and the instructor understand where you are and how the project is going. Finally, the schedule and plan. This is of particular interest to me. I want to know what you've done since the feasibility study, what have you learnt, whether there are changes in plans, whether there are any problems, what risks you've found, and do you have a reasonable plan to complete the project by the end of the semester. Now for the materials that you might prepare for a presentation. First of all, visual aids. It's useful but not essential to have visual aids such as slides. Here's some hints how you might prepare them. The most important rule is keep them simple. Your aim is to convey information, not to entertain the audience. They must be legible. Remember that the audience members may have poor eyesight. And remember also that what looks good on your personal computer may not look good on a projection display in a meeting room. For this reason, use large fonts for text. I would suggest no fonts smaller than 20 point. Use light backgrounds, dark letters, and dark lines on diagrams. If a diagram is complex, too complex to be legible, divide it into parts and show separate parts on several slides. Finally, avoid the common Microsoft templates. If you see many presentations, as I do, you get very bored with seeing the same templates. Next, handouts. If you wish to provide your audience with a handout, do not hand it out at the beginning of your presentation. Perhaps you might hand it out several days in advance, or you might hand it out at the end of a presentation, but not at the beginning. Demonstrations. Demonstrations are great, but they need preparation and practice to do well. So rehearse them and rehearse the technical side as well as the script of what you're going to do. Load and configure all the software before the presentation, check it, and then do not change anything. If you need test data, create it in advance. If you have to type complex commands to run a demonstration, do so before the presentation. For the demonstration, prepare a script. That is, decide which sequence of user interactions you're going to go through, the examples that you're going to use, who will do which tasks, and how you're going to clean up at the end for another demonstration. Remember, you may be interrupted in the middle, and then you're going to have to continue or even go back in your demonstration, so be prepared for that. And remember to tell the audience what they're seeing. I always want to know, am I looking at an operational system? Am I looking at a mock-up with dummy stubs, a prototype? Just tell me, okay? As well as the content, think about the logistics. You need to have a rehearsal to check the visual aids and the demonstrations, and after the rehearsal, change nothing, okay? If you have a presentation with several presenters, there's two ways you can organize it. One is you can have one person act as a chair, and that person can call on the other members of the team. The other way is for each person, after they've presented their portion, to hand over to the next person. Both ways work, but think about it in advance. As part of your rehearsal, check out the equipment in the meeting room. What network will you use, if any? How will you connect a computer? Which computer will you use if you want one? Be very careful about firewalls. You may have developed your software one side of a firewall. Is the meeting room able to access data across the firewall? For the CS5150 presentations, you've got 3 presentations. As part of the course, everybody must be the presenter for at least part of one presentation during the course. So think ahead when your inexperienced people are going to present. Usually inexperienced people are most comfortable in describing work which they actually did themselves. But be sure to avoid too much technical details that are not appropriate for the audience. Now for the actual presentation. At any moment during the presentation, there'll be one person presenting. That person should stand. The other team members should sit patiently. There will often be questions and ideas that come out during the presentation, so one team member should be appointed to take notes. I recommend that the first presenter should introduce everybody and repeat this at each presentation. If you're presenting and you're asked a question, if you know the answer, answer it. Or, if you're asked a question that you don't know the answer, ask another team member to answer. Otherwise, make a note and reply later. But what you should never do is interrupt your colleagues. If somebody else is presenting and you have information to add, raise your hand and the presenter can decide whether to call on you or not. But never interrupt. Now for the final presentation. What do you want to achieve? Well, one thing is personal and team satisfaction in handing over a good piece of work to the client. You want to complete the course in good style, and of course you want to get a good grade. And you want a clean handover to the client without loose ends. This may be a basis for future work with the client, other members of the team, or with this project. Who is the audience and what do they want? First of all, let's think about the clients. The clients have invested effort in this project. They want to know, is it ready for production? Should they invest more effort into bringing it into production? Or should they abandon the project? What about the course team? What has been accomplished? What has been learned? Is your client satisfied? Are you handing over a maintainable system? As you prepare for this presentation, remember that you only have 45 minutes. You can't describe everything that you've done during the semester. The most important thing is a demonstration of an operational system. Show the system in operation, but be honest about gaps and weaknesses. You should have a short presentation to go with your demonstration, and you can use that to review the goals, a summary of the achievements and gaps, and a summary of what is being delivered. It's also an opportunity for a discussion with the instructor and with the client.
Lecture 24,
End of lecture. Lecture 25, Professionalism.
This lecture is about professionalism. By professionalism, I mean an approach to software development that takes into account the interests of all the stakeholders and produces good quality software in a responsible manner. The examples are taken from my own career. Some are successes, some are disappointments, but there's a lesson to be learned from each one.
I begin with some personal thoughts about software engineering. The software industry needs to take more responsibility for its products. Let's look at some of the problems. Products are sold or licensed with no guarantees about whether they work as advertised. Time to market dominates much of software development, often at the expense of quality. We know how to develop much more reliable and secure software, but reliability and security often have low priority in business plans. We can compare software with the car industry. Not very long ago, the car industry was dominated by fashion and style. Safety and reliability were considered unimportant. Then the industry was shamed by organizations that pointed out how unsafe their cars were, and they found that cars coming from countries like Japan sold on their reliability. Nowadays, the car industry produces vehicles which are much safer and much more reliable. We know that too much software development is wasted. Projects are often begun with poorly thought out scope. Senior management often pays little attention to computing, though it's a strategic area of almost every organization. Technical teams are often poorly led, and we do not have a good methodology for education in software development. I mentioned what used to be called a thick sandwich. This was an educational system in which people alternated an apprenticeship working on practical problems alongside professionals with formal education in the classroom. I think this approach is much better than our technique of 4 years of classroom education followed by practical experience. There is an article on this topic in IEEE Spectrum. It's called Why Software Projects Fail, and the subtitle is We Waste Billions of Dollars Each Year on Entirely Preventable Mistakes. Software development projects can fail in many ways. There's the software engineering triangle, in which people are trying to trade off whether they should be late, over budget, or their product should lack function, be full of bugs, and have bad performance. But there's also changing circumstances, changing markets, better alternatives, changes of management. I would argue that the biggest single source of problems is poor understanding between the client and the development team, and that's been a theme throughout this course. I am now going to give you some examples of software projects that encountered problems. In some of them, the problems were successfully overcome. In others, the projects were total failures. Most of the examples are based on my own experience, successes and failures. Some are recent, others happened many years ago, but I think the themes are completely relevant to today. I've hidden the names of the organizations and the dates, but these are all true examples. Because my experience has been mainly with universities, not-for-profits and government agencies, most of the examples, but not all, are from those areas. The first example could easily happen to you. A development team at a university was given government funds to build a high-performance gateway from Protocol X to Protocol Y. A promising young developer was hired and assigned to the task, but the project was too difficult for him. He just didn't have the technical skills and experience. Unfortunately, he hid his problem for many months. Eventually, the project was cancelled, having produced nothing of value. So what can we learn from this experience? The first thing is, if you're ever in that situation, ask for help. when your team leader says to you how you're doing, saying, I'm having difficulty. On the other hand, the team leader was at fault because the team leader didn't pay attention to a new person who he should have been monitoring more carefully. This was a failure of leadership by a very experienced leader. Here's another example. This is one of mine. A university developed a novel programming language for educational software. For several years, the language showed considerable promise. It was used successfully for a number of projects. But after a few years, it was clear the language was not gaining acceptance and that it was being left behind by alternatives. But we continued the development for many more years. I think we cost the university about $500,000. Why didn't I cancel this? The answer is a question of dynamics in the personnel involved. The president of the university really liked this project. It was one of the projects he talked about when he talked about the university. I had good relationships with the president, but I did not want to use up my good relationship in cancelling his favourite project. Therefore, I kept it going one more year and then one more year until eventually it had to be cancelled. Here's an example that is surprisingly common. An organization had antiquated administrative systems. Senior management, not involving senior technical staff, decided to replace them all with commercial packages from a well-known vendor. The timetable and budget were hopelessly optimistic. They were basically the timetable and budget that the marketing people from the vendor proposed. Then work began. The staff knew they could not do the job with the resources they had in the time. They became dispirited, and many of the best people left. The chief information officer very sensibly found another job, and a new chief information officer was appointed. So what should she do? Well, she did exactly the right things. First of all, she was very upfront with everybody involved, up to the president of the organization, about the problems. Then she looked around and realized that actually some good work had been done. She decided, with support from the president, to continue and finish that part of the work and to cancel the other 3/4 of the project. This cost the organization a lot of money, but at least they got something concrete out of their investment. The next two examples are quite similar. In the first one, a university had a big joint project with a company to develop new system software. After 2 years' work by a largish team, a junior software developer persuaded the university that this technical approach was wrong. The system architecture was just not going to work very well. So what should the university do? What should the company do? I was not involved, so I cannot really answer those questions, but I can tell you what they did. The university said, we're going to stop work, start again, and do it properly. The company said, we're too far along with this, we can't change, and we will continue as we're going. We need a product to take to market. Interestingly enough, the university, because it started again with a better architecture, managed to finish their version of the system almost about the same time that the company finished theirs, and the university version was much better. The other one may or may not be true, but I believe it is historically correct. The company, and this time I will name the company, it was Microsoft, and it had a very big project to develop a new computer operating system. After several years of work by thousands of people, the head of the company, that was Bill Gates, reviewed the project and decided that the technical approach was wrong. So what should the company do? Well, apparently, and I believe this to be true, he basically said, stop, we will go back and we will do it properly. And of course, the Microsoft operating systems under Bill Gates' leadership were tremendously successful. Here is an interesting example about the dynamics of organizations. A not-for-profit corporation that I worked for developed a system for a government organization. After 3 years, we had all the major components and the system had been demonstrated successfully with real users. I left the organization, I came to Cornell, but 9 years later I discovered the system was still not in full production. The reasons that were given were incremental improvements to the software, repeated requests for more functionality, reluctance to reorganize clerical staff. But the real reason was that nobody had a sense of urgency. Nobody in the government organization really was committed to making this change to their organization a success. Here is an example I feel pleased about. A group at the university where I was in charge of computing developed innovative user interface software, which was technically superior to any commercial alternatives. At the same time, a group at another university was doing work in the same area. The leader of that work considered the work that we were doing to be more advanced, but that university had an industrial partner, and the industrial partner planned to turn their work into a product with massive support, while nobody was committed to supporting the work that we were doing. So what should we do? We looked at where we were and where we might be in a year or two's time, and it was clear that our work was not going to be successful in the long term. It needed much more resource than we could ever put into it. Therefore, we cancelled our project fairly early and merged some of our work into the mainstream work being done at the other university. In this way, our resources were available to work on other innovative projects. Here's an example of being overtaken by events. A university group that I was in charge of had a project to develop a large application suite for libraries. We had funds from a company, from private foundations, and the government. After several years, we had an extensive system running at the university, and the company was marketing the technology to its customers. It was a success. But technical management at the company and our group became convinced that the times had changed. There were better protocols and formats than those we had chosen, and the system was not going to succeed in the long term against the competition. So what should the company do and what should the university do? Well, the company did exactly the right thing. They cancelled the project. And what should the university do? I think we did the right thing. We basically froze the system as it was in operation and merged the new technology into it over a period of years. I'm not sure what conclusions to draw from the next example, but it's an interesting example of the dynamics of large corporations. A company gave a university $1 million to port a new operating systems to its personal computers. I was actually the leader of this project, and the grant was given to a group that I led. The work was very well done, on time, and technically a great success. But when we came to deliver it, the company had changed its president, all the senior technical people we'd worked with had gone, and the work was wasted. Many years later, and several presidents later, the company has built its future around a modern version of the same operating system. In fact, a graduate student from the university who worked on this project became the senior vice president of the company and introduced its modern generation of software. Here is one of my greatest disappointments. The National Science Foundation wanted a very large computer system. The approach they took was to give grants to 6 organizations, basically 6 universities, to develop demonstration projects. They hoped that the 6 organizations would then submit a single multi-million-dollar 5-year proposal and develop the production system together. But there were differences, technical and personal, between the organizations, and it became obvious that this was not going to work. I was one of the people who kept trying to make it work, but 3 weeks before the proposal was due, I decided the plan was doomed to failure. One of my colleagues at the time said, "Why did it take me so long to see the obvious?" Anyway, what should I do? I first of all said, that we were not going to go along with the six organizational plan. And two of the other universities said they would join with us. So the three universities, in a great hurry, put together a reasonably good proposal to do the entire job themselves, and we received the contract from the National Science Foundation. Why do I consider this a disappointment? Why is this a failure? The reason is that in 3 weeks, we did not have time to really work out the organizational structure we needed for success. And although we received the reward of the grant from the National Science Foundation, we had put together a team that was not capable of doing the job we wanted.
Lecture 25, end of Part 1. Lecture 25, Part 2.
What can we learn from these examples? The examples are very different, but in every case, the difficulties are about relationships between senior management, technical management, development teams, and individual developers. When this was a good relationship, tough decisions were made and the problems were resolved or at least minimized. When this was a bad relationship, nobody faced up to the problems and the waste of resources continued. Only too often we see organizations that work like this. Directors and shareholders appoint the president, and the president wants to be a success. The president does not want to admit failures. The president appoints the chief information officer and tells the chief information officer to be successful. The chief information officer does not want to admit failures, appoints computing managers, and they do not want to admit failures. The computing managers appoint the developers, and the developers do not want to admit failure. So everybody is under pressure not to admit problems, and everybody pretends that things are going well. Eventually, the troubles cannot be hidden, and people just try to blame each other. The directors and the shareholders try to blame the president. The president tries to blame the chief information officer. The chief information officer tries to blame the computing managers and also grumbles about the president. The computing managers try to blame the developers and grumble about the chief information officer. The developers grumble about the managers. We have a thoroughly unhappy and unproductive organization. So, what can we do better? First, we have to admit that there are going to be problems. Major computing projects are very complex. Inevitably, there are delays and failures. And few organizations know how to manage risk and uncertainty. The best chief information officers put a lot of effort into managing their organizations to minimize risk. For this, they have the confidence of the staff, and the staff keep them truthfully informed, and they have the self-confidence to keep their seniors truthfully informed. So managing risk and managing projects to avoid risk begins with visibility. Open and visible software processes avoid surprises. They will need continual review of requirements, and as we've seen, there's got to be a willingness to modify or even cancel projects. Visibility and risk management is one of the reasons we aim for short phases, each with deliverables or incremental methods of software development. Here is an example about visibility. You saw the example earlier in the lecture on reliability. An ambitious leader had created a library consortium whose success depended upon a large, innovative computer system. The system was continually failing, running very slowly, losing important data, and so forth. The board hired me as a consultant to advise them whether to abandon the entire consortium. Over a period of a few days, I talked with the technical staff. The staff had a technical plan to solve the problems, but they needed time. And the ambitious leader had continually promised unrealistic delivery dates. I simply asked the technical team for a cautious timetable. and then explained it to the board. The technical team had the timetable, it's just nobody had asked them for it. The board approved the extended timetable, which turned out to be quite accurate, and the consortium was successful under a different leader. So what can we learn from this example? It's a simple example of bad visibility. If anybody had asked the people who were doing their work for their honest opinion, they would have never got into these problems. I'm slightly hesitant about the next example because it's an old one, but it's a very good example of changing the requirements and changing design as external circumstances change. In 1994, a not-for-profit organization developed a high-performance distributed system to map names to resources. That date is very important because it's just when the first glimmerings of web technology were emerging. But in 1994, there was only one web browser, that was Mosaic. There was no way to download code like Java applets. Mirroring and caching utilities were not available, and there was no commercial interest. The software was written in 1994 and not used very much. But with the web technology expanding and commercial interest in web technology expanding, the organization kept going, and they rewrote the software, greatly improved it, changed the requirements, used modern technology, and today it's widely used. You might jokingly say, if a job's worth doing, it may be worth doing twice. Certainly it was in this case. That example shows how external changes can affect a software project. Large software projects typically take at least 2 years from start to finish, often much more. You can sometimes divide them into 2 phases, a formative phase in which changes of plan are fairly easy to accommodate. This goes up through the system architecture. But once you get into the detailed implementation phase, it's almost impossible to make fundamental changes. So you want to keep that phase as short as possible. Incremental methodologies such as Agile aim to apply the advantages of small teams and short development cycles to large projects. So the phase in which you cannot make changes is very short. I want to end this section on managing risk with a few words about how to stop gracefully. Cancelling a project is difficult. It's much harder to cancel a project than to start one. And it's much harder to withdraw a service than it is to introduce ones. One of the things is the personalities of people involved. The people who wanted the system, the people who argued for the system, the advocates, must now reverse their public stance. People have got to manage the expectations of all the stakeholders. If there's a service, the users of the service need a migration strategy. You can't just turn things off. And the technical staff must have a graceful way forward. If people have been working very hard on a project for a long time, you cannot just suddenly cancel them and expect them to be happy. In general, if a project has to be cancelled, it's much easier to do it early rather than late in the development cycle. I hope you'll agree that these examples demonstrate that software development, and particularly the leadership of software development, demands a high degree of professionalism. This leads to the question, is software development a branch of engineering and should we treat it as such? The answer to all such questions is the same. It depends on how you define engineering. Some years ago, I was on the board of the ACM when there was a proposal in a state legislature to license professional engineers in software engineering. And the question was, what role should ACM play? What we did was we looked at the definition of engineering, and we found that there were 2 fundamentally different definitions. One is this. Engineering is the profession of creating cost-effective solutions to practical problems by applying scientific knowledge and establishing practices, building things and taking responsibility for them. With this definition, software development is clearly engineering. But there's a second definition of engineering. An engineer is a professional who is licensed by a professional society based on a set educational program with a standard body of knowledge and specified experience, and who is the only person permitted to oversee certain tasks. If this is your definition of engineering, it's hard to see it applied to software development. I want to end this lecture by talking about professional responsibility. This example comes from the book by Flieger. A software system fails and several lives are lost. An inquiry discovers that the test plan did not consider the case that caused the failure. Who is responsible? The testers for not noticing the missing cases, the test planners for not writing the complete test plan, the managers for not having checked the test plan, or the client for not having done a thorough acceptance test. Here is my answer to the question. What are the professional responsibilities for the software developers and testers? The professional responsibilities start by carrying out assigned tasks thoroughly and in a professional manner. But there's more than that. It's being committed to the entire project, not just to the tasks that have been assigned to you. Resisting pressures to cut corners on vital tasks, and alerting colleagues and management to potential problems. If you behave in this manner and things go wrong, I don't think you should feel too badly about the things that go wrong. What about the computing management? Well, their responsibility begins with organizational culture that expects quality. They need to appoint suitably qualified people to vital tasks such as testing safety-critical software. They need to establish and oversee the software development process, and they need to provide time and incentives that encourage quality work. They have a responsibility for working closely with the client, and they need to accept the responsibility for the work of their team. The client has very similar responsibilities. Again, an organizational culture that expects quality, and the appointment of suitably qualified people. Reviewing the requirements and designs carefully. Establishing and overseeing the acceptance process. Providing time and incentives that encourage quality work, and working closely with a software team. And the client should accept responsibility for the resulting product. The conclusion. Professional responsibility runs throughout software development. Organizations put trust in software developers. They expect you to be competent. Software that does not work effectively can destroy an organization, literally. They expect you to handle confidentiality. Software developers and system administrators may have access to highly confidential information. They expect you to be aware of the legal environment. Software exists in a complex legal environment. And they expect you to be aware of acceptable use and misuse. Computer abuse can paralyze an organization. These are themes that we introduced right at the beginning of the course, and they run all the way through software development. Lecture 25, end of lecture.